What if I told you that everything you think you know about our solar system is only the surface of a much deeper story, a simplified version of something far more complex, far more chaotic, and far more mysterious than the clean diagrams we've all seen in books or online? Because when we imagine the solar system, we picture something orderly, something predictable, the sun glowing at the center while planets move in calm, perfect orbits around it, each one neatly placed, each one fully understood. But the truth is that this image hides almost everything that actually makes the solar system fascinating. Because our solar system is not just a collection of planets, it is a dynamic system that is still evolving, still changing, still shaped by forces that operate on timescales so large that we can barely comprehend them. And as we look deeper, we begin to see that there are entire regions filled with objects we rarely talk about. Ancient remnants of the early solar system drifting far beyond the visible planets. Massive distances where sunlight becomes weak and time itself feels slower. Where objects move so gradually that a single orbit can take thousands or even millions of years. And within these distant regions, there are patterns that don't fully make sense, objects that move in ways that suggest something unseen is influencing them. Hints that our solar system might not be as complete as we think. And beyond that, there are visitors from outside, objects that were not born here, traveling between stars and briefly passing through our system, reminding us that the boundary between our solar system and the rest of the galaxy is not as clear as we once believed. So what we are about to explore is not just a list of planets, but a journey through a system that is still full of unanswered questions. From worlds that have remained almost unchanged for billions of years to others that may still be evolving right now. From environments that are completely hostile to anything we know to one very special planet that somehow exists in a delicate balance that allows life to thrive. Because the deeper we go, the more we begin to realize something important. We are not just exploring space. We are exploring a system that is still revealing its secrets. My name is FD, you're watching Universe Stuff, and in this series we're going to explore every planet in our solar system, step by step, uncovering the mysteries, the science, and the hidden details that most people never hear about. So sit back, relax, and enjoy the journey. There is a planet in our solar system that lives closer to the sun than any other world. A planet that exists in a place where heat, radiation, and gravity create conditions so extreme that they push the limits of what a planet can endure. And yet, despite being the closest planet to the sun, it is also one of the least understood. A small, dense, and heavily cratered world that for a long time remained hidden in the sun's glare, difficult to observe, difficult to explore, and easy to underestimate. This planet is Mercury. At first glance, Mercury might seem simple, almost insignificant compared to the larger and more visually striking planets farther out. But this simplicity is deceptive, because Mercury is a world defined by extremes, a place where the surface temperature can rise high enough to melt metal during the day, and then drop to levels colder than deep space at night, a planet where a single day lasts longer than an entire year, creating a rhythm of light and darkness that is completely different from anything we experience on Earth. But what makes Mercury truly fascinating is not just its environment, but its story, because everything about this planet suggests that it has experienced events that we don't fully understand, from its unusually large metallic core to its strange rotational behavior, from its ancient, cratered surface to the unexpected presence of water ice hidden in permanent shadows near its poles. A discovery that challenges the very idea of what is possible so close to the Sun. And as we begin to study Mercury more closely, we start to see that it is not just a simple rocky planet, but a world that holds clues about the early solar system, about violent collisions, about planetary formation, and even about the fundamental laws of physics themselves, because Mercury's orbit around the Sun was one of the first pieces of evidence that led to a deeper understanding of gravity, showing us that even small discrepancies in motion can reveal profound truths about the universe. So as we begin this journey with Mercury, we are not just looking at the first planet in the solar system. We are looking at a world that challenges our expectations, a world that forces us to rethink what a planet can be, and a world that reminds us that even the closest and most familiar objects in our cosmic neighborhood can still hold mysteries that we have yet to fully understand. If you could somehow stand on the surface of Mercury, the first thing you would notice is not the heat, not the silence, but the sky, because unlike Earth, where the sky is blue and filled with atmosphere, on Mercury the sky is completely black, even during the day, a deep and endless darkness where the sun appears not as a gentle source of light, but as an overwhelming, blinding force dominating the horizon, larger and more intense than anything we have ever experienced. A star that feels almost too close, almost too powerful to look at directly. And this is where Mercury immediately begins to feel different from every other planet, because it exists in a region where the sun's influence is not just strong, but dominant, shaping everything about the planet from its temperature to its motion, from its surface to its internal structure. And yet, despite being so close to the sun, Mercury is not a world of constant heat, but a world of extremes, where temperatures swing violently between day and night, rising above 400 degrees Celsius under direct sunlight, and then dropping to nearly minus 180 degrees Celsius in darkness, creating one of the most dramatic temperature differences anywhere in the solar system. This happens because Mercury has almost no atmosphere, nothing to trap heat, nothing to distribute it across the planet, meaning that each part of the surface experiences conditions almost independently, as if the planet is unable to regulate itself, unable to smooth out the extremes, leaving it exposed to the full intensity of space, where energy arrives directly from the sun and then escapes just as quickly once the light disappears. But what makes this even more unusual is how slowly Mercury rotates, because a single rotation takes about 59 Earth days, while its orbit around the sun takes only 88 days, creating a strange resonance where the planet rotates exactly 3 times for every 2 orbits, a relationship that leads to an almost surreal experience on the surface, where the sun does not simply rise and set in a predictable pattern, but instead behaves in ways that would feel completely unnatural, appearing to pause in the sky, move backward, and then continue forward again, a consequence of the complex gravitational interaction between Mercury and the Sun. And this interaction is incredibly strong, because Mercury is so close to the Sun that it experiences tidal forces that have shaped its rotation over billions of years, locking it into this resonance, stabilizing its motion in a way that minimizes energy loss. And yet, even within this stability, there is complexity, because Mercury's orbit is not perfectly circular, but highly elliptical, meaning that its distance from the Sun changes significantly over the course of its year, bringing it closer at some times and farther away at others, which further influences how sunlight interacts with its surface. So when you imagine standing on Mercury, you are not just imagining a hot, barren world. You are imagining a place where the very concept of time and day feels unfamiliar, where the sky remains black, where the sun dominates everything, and where the surface exists in a constant struggle between extremes, unable to reach equilibrium, unable to soften the conditions that define it. And yet, despite all of this, Mercury is not chaotic in the way we might expect, because its motion is governed by precise physical laws, by gravitational interactions that can be calculated and predicted with incredible accuracy. And it is within these precise motions that we begin to uncover something deeper, something that connects this small planet to some of the most important discoveries in physics. Because Mercury is not just a planet, it is a key to understanding how gravity truly works. There is something about Mercury that quietly breaks the rules, something subtle enough that it went unnoticed for centuries, and yet important enough that it would eventually change our entire understanding of the universe. Because when scientists began carefully tracking Mercury's motion around the Sun, they discovered that its orbit was not behaving exactly the way it should, at least not according to the laws of physics as they were understood at the time. And this small discrepancy, almost invisible at first, would become one of the greatest scientific mysteries of the 19th century. Because Mercury does not simply orbit the Sun in a perfect, repeating ellipse. Instead, its orbit slowly shifts over time, a motion known as precession, where the point of closest approach to the Sun moves slightly with each orbit, tracing out a slow rotation that takes place over many years. And while most of this motion could be explained by the gravitational influence of other planets, there remained a tiny difference, a small amount of precession that could not be accounted for, no matter how precise the calculations became. At first, scientists believed that there must be something else causing this effect, perhaps an unseen planet closer to the Sun, a hypothetical world that they called Vulcan, or perhaps some unknown force acting on Mercury. But despite years of searching, no such planet was ever found, and the discrepancy remained, a small but persistent flaw in what was otherwise a very successful theory of gravity. And then in the early 20th century, everything changed. Because when Albert Einstein introduced his theory of general relativity, he proposed something radical, something that went far beyond Newton's idea of gravity as a force acting between objects, instead suggesting that gravity is the result of the curvature of spacetime itself, that massive objects like the Sun actually bend the fabric of space and time around them, and that this curvature affects the motion of objects moving nearby. When Einstein applied his equations to Mercury, something incredible happened, because the missing piece of the puzzle, the unexplained precession, suddenly made sense. His theory predicted exactly the amount of shift that had been observed, solving a problem that had remained unsolved for decades, and providing one of the first major confirmations that general relativity was not just a theoretical idea, but a real description of how the universe works. And this is what makes Mercury so unique, because it is not just a planet orbiting the Sun. It is a place where the effects of space-time curvature become noticeable, a natural experiment where the influence of a massive star is strong enough to reveal the deeper structure of reality, something that we cannot easily observe with planets that are farther away, where these effects become much smaller. But the implications go even further, because if gravity is not just a force, but a property of spacetime itself, then the motion of every planet, every object, every system in the universe is connected to this underlying structure. And Mercury, in its small and subtle way, was one of the first places where we were able to see this connection, to measure it, and to confirm that our understanding of the universe needed to change. So when we look at Mercury, we are not just looking at a world of craters and extreme temperatures. We are looking at a planet that helped unlock one of the deepest truths in physics, a world that sits at the boundary between classical mechanics and modern relativity, quietly demonstrating that even the smallest differences in motion can reveal something profound about the nature of reality. And as we continue to explore Mercury, we begin to realize that its importance goes far beyond its size, because it is not just the closest planet to the Sun. It is also one of the closest connections we have to understanding how the universe itself is structured, how space and time interact, and how gravity shapes everything we see. If there is one mystery about Mercury that stands out above all others, it is this: it should not look the way it does, because when scientists compare Mercury to the other rocky planets in our solar system, something immediately feels wrong, something doesn't quite fit, and that something is its structure, because Mercury is far too dense for its size, far too dominated by its metallic core, as if most of the planet's outer layers are simply missing. Because under normal conditions, when a planet forms, it develops a layered structure, with a dense core surrounded by a thick mantle and crust. But Mercury does not follow this pattern. Instead, its core makes up the majority of the planet, leaving only a relatively thin outer shell. And this has led scientists to ask a very simple but very unsettling question. What happened to the rest of Mercury? One of the most widely accepted explanations is that Mercury did not always look like this, that in its early history, it may have been a much larger planet, more similar to Earth in composition, with a thicker mantle and crust, until something catastrophic occurred, something powerful enough to strip away a significant portion of its outer layers, leaving behind the dense core that we see today. And the most likely candidate for such an event is a massive collision, an impact so violent that it would have reshaped the entire planet, sending vast amounts of material into space, material that may have been lost forever or perhaps even contributed to the formation of other objects in the early solar system, a process that would have fundamentally altered Mercury's identity, turning it from a more typical rocky planet into the unusual metal-rich world we observe today. But this raises another question, because if such a collision did occur, why does Mercury still exist in its current form? Why was it not completely destroyed? And how did it retain enough of its structure to remain a planet? And this is where things become more complex, because simulations suggest that such an impact would have required very specific conditions, a particular angle, a particular velocity, a particular set of circumstances that allowed Mercury to survive while losing much of its outer material. And yet, there is another theory, one that does not rely on destruction, but on formation itself, suggesting that Mercury may have formed in a region of the early solar system where temperatures were so high that lighter materials could not condense, leaving only heavy, metal-rich elements behind, which would naturally lead to a planet with a large core and a thin mantle, a world that was unusual from the very beginning, shaped not by a violent event, but by the conditions of its birth. Both of these theories tell very different stories, one of destruction and survival, the other of formation under extreme conditions, and at the moment, we do not know which one is correct, or if the truth lies somewhere in between. But what we do know is that Mercury is not a typical planet. It is an outlier, a world that challenges our understanding of how planets form and evolve. And this is what makes Mercury so important, because by studying it, we are not just learning about one planet, we are learning about the processes that shape entire planetary systems, about the role of collisions, about the influence of temperature, and about the delicate balance that determines what a planet becomes over time. Because Mercury is not just a planet that exists close to the Sun. It is a planet that may have lost part of itself, and in doing so, it became something entirely different. When we look at Mercury from a distance, it may appear like a simple gray sphere, quiet and unchanging. But the moment we begin to examine its surface in detail, we discover something far more complex, a landscape that tells a story stretching back billions of years, a story written in impact scars, fractures, and ancient plains, a surface that has remained almost untouched since the earliest days of the solar system, preserving a record of a time when collisions were constant and violent. Because Mercury's surface is one of the oldest in the entire solar system, heavily cratered and marked by impacts of all sizes, from small pits to massive basins, each one representing a moment when another object, traveling through space at incredible speeds, collided with the planet, releasing enormous amounts of energy and permanently altering the landscape. And unlike Earth, where erosion, weather, and tectonic activity constantly reshape the surface, Mercury has no atmosphere, no water, and no active plate tectonics to erase these features, meaning that its surface has remained largely unchanged for billions of years. And among these features, there is one that stands out above all others, a structure so large and so dramatic that it dominates an entire region of the planet, known as the Caloris Basin, one of the largest impact basins in the solar system, formed by a collision so powerful that it likely sent shockwaves through the entire planet, creating fractures and distortions even on the opposite side of the globe, a reminder of just how violent the early solar system once was. But the surface of Mercury is not only shaped by impacts, because there is also evidence of volcanic activity, vast smooth plains that appear to have been formed by ancient lava flows, suggesting that at some point in its history, Mercury was geologically active, with molten material rising to the surface and covering older, heavily cratered regions, creating a contrast between ancient terrain and slightly younger volcanic plains, adding another layer to the planet's complex history. And then there are the features that reveal something even more unusual, structures known as lobate scarps, long, cliff-like formations that stretch across the surface, formed as the planet cooled and contracted over time, shrinking slightly as its interior lost heat, causing the crust to compress and wrinkle, almost like the skin of a drying fruit. And these scarps are evidence that Mercury is not completely static, that it has changed over time and may still be changing, even today. Because despite its small size and seemingly inactive state, Mercury may still be cooling, still contracting, still evolving, albeit very slowly over timescales that are difficult for us to observe directly, but can be inferred through careful study of its surface features, giving us insight into how planets change long after their formation. And perhaps what makes Mercury's surface so fascinating is that it is not just a landscape, but a record, a preserved history of the solar system's early days, a snapshot of a time when planets were still forming, still colliding, still shaping one another through violent interactions. And by studying this surface, we are effectively looking back in time, uncovering clues about how our solar system came to be. Because Mercury, in its silence and stillness, has preserved something that most other planets have lost, a memory of the beginning. There is something about Mercury that seems almost contradictory, something that challenges everything we think we know about temperature, sunlight, and the basic conditions required for ice to exist, because this is a planet that orbits closer to the Sun than any other, a world where the surface can become hot enough to melt metal, a place defined by extreme heat and intense radiation. And yet, hidden in its darkest regions, there exists something completely unexpected: water ice. At first, this discovery sounds impossible, because how could ice survive on a planet so close to the Sun? How could something so delicate remain stable in an environment that is otherwise so extreme? But the answer lies in one of Mercury's most unusual characteristics, something that is easy to overlook but has profound consequences. Mercury's axis is almost perfectly upright. Unlike Earth, which is tilted and experiences seasons, Mercury has almost no axial tilt at all, meaning that at its poles, the Sun never rises high above the horizon, and in certain deep craters near the poles, sunlight never reaches the bottom at all, creating regions of permanent shadow, places where the Sun has not shone for billions of years. These shadowed craters are among the coldest places in the entire solar system. Temperatures inside them can drop below -170 degrees Celsius, cold enough for water ice to remain stable indefinitely, protected from the intense heat that dominates the rest of the planet, creating pockets of frozen material in a world that is otherwise defined by extreme heat. But this discovery raises another question: where did the water come from? Because Mercury itself is not expected to have formed with large amounts of water, especially so close to the Sun, where volatile materials would have been less likely to condense. And this has led scientists to propose that the ice may have been delivered by comets or water-rich asteroids, objects that collided with Mercury over billions of years, depositing ice into these permanently shadowed regions, where it could remain preserved. And this idea connects Mercury to a much larger story, because it suggests that water, one of the most important substances for life as we know it, is not confined to a single region of the solar system, but can be transported across vast distances, delivered to planets through impacts, stored in unexpected places, and preserved under conditions that allow it to survive even in the most extreme environments. But the ice on Mercury is not just a scientific curiosity. It is also a reminder that even the most hostile worlds can contain hidden environments where conditions are very different from what we might expect. Regions where temperature, light, and chemistry create pockets of stability in an otherwise unstable world. And this idea has implications not just for Mercury, but for other planets and moons throughout the solar system, where similar shadowed regions may exist. And when we think about this, Mercury begins to feel less like a simple, lifeless rock and more like a complex system, a planet with layers of reality, where extreme heat exists alongside extreme cold, where sunlight dominates most of the surface but never reaches certain regions, and where something as fragile as ice can survive for billions of years in complete darkness. Because Mercury is a world of contrasts, a planet of fire and ice. And it is only beginning to reveal how much more there is beneath the surface. At first glance, Mercury appears to be a completely inactive world, a small, airless planet that has long since cooled, a place where geological activity has faded into the past, leaving behind only craters and ancient scars. And based on its size alone, this is exactly what we would expect, because small planets lose their internal heat much faster than larger ones. And over time, this loss of heat should cause their interiors to solidify, shutting down the processes that drive magnetic fields and geological activity. But Mercury does not follow this expectation, because despite its small size, despite its age, and despite its proximity to the Sun, Mercury still has a magnetic field. And that should not be possible. Because in order for a planet to generate a magnetic field, it must have a partially molten, electrically conductive core, one that is still moving, still circulating, still active, creating a dynamo effect that produces the magnetic field. And for a planet as small as Mercury, maintaining such a molten core over billions of years is something that scientists did not expect to see. And yet, measurements from spacecraft like Messenger have confirmed that Mercury does indeed have a global magnetic field, weaker than Earth's, but clearly present, clearly active, and clearly telling us that something is still happening deep inside the planet, something that has allowed it to retain heat far longer than we would have predicted. This raises a fundamental question. How? How does a small planet like Mercury keep its core partially molten for so long, when other planets of similar size like Mars have largely lost their magnetic fields and cooled internally? One possible explanation lies in the composition of Mercury's core, which is believed to contain not only iron, but also lighter elements such as sulfur, which can lower the melting point of the material, allowing parts of the core to remain liquid even at lower temperatures, effectively extending the lifetime of its internal activity, keeping the dynamo process alive for much longer than it otherwise would be. But there is also another factor to consider: Mercury's proximity to the Sun. Because being so close to such a massive object means that Mercury experiences strong gravitational interactions, tidal forces that can generate internal heating, similar in concept to what we see on some moons of Jupiter and Saturn, where gravitational stretching and compression create heat within the interior. And while this effect is much smaller on Mercury, it may still contribute to maintaining some level of internal activity over long timescales. And then there is something even more subtle. Mercury's magnetic field is not perfectly centered. It is slightly offset toward the north, creating an uneven magnetic environment around the planet, something that we do not fully understand, and something that suggests that the internal processes generating the field may be more complex than a simple, uniform dynamo, indicating that Mercury's interior may be structured in ways that are different from other terrestrial planets. But the presence of a magnetic field does more than just tell us about the planet's interior. It also affects how Mercury interacts with the space environment around it, because the magnetic field creates a small magnetosphere, a region where charged particles from the sun are deflected or guided, shaping how solar wind interacts with the planet, creating dynamic processes that can strip atoms from its surface and contribute to its thin exosphere. So Mercury is not just a passive object orbiting the sun. It is an active participant in a complex system of interactions, where its internal structure, its magnetic field, and its environment all influence one another, creating a planet that is far more dynamic than it appears from a distance. Because Mercury should be a dead world, but it is. And that means there is still something about it that we don't fully understand. If you could stand on Mercury and look out across its surface, what you would experience would not feel like standing on a planet in the way we understand it on Earth, because there is no real sky, no atmosphere to scatter light, no air to breathe. And yet, Mercury is not completely surrounded by nothing, because it does have something so thin and so fragile that it barely qualifies as an atmosphere at all, something known as an exosphere. Unlike Earth's atmosphere, which is dense and stable, Mercury's exosphere is constantly forming and disappearing at the same time, a delicate cloud of atoms that are not held tightly to the planet, but instead move freely, drifting, escaping, and being replenished in a continuous cycle that is driven by the harsh conditions of space and the intense energy of the sun. This exosphere is made up of elements like sodium, potassium, oxygen, and helium, atoms that are constantly being knocked off the surface of Mercury by solar radiation, micrometeorite impacts, and the relentless bombardment of charged particles from the sun, a process known as sputtering, where high-energy particles strike the surface and eject atoms into space, creating a temporary, ever-changing envelope around the planet. But because Mercury's gravity is relatively weak and its atmosphere is so thin, many of these atoms do not stay for long, instead escaping into space, drifting away from the planet, forming a faint tail that stretches behind Mercury, almost like a comet, a feature that is invisible to the naked eye but has been detected by sensitive instruments, revealing that Mercury is not just losing material, but actively interacting with its environment in a way that is both subtle and continuous. And this creates a strange situation where Mercury is slowly being eroded, atom by atom over billions of years, its surface constantly exposed, constantly altered, constantly losing tiny pieces of itself to the surrounding space, a process so slow that it is almost impossible to notice on human timescales. But over the lifetime of the solar system, it becomes significant, a reminder that planets are not permanent, that they change, that they evolve, and that they can even lose parts of themselves over time. But what makes this process even more fascinating is how it connects Mercury to the Sun. Because the solar wind, a stream of charged particles flowing outward from the Sun, plays a major role in shaping Mercury's exosphere, interacting with its magnetic field, guiding particles toward the surface, and driving the processes that release atoms into space, creating a direct link between the star and the planet, a constant exchange of energy and material that defines Mercury's environment. And in this sense, Mercury is not just orbiting the Sun, it is being shaped by it, continuously, relentlessly. A planet that exists at the edge of survival, exposed to forces that are slowly wearing it down, gradually changing it, and connecting it to the larger system in ways that are both invisible and profound. Because when we think of planets, we often imagine them as stable, unchanging worlds. But Mercury reminds us that this is not always the case, that even a solid, rocky planet can be part of a dynamic system where matter is constantly being exchanged, where surfaces are constantly being altered, and where the boundary between the planet and space itself becomes blurred. And as we continue to explore Mercury, we begin to see that it is not just a world of extremes, but a world of transitions, a place where matter moves between states, where energy flows continuously, and where the line between what belongs to the planet and what belongs to space becomes increasingly difficult to define. When we look at Mercury, it is easy to think of it as something permanent, a small but stable planet that has existed for billions of years and will continue to orbit the Sun in the same way far into the future, repeating its path over and over again in a predictable cycle. But when scientists study its motion over extremely long timescales, something unexpected begins to appear, because Mercury's orbit is not as stable as it seems, and over millions and billions of years, small gravitational interactions can grow into something much larger, something that introduces uncertainty into what we once believed was a perfectly ordered system. Because Mercury is constantly being influenced not only by the Sun, but also by the gravitational pull of other planets, particularly Jupiter, which, despite being far away, has enough mass to subtly affect Mercury's orbit over time. And these effects, although incredibly small in the short term, can accumulate, creating a system where tiny changes can lead to significant differences over long periods, a phenomenon known as chaos in dynamical systems. This means that while Mercury's orbit can be predicted very accurately over thousands or even millions of years, beyond a certain point, the uncertainty grows, and the exact path becomes less certain, not because we lack understanding, but because the system itself becomes inherently unpredictable, sensitive to even the smallest variations, making it impossible to determine exactly what will happen far into the future. And when scientists run simulations of the solar system over billions of years, they find that there is a small but real possibility that Mercury's orbit could become unstable, that its path could change in such a way that it might eventually collide with another planet, such as Venus or even Earth, or be thrown into the Sun, or even ejected from the solar system entirely. Scenarios that sound dramatic, almost unbelievable, but are grounded in the mathematics of orbital dynamics. These events are extremely unlikely on human timescales, and the probability remains low. But the fact that they are possible at all changes how we think about the solar system, because it shows us that even a system that appears stable and predictable is actually dynamic and evolving, shaped by interactions that can lead to very different outcomes over long periods of time. And this idea extends beyond Mercury, because it suggests that planetary systems in general are not fixed, but constantly changing, constantly adjusting, constantly influenced by the gravitational interplay between their components. And this has implications not only for our own solar system, but for planetary systems throughout the galaxy, where similar processes may be shaping the orbits of planets in ways that we are only beginning to understand. But Mercury, being the closest planet to the Sun and one of the most dynamically sensitive, becomes a kind of focal point for these studies, a planet where the effects of gravitational interactions, relativistic corrections, and long-term instability all come together, making it one of the most interesting objects for understanding how planetary systems behave over time. So when we look at Mercury, we are not just looking at a snapshot of the present, we are looking at a system in motion, a system that has evolved over billions of years and will continue to evolve long into the future. A system where the outcome is not entirely fixed, where multiple possibilities exist, and where even something as seemingly simple as a planet's orbit can hold within it the potential for dramatic change. Because Mercury is not just a planet that exists, it is a planet that is still becoming. There is something deeply unsettling about Mercury, something that goes beyond its surface, beyond its temperature, beyond even its strange orbit, because this is a planet where the concept of time itself begins to shift, not in a way that you could easily notice with your senses, but in a way that is real, measurable, and deeply connected to the fundamental structure of the universe. Because Mercury exists so close to the Sun that it sits within a region where gravity is not just a force, but a distortion of spacetime itself. According to Einstein's theory of general relativity, time does not pass at the same rate everywhere. Instead, it is influenced by gravity, meaning that the stronger the gravitational field, the slower time moves relative to regions where gravity is weaker. And because Mercury is much closer to the Sun than Earth, it experiences a stronger gravitational field, which means that time on Mercury actually passes slightly more slowly than it does on Earth. This effect is incredibly small, far too small for a human to notice in everyday experience, but it is measurable with precise instruments, and it has been confirmed through observations and experiments, showing that even something as fundamental as time is not absolute, but depends on where you are in the universe, how fast you are moving, and how strong the gravitational field is around you. And Mercury provides one of the best natural environments in the solar system to observe these effects, because its proximity to the Sun amplifies the curvature of spacetime, making the deviations from classical physics more noticeable, more measurable, and more important for understanding how the universe actually behaves, turning this small planet into a kind of natural laboratory for testing the limits of our theories. But time dilation is not the only relativistic effect that Mercury reveals, because its orbit itself is influenced by the curvature of spacetime, as we discussed earlier, with its precession providing one of the first confirmations of general relativity. And together, these effects show us that Mercury is not just moving through space, but through a dynamic structure where space and time are intertwined, where gravity shapes the path of objects not by pulling them in a traditional sense, but by altering the geometry through which they move. And when we think about this, Mercury begins to feel less like a simple planet and more like a gateway to deeper understanding, a place where the everyday rules we are used to begin to bend, where time is not constant, where motion is influenced by geometry, and where the universe reveals itself in subtle but profound ways. Because if time can change, even slightly, depending on where you are, then the idea of a universal clock, a single timeline that applies everywhere, begins to break down, replaced by a more complex picture where each location in the universe has its own experience of time, its own rate, its own perspective. And Mercury, in its quiet orbit around the Sun, is one of the places where we can begin to see this difference. And this realization connects Mercury to something much larger, because the same principles that affect time near the Sun also apply near black holes, near neutron stars, near any region of strong gravity, meaning that by studying Mercury, we are not just learning about a single planet, but about the behavior of the universe itself, about how space and time interact, and about how the fundamental laws of physics operate under different conditions. So Mercury is not just a world of rock and metal. It is a world where time itself is different. A world that quietly reminds us that reality is more flexible, more complex, and more fascinating than we often imagine. Deep beneath the surface of Mercury, far below the craters and the ancient plains, lies one of the most puzzling features in the entire solar system, a core so large, so dominant, and so unexpectedly active that it challenges our basic understanding of how planets evolve over time. Because by all conventional models, a planet as small as Mercury should have lost most of its internal heat billions of years ago, its interior solidifying into a quiet, inactive mass. But that is not what we observe. Instead, Mercury's core remains at least partially molten, still capable of generating motion, still capable of sustaining a magnetic field. And this suggests that something inside the planet is allowing it to retain heat far longer than expected, something that slows down the cooling process and keeps the interior dynamic, even after billions of years of exposure to space. One explanation lies in the composition of the core itself, because unlike Earth, whose core is primarily iron and nickel, Mercury's core is believed to contain significant amounts of lighter elements, such as sulfur, which lowers the melting point of the material, allowing it to remain liquid under conditions where a pure iron core would have already solidified, effectively extending the lifespan of Mercury's internal activity and delaying the transition to a fully solid state. But composition alone may not be enough to explain everything, because Mercury's core is not just large, it is proportionally enormous, taking up most of the planet's interior, which changes how heat is distributed and retained, creating a situation where the thermal evolution of the planet is very different from that of other rocky worlds, leading to behaviors that we are still trying to model and understand. And then there is the boundary between the core and the mantle, a region where complex interactions may be taking place, where heat is transferred, where materials mix, and where the dynamics of the interior are shaped by processes that are difficult to observe directly, but can be inferred through measurements of the planet's magnetic field, its rotation, and its response to gravitational forces. Because Mercury is not a perfectly rigid body, it responds to the gravitational pull of the Sun in subtle ways, slightly deforming under tidal forces, and by measuring these deformations, scientists can gain insight into the internal structure of the planet, determining how much of it is solid and how much remains liquid, revealing a world that is still, in some sense, alive beneath its surface. And this leads to a deeper realization, because Mercury is not just a relic of the past, it is a planet that continues to evolve, albeit very slowly, with processes that operate on timescales far beyond human experience. A world where change is measured not in years or centuries, but in millions and billions of years. And yet, those changes are still happening, still shaping the planet in ways that we are only beginning to detect. But perhaps the most intriguing aspect of Mercury's core is not just that it is molten, but that it is still generating motion, still circulating, still creating a magnetic field that extends into space, interacting with the solar wind, shaping the planet's environment, and connecting the deep interior to the space around it in a continuous cycle of energy and motion. So when we think about Mercury, we should not think of it as a dead world, but as a planet that exists in a slow state of change, a world where the past and the present are intertwined, where ancient processes continue to influence current conditions, and where the interior remains active in ways that challenge our expectations. Because Mercury, despite its size, despite its age, and despite its harsh environment, is still holding onto its heat, still maintaining its internal dynamics, and still reminding us that even the smallest planets can defy our assumptions. For most of human history, Mercury was little more than a moving point of light in the sky, a small, fast object that appeared briefly near the horizon just before sunrise or after sunset, never rising high, never staying visible for long, always hiding in the overwhelming brightness of the sun, making it one of the most difficult planets to observe and one of the least understood for centuries, not because it was unimportant, but because it was simply too hard to study with the tools we had. And even when telescopes improved, Mercury remained elusive, because observing something so close to the sun is inherently dangerous and technically challenging, requiring precise timing, careful positioning, and often limiting observations to short windows when the planet could be seen safely, which meant that for a long time, our understanding of Mercury was based on incomplete data, fragmented observations, and assumptions that could not be fully tested. It wasn't until the space age that we finally began to uncover the true nature of Mercury, when humanity developed the capability to send spacecraft beyond Earth and explore other worlds directly. And yet, even then, Mercury remained one of the most difficult destinations to reach, not because of its distance, but because of its proximity to the Sun. Because reaching Mercury is not simply a matter of traveling inward, it requires losing a significant amount of orbital energy, slowing down enough to fall toward the Sun while also avoiding being pulled too quickly, a process that is far more complex than traveling outward to planets like Mars or Jupiter. And this is why missions to Mercury are rare, requiring careful planning, multiple gravity assists, and long travel times to achieve the necessary trajectory. The first spacecraft to visit Mercury was Mariner 10, launched by NASA in the 1970s, a mission that used gravity assists from Venus to reach Mercury, becoming the first human-made object to fly past the planet, capturing images of its surface, and providing the first close-up view of this mysterious world, revealing a landscape covered in craters and confirming some of the early assumptions about its appearance, but also raising new questions about its structure and composition. However, Mariner 10 could only map about half of the planet's surface, leaving the other half completely unknown, a reminder that even after our first visit, Mercury was still holding back part of its story, still partially hidden, still not fully explored. It would take decades before we returned, when NASA launched the Messenger mission, a spacecraft specifically designed to orbit Mercury and study it in detail. And after a long and complex journey involving multiple flybys of Earth, Venus, and Mercury itself, Messenger finally entered orbit around the planet in 2011, becoming the first spacecraft to do so and opening a new chapter in our understanding of Mercury. Messenger provided detailed maps of the entire surface, measured the planet's composition, studied its magnetic field, and confirmed the presence of water ice in permanently shadowed craters, transforming our understanding of Mercury from a simple, cratered world into a complex and dynamic system with a rich history and ongoing processes that we had not fully anticipated. And yet, even with all this data, Mercury remains a challenging place to study, because the conditions are so extreme that spacecraft must be carefully designed to withstand intense heat and radiation, using sunshields, specialized orbits, and precise thermal control systems to survive long enough to collect meaningful data. And even then, missions are limited in duration, constrained by the harsh environment that surrounds the planet. Today, the exploration of Mercury continues with the BP Colombo mission, a joint effort between the European Space Agency and the Japan Aerospace Exploration Agency, currently on its way to Mercury, carrying advanced instruments that will provide even more detailed measurements of the planet's surface, interior, and environment, offering the potential to answer questions that have remained unresolved and to uncover new mysteries that we have not yet imagined. Because despite everything we have learned, Mercury is still not fully understood, still not completely mapped in terms of its internal processes, still holding onto secrets that can only be revealed through continued exploration, reminding us that even the closest planet to the Sun can remain one of the most difficult to reach and one of the most challenging to study. And as we think about this, we begin to realize that exploration is not just about distance. It is about complexity, about the challenges that arise from the environment, the physics, and the conditions of each world, and Mercury, in all its intensity, represents one of the greatest challenges we have faced in our efforts to explore the solar system. When we look at Mercury today, it is easy to focus on what it is now, a small, dense, and extreme world orbiting close to the Sun. But in reality, Mercury is also something much older, something far more significant, because it is one of the best preserved records of the early solar system, a planet that has remained largely unchanged on its surface for billions of years, carrying within it a history that reaches back to the very beginning of planetary formation. Because in the early days of the solar system, everything was very different. The Sun had just formed, surrounded by a rotating disk of gas and dust, a chaotic environment where particles collided, merged, and gradually grew into larger bodies, forming the first planetesimals and eventually the planets themselves, a process that was far from smooth, far from orderly, and filled with violent interactions that shaped the structure of the system we see today. And Mercury, being so close to the Sun, formed in one of the most extreme regions of this early disk, where temperatures were higher, where materials behaved differently, and where only certain elements could condense and accumulate, leading to a planet that was fundamentally different from those forming farther out. A world that was shaped from the very beginning by conditions that were more intense than almost anywhere else in the solar system. But what makes Mercury so valuable as a record of this time is the fact that its surface has not been significantly altered by processes like erosion, weathering, or plate tectonics, meaning that the impact craters and geological features we see today are essentially frozen in time, preserving a snapshot of the early solar system that has been lost on other planets, including Earth, where active processes have erased most of the evidence of that ancient past. Because when we study the distribution and size of craters on Mercury, we are not just looking at random features, we are looking at a timeline, a record of how often impacts occurred, how intense they were, and how they changed over time, providing insights into a period known as the Late Heavy Bombardment, a time when the inner solar system experienced a high frequency of collisions, shaping the surfaces of the terrestrial planets in ways that are still visible today. And by comparing Mercury's surface to that of the Moon, Mars, and other bodies, scientists can piece together a broader picture of how the solar system evolved, how materials were distributed, how planets grew, and how they were shaped by the interactions that took place in those early stages, making Mercury not just a planet, but a key piece of evidence in understanding the history of our entire cosmic neighborhood. But Mercury's role goes even deeper, because its composition, its density, and its unusual structure provide clues about the processes that determine how planets differentiate, how heavy elements sink to form cores while lighter materials form mantles and crusts, and how these processes can vary depending on location, temperature, and the history of collisions, offering insights that extend beyond our solar system to the study of exoplanets and planetary systems around other stars. So when we study Mercury, we are not just studying a single world, we are studying the remnants of a much larger story, a story that began billions of years ago and continues to influence the structure of the solar system today. A story that connects the smallest details of a planet's surface to the largest questions about how planetary systems form and evolve. And in this sense, Mercury becomes something more than just the first planet from the Sun. It becomes a window into the past, a world that allows us to look back in time and understand the processes that created not only Mercury itself, but the entire system of planets that surround our star. Imagine for a moment that you could stand on the surface of Mercury, not as a human constrained by biology and survival, but as an observer able to experience the environment without being destroyed by it, because what you would see, what you would feel, would be unlike anything on Earth, a world that is both silent and overwhelming, simple in appearance yet extreme in every possible way. The first thing you would notice is the stillness. There is no wind, no sound, no movement in the air, because there is no air. The surface stretches out in every direction, covered in craters and rocky plains, illuminated by a sun that appears enormous in the sky, more than twice the size it appears from Earth. A blinding disk of light that dominates the horizon, casting sharp, dark shadows that never soften, because there is no atmosphere to scatter the light. And the sky above you would remain completely black, even at noon, filled with stars that are normally hidden during the day on Earth, creating a strange contrast where the brightness of the sun exists alongside the darkness of space, a reminder that Mercury exists at the boundary between a planet and the vacuum of space, exposed to the universe in a way that no other terrestrial planet is. But what makes this experience even more unusual is how slowly everything changes, because on Mercury, time feels stretched, extended, as if the planet itself is moving in slow motion, with days that last for months, where the sun rises gradually, moves across the sky, pauses, reverses direction, and then continues again, creating a motion that feels almost unnatural, almost as if the sky itself is behaving incorrectly. And as the sun climbs higher, the heat begins to build, not gradually as on Earth, but intensely directly, because there is nothing to filter or distribute the energy, causing the surface to heat up to extreme temperatures, turning the ground into a place that would be completely inhospitable, while just beyond the edge of the sunlight, in the shadows, the temperature remains incredibly cold, creating a sharp boundary between heat and cold that exists side by side. And if you were to move toward one of the poles, into the deep craters where sunlight never reaches, you would find something even more surprising, a region of permanent darkness, where the temperature remains low enough for ice to exist, a hidden world within a world, where the extremes of Mercury create pockets of stability that seem almost impossible given the planet's proximity to the sun. But perhaps the most profound part of standing on Mercury would not be the heat, the cold, or even the view, but the sense of isolation, because Mercury feels distant, not just in space, but in experience, a world that is so different from Earth that it challenges our intuition about what a planet should be. A place where the familiar concepts of sky, day, and environment are replaced by something far more extreme and far less forgiving. And yet, despite all of this, Mercury is still governed by the same physical laws that apply everywhere else, still part of the same system, still orbiting the same sun, reminding us that even the most extreme environments are connected to the same underlying principles, the same forces, and the same processes that shape the entire universe. So standing on Mercury, is not just about experiencing another world. It is about experiencing the limits of what a world can be. When we compare Mercury to the other planets in our solar system, it is easy to place it at the bottom of the list, to see it as small, simple, and unremarkable, especially when compared to the massive gas giants or the more visually dynamic worlds like Earth or Mars. But this perspective misses something important, because Mercury is not just different, it is fundamentally unique, a planet that does not quite fit into the categories we use to describe other worlds. Because Mercury is not just a rocky planet like Earth or Mars, it is a metal-rich world dominated by its core, a planet where the ratio between metal and rock is unlike anything else in the solar system, suggesting a formation history that was shaped by processes that did not affect other planets in the same way, making it an outlier, a case that challenges our assumptions about how planets form and evolve. And when we compare Mercury to the Moon, we see similarities in appearance, both heavily cratered, both lacking atmospheres, both preserving ancient surfaces, but the similarities end there, because Mercury is far more massive, far more dense, and far more complex internally, with a magnetic field and a partially molten core, features that the Moon does not possess, highlighting how two worlds can look similar on the surface while being completely different beneath it. Compared to Mars, Mercury appears even more extreme, because while Mars has an atmosphere, seasons, and evidence of past water, Mercury exists in a much harsher environment, with no atmosphere to speak of and conditions that are far less stable, showing us how distance from the Sun and planetary size can lead to dramatically different outcomes, even among rocky planets. And when we compare Mercury to Venus and Earth, the contrast becomes even more striking, because while those planets have thick atmospheres that regulate temperature and create complex weather systems, Mercury is completely exposed, lacking any protective layer, making it a world where external forces, like solar radiation and micrometeorite impacts, have a direct and immediate effect on the surface. But perhaps what makes Mercury most misunderstood is the assumption that small means simple, because Mercury demonstrates that this is not true, that even a small planet can have a complex history, a dynamic interior, and interactions with its environment that are both subtle and profound, reminding us that size alone does not determine complexity. And in many ways, Mercury represents an extreme version of processes that occur throughout the solar system, a planet where the effects of heat, gravity, and radiation are amplified, making it easier to study certain phenomena, easier to observe certain interactions, and easier to test our understanding of planetary science in conditions that push those processes to their limits. So Mercury is not just the first planet from the Sun. It is a planet that challenges categories, a planet that exists between definitions, a world that reminds us that the diversity of planetary systems is far greater than we often assume. And as we move forward, continuing our journey, Mercury leaves us with an important realization. The closer we look, the more we understand that even the smallest world can hold the biggest surprises. There is something almost unsettling about Mercury when you begin to step back and look at it not just as a planet, but as a concept, as an idea of what a world becomes when it is pushed to the very limits of what is physically possible. Because Mercury exists in a place where survival itself seems uncertain, where the forces acting upon it are so intense, so relentless, that it feels less like a stable world and more like something that is constantly being tested, constantly being shaped, constantly being worn down by the environment around it. Because Mercury lives closer to the Sun than any other planet, and that proximity is not just a detail, it is the defining characteristic of everything the planet is, everything it has been, and everything it will become, a position that exposes it to extreme radiation, powerful gravitational forces, and a constant stream of energetic particles that interact with its surface in ways that slowly, almost imperceptibly, change it over time. And when we think about this, Mercury begins to feel less like a permanent object and more like something temporary, something that exists in a delicate balance, a world that has managed to survive for billions of years, but not without being altered, not without losing material, not without being shaped by forces that are still acting on it today. Because unlike Earth, which has systems that protect and stabilize it, an atmosphere that shields it from radiation, a magnetic field that deflects charged particles, and geological processes that recycle its surface, Mercury lacks most of these protections, leaving it exposed, vulnerable, and directly connected to the environment of space, where there is no buffer, no protection, and no delay between cause and effect. And yet, despite this exposure, Mercury continues to exist, continues to orbit the Sun, continues to maintain its structure, suggesting that even under the most extreme conditions, stability is possible, that a planet can endure even when it is constantly being pushed toward its limits. A reminder that the universe is capable of sustaining objects in environments that seem almost impossible. But there is also something deeper here, something that goes beyond the physical description of the planet, because Mercury represents a kind of boundary, a point where the familiar begins to fade and the extreme begins to take over, a place where the conditions that define most planets are no longer present, replaced by something more fundamental, more raw, more directly connected to the forces that shape the universe. Because on Mercury, there is no atmosphere to soften the experience, no water to reshape the surface, no life to interact with the environment, only rock, metal, and the direct influence of the Sun, creating a world that feels stripped down to its most basic components, a planet that exists in a state that is closer to the underlying physics of the solar system than the more complex environments of other worlds. And in this sense, Mercury becomes something more than just a planet. It becomes a kind of reference point, a world that shows us what happens when a planet exists without the layers of complexity that we often associate with habitability, a place where the fundamental forces of gravity, radiation, and motion are more visible, more direct, and more dominant. So Mercury is not just extreme, it is elemental, a world that exists at the edge of survival, where the balance between existence and destruction is constantly being maintained, and where the forces that shape the universe are felt more strongly than almost anywhere else in the solar system. And as we continue to explore it, we begin to understand that Mercury is not just a place, it is a limit. For all that we have learned about Mercury, for all the missions, measurements, and models that have brought us closer to understanding this small and extreme world, there is still something incomplete about the picture, something unresolved, something that reminds us that Mercury is not a solved problem, but an open question, a planet that continues to challenge our understanding in ways that are both subtle and profound. Because even now, there are aspects of Mercury that we cannot fully explain, details that do not quite fit into our current models, observations that raise more questions than they answer. And this is what makes Mercury so fascinating, because it is not just a planet that we study. It is a planet that pushes back, that resists simple explanations, that forces us to reconsider what we think we know. One of the biggest unanswered questions is still its origin, because while we have theories about massive impacts and high-temperature formation, we do not yet have definitive evidence that confirms one scenario over the other, leaving Mercury's early history uncertain, a story that we can only reconstruct indirectly, using clues that are incomplete and sometimes ambiguous. And then there is the question of its magnetic field, because while we know that Mercury has one, we do not fully understand how it is generated in detail, why it is offset from the center, and how its internal dynamics sustain it over such long timescales, raising questions about the structure of its core and the processes that are taking place deep beneath the surface. There are also mysteries related to its surface composition, because measurements have revealed unexpected abundances of certain elements, including volatile compounds that should not be present in large quantities so close to the Sun, suggesting that either our understanding of planetary formation is incomplete, or that Mercury has experienced processes that have altered its composition in ways we do not yet fully understand. And even its exosphere, the thin cloud of atoms surrounding the planet, is not fully understood, because while we know how it is formed in general terms, the detailed processes that control its variability, its composition, and its interaction with the solar wind are still being studied, revealing a system that is more complex than it first appears. But perhaps the most intriguing aspect of Mercury is not any single mystery, but the fact that all of these questions are connected, that the planet's structure, composition, magnetic field, and environment are all part of a larger system, a system that we are still trying to piece together, where each answer leads to new questions, and where the deeper we look, the more complex the picture becomes. Because Mercury is not just a planet that we have yet to fully understand. It is a reminder that understanding itself is a process that is never complete, a process that evolves as we gather more data, develop better models, and refine our theories, constantly pushing the boundaries of what we know and what we can explain. And this is why Mercury remains important, because it represents the frontier of our knowledge, a place where science is still actively unfolding, where discoveries are still being made, and where the answers we are looking for may require us to think differently, to question assumptions, and to explore new ideas. So as we continue this journey, Mercury leaves us not with certainty, but with curiosity, not with final answers, but with open questions, reminding us that even the closest planet to the Sun can still hold mysteries that we have yet to solve. Even after everything we have uncovered about Mercury, The most exciting part may still lie ahead, because the planet is far from fully explored, and with new technology, new missions, and new scientific questions, we are entering a phase where Mercury could reveal details that were previously impossible to detect, opening the door to discoveries that could reshape our understanding not only of this planet, but of planetary science as a whole. Because the next chapter of Mercury exploration is already underway, with missions like BP Colombo, a collaboration between Europe and Japan, designed to study the planet in greater detail than ever before, carrying advanced instruments that will analyze its magnetic field, its internal structure, its surface composition, and its interaction with the solar wind, providing data that is far more precise and far more comprehensive than anything we have collected so far. And what makes this mission particularly important is that it is not just a continuation of previous studies, but an expansion, a deeper investigation into the processes that define Mercury, aiming to answer questions that have remained unresolved for decades, such as the exact composition of its core, the mechanisms behind its magnetic field, and the origin of its unusual surface features. But beyond the specific goals of this mission, there is a broader shift taking place, because our ability to study planets is becoming more advanced, more detailed, and more interconnected, allowing us to combine data from multiple sources, to compare Mercury with other planets in new ways, and to develop models that can explain not just individual features, but entire systems, providing a more complete understanding of how planets form, evolve, and interact with their environments. And this is where Mercury becomes especially important, because it represents an extreme case, a planet where the effects of proximity to a star, high temperatures, and strong gravitational forces are amplified, making it an ideal subject for testing our theories under conditions that are more intense than those found on other terrestrial planets. Because if we can understand Mercury, we can better understand planets that exist close to their stars in other systems, worlds that are being discovered in large numbers around distant stars, many of which may resemble Mercury more than they resemble Earth, meaning that the insights we gain from studying this small planet could have implications far beyond our own solar system. But perhaps the most exciting aspect of future exploration is not just the answers we expect to find, but the questions we have not yet thought to ask, because every time we explore a new world in greater detail, we discover things that we did not anticipate, features that do not fit our models, and phenomena that require new explanations, reminding us that exploration is not just about confirming what we know, but about discovering what we don't. So Mercury stands at the edge of discovery, a planet that has already challenged our understanding in many ways, and that may continue to do so as we gather more data, refine our theories, and push the limits of what we can observe and measure. Because the story of Mercury is not finished, it is still being written, and the next chapters may change everything we think we know. When we think about the solar system as a whole, our attention is often drawn outward toward the larger planets, the more visually striking worlds, the ones with rings, storms, and moons, but Mercury sits quietly at the very beginning of it all, close to the sun, small, easily overlooked, and yet in many ways it represents the starting point of the entire system, the inner boundary where the influence of the sun is strongest and where the conditions are most extreme. Because Mercury exists closer to the sun than any other planet, it experiences the solar system in its most direct form, without the layers of complexity that we see elsewhere, without thick atmospheres, without oceans, without the processes that soften and reshape planetary environments, leaving behind a world that feels almost raw, almost untouched by anything other than the fundamental forces that govern motion, heat, and gravity. And in this sense, Mercury becomes something more than just a planet. It becomes a reference point, a place where we can see the solar system in its simplest and most exposed state, a world that allows us to strip away the details and focus on the underlying structure, the basic interactions that define how everything moves, how everything evolves, and how everything is connected. Because when we look at Mercury, we are looking at a planet that has endured billions of years of exposure to the sun, a world that has been shaped by heat, by impacts, by radiation, and by time itself. And yet, despite all of this, it remains, still orbiting, still existing, still part of the system. A reminder that even in the most extreme environments, stability can persist. But there is also something humbling about Mercury, something that forces us to reconsider our perspective. Because when we compare it to Earth, we see just how different our own planet is, how much of what we experience depends on a delicate balance of conditions that Mercury does not have. And this contrast highlights just how unique Earth is, not just in its ability to support life, but in the complexity of its systems and the stability of its environment. And yet Mercury is no less important, because it shows us what a planet looks like without those layers, without protection, without moderation. A world where the fundamental forces are fully exposed, where the environment is defined by extremes, and where the passage of time is recorded in a way that is far more direct, far more visible, and far more permanent than on more active planets. So Mercury, in its silence, in its stillness, in its simplicity, becomes something profound, a reminder that the solar system is not just a collection of worlds, but a spectrum of possibilities, a range of environments shaped by distance, composition, and history, each one offering a different perspective on what a planet can be. And as we prepare to leave Mercury behind, to move outward to the next planet, we carry with us everything it has shown us, the extremes, the mysteries, the questions, and the insights, all of which contribute to a deeper understanding of the system we are part of. Because Mercury may be the smallest of the planets, but it is also the beginning. As we reach the end of our journey across Mercury, what remains is not just an image of a small, cratered world orbiting close to the sun, but something far more complex, far more meaningful, because Mercury is not simply the first planet in the solar system. It is a world that exists at the very edge of the sun's influence, a place where the forces that shape the entire system are felt in their most direct and most extreme form. Because everything about Mercury is defined by its proximity to the sun, from its extreme temperatures to its unusual rotation, from its thin exosphere to its dynamic magnetic interactions, and even to the way time itself behaves in its orbit, making it a planet that is constantly connected to the star it orbits, constantly influenced, constantly shaped. a world that cannot be understood without understanding the sun itself. And in many ways, Mercury feels less like an independent planet and more like an extension of the sun's domain, a boundary object that exists between the star and the rest of the solar system, a place where the transition from stellar influence to planetary stability begins, marking the inner edge of the system as we know it. But what makes Mercury truly remarkable is not just its environment, but what it teaches us, because through its extremes, its mysteries, and its differences, it has forced us to expand our understanding of what a planet can be, to reconsider how planets form, how they evolve, and how they interact with their surroundings, revealing that even the smallest and most overlooked worlds can hold insights that reshape our view of the universe. Because Mercury has shown us that size does not determine importance, that proximity does not guarantee simplicity, and that even in the most extreme conditions, complexity can emerge, whether in the structure of its core, the behavior of its orbit, or the interactions between its surface and the space around it. And as we step back and look at Mercury one last time, we begin to see it not just as an object, but as a story that began billions of years ago in the early solar system, shaped by collisions, by heat, by gravity, and by time, a story that continues even now as the planet slowly evolves, slowly changes, and slowly reveals its secrets. But this is not the end of the journey, because Mercury is only the first step. Beyond it lies a solar system filled with worlds that are larger, more complex, and in many ways even more mysterious, each one with its own story, its own history, and its own questions waiting to be answered. And as we leave Mercury behind, moving outward toward the next planet, we carry with us everything we have learned, every detail, every mystery, every insight, using it as a foundation for what comes next, because understanding one world brings us closer to understanding them all. So take one last look at Mercury, a planet of extremes, a world of fire and ice, a place where gravity bends time, where the sun dominates the sky, and where the surface holds the memory of the beginning. And as we move on, remember this: even the smallest planet can tell the biggest story. What if I told you that the most dangerous planet in our solar system once may have looked like home, that beneath its thick clouds and extreme heat lies the story of a world that could have been like Earth, a planet that formed in almost the same region, from almost the same materials, under almost the same conditions, and yet somehow ended up becoming one of the most hostile environments we have ever discovered? Because Venus is often called Earth's twin, similar in size, similar in mass, similar in composition. At first glance, it seems like a mirror of our own world, a second chance at something familiar, a planet that should have followed a similar path, developing oceans, an atmosphere, and perhaps even life. But it didn't. Instead, Venus became something else entirely. A planet where the surface temperature is hot enough to melt lead, where the atmosphere is so thick that it crushes anything that tries to land, and where clouds made of sulfuric acid cover the entire planet, hiding everything beneath them, creating a world that feels less like a planet and more like a warning. And what makes this even more unsettling is that we cannot see its surface directly, because Venus is completely covered in clouds, endless, dense, impenetrable. For centuries, this made Venus one of the greatest mysteries in the sky, a bright object that revealed nothing about what lay beneath, leading people to imagine oceans, jungles, or even alien civilizations hidden below its cloud cover. But when we finally found a way to look through those clouds using radar instead of visible light, what we discovered was something completely different. A surface shaped by volcanoes, vast plains of solidified lava, and a landscape that feels more like a frozen hell than a living world. Because Venus is not just hot, it is stable in its heat, everywhere, all the time. Day and night, pole to equator, the temperature barely changes, creating a planet where the concept of climate as we know it simply does not exist, replaced by a constant, overwhelming pressure and heat that never fades. And yet, despite all of this, Venus may once have had oceans, liquid water, possibly for millions or even billions of years, which means something happened, something changed. Something pushed this planet past a point of no return, turning it from a potential Earth-like world into the most extreme version of a greenhouse planet we know. And that is where the real story begins. Because Venus is not just another planet. It is a mystery, a transformation, a warning, and possibly a glimpse into what could happen to worlds like our own. If you could descend through the clouds of Venus, slowly moving from the upper layers of its atmosphere down toward the surface, what you would experience would not feel like entering a planet, but like sinking into something thick, something heavy, something almost alive, because the atmosphere of Venus is not just dense, it is overwhelming, a massive envelope of gas that surrounds the planet with a pressure so intense that it changes the way the environment behaves entirely. Because on Venus, the atmosphere is not something you move through lightly. It presses down on everything, constantly, relentlessly. At the surface, the pressure is about 90 times greater than what we experience on Earth, equivalent to being nearly 1 kilometer underwater, a force so strong that it compresses gases, alters chemical reactions, and creates conditions that are completely alien compared to anything we know. And this pressure does something else. It traps heat, extremely efficiently. Because the atmosphere of Venus is composed mostly of carbon dioxide, a powerful greenhouse gas, and with so much of it packed so tightly around the planet, heat from the sun enters the atmosphere but cannot escape, becoming locked inside, building up over time, and creating a thermal environment that has remained stable for millions of years, turning Venus into the hottest planet in the solar system, even hotter than Mercury, despite being farther away from the sun. But the deeper you go, the stranger it becomes, because as you descend, the temperature rises, the pressure increases, and the light begins to fade. The clouds above are thick, reflecting most of the sunlight back into space, meaning that by the time you reach the surface, the world is not bright and open, but dim, hazy, and almost suffocating, a place where visibility is limited and the sky appears as a dull, orange glow rather than a clear view of the sun. And within these clouds, something even more unusual exists. Layers. Distinct regions of the atmosphere, each with its own temperature, pressure, and chemical composition, creating an environment that changes dramatically with altitude, almost like different worlds stacked on top of each other, with the upper layers being relatively mild compared to the crushing conditions below. In fact, at certain altitudes, around 50 to 60 kilometers above the surface, the temperature and pressure are surprisingly similar to those on Earth, a narrow band where conditions are almost comfortable, at least in comparison, leading some scientists to consider the possibility that if life exists on Venus, it might not be on the surface at all, but floating within these clouds, surviving in a region where the environment is less extreme. But there is a problem. Those clouds are made of sulfuric acid, highly corrosive, toxic, a chemical environment that would destroy most known forms of life, making the idea both fascinating and deeply uncertain, a possibility that sits on the edge between science and speculation. And yet, the fact that such a region exists at all changes how we think about Venus, because it shows us that even on a planet as hostile as this, there are variations, layers, and environments that differ from one another, creating complexity in a place that might otherwise seem uniform and unchanging. But no matter where you are in the atmosphere, one thing remains constant: the weight, the pressure, the sense that the sky itself is not above you, but all around you, pressing down from every direction, creating a world where the environment is not something you observe, but something you feel, something you are constantly aware of, something that defines every moment of existence on the planet. Because on Venus, the sky is not something you look at. It is something you are trapped inside. Long before we understood what Venus truly was, those clouds were the greatest mystery, a smooth, bright layer that covered the entire planet, reflecting sunlight so efficiently that Venus became one of the brightest objects in the night sky, earning names like the morning star and the evening star. And for a long time, people believed those clouds might be made of water, that beneath them there could be oceans, weather, maybe even life. But the reality is far more disturbing. Because the clouds of Venus are not made of water, they are made of sulfuric acid, highly corrosive droplets suspended in a dense atmosphere, forming thick layers that stretch across the entire planet, completely hiding the surface below, creating a permanent barrier between what lies beneath and anything observing from above, turning Venus into a world that cannot be seen directly, only inferred through indirect methods like radar and spectroscopy. And these clouds are not calm. They move fast, extremely fast. Because high above the surface, winds race around the planet at speeds of up to 300 to 400 kilometers per hour, circling the entire globe in just a few days, far faster than the planet itself rotates, a phenomenon known as superrotation, where the atmosphere essentially outruns the planet beneath it, something that we still do not fully understand, a system driven by complex interactions between heat, pressure, and planetary rotation. But as you move deeper into these clouds, the environment becomes even more strange, because the droplets of sulfuric acid form layers of haze and mist, scattering what little light penetrates through, creating a dim, orange-tinted world below, where the sun is never seen clearly, only as a diffuse glow, a faint reminder of the star that dominates the system. And then there is the rain, because within these clouds, sulfuric acid can condense and fall, forming droplets that begin to descend toward the surface. But something unexpected happens, something that makes this process even more unsettling. The rain never reaches the ground. Because as the droplets fall, they enter hotter layers of the atmosphere, where the temperature is so high that the acid evaporates before it can reach the surface, turning back into vapor and rising again, creating a cycle of evaporation and condensation that traps the material within the atmosphere, a kind of endless invisible storm that never actually touches the ground. So on Venus, it rains acid, but the rain never lands. It forms, it falls, and then it disappears, over and over again. An endless loop within the clouds. And this creates a planet where the surface is completely isolated, cut off from any direct interaction with the upper atmosphere in the way we understand it on Earth, creating layers that behave almost independently, each one with its own dynamics, its own chemistry, and its own conditions. But perhaps the most unsettling part of all this is how familiar it once seemed. Because those clouds from a distance look soft, bright, harmless. And for a long time, we believed they might be. But in reality, they hide one of the most hostile environments in the solar system, a world where even the sky itself is dangerous, where the atmosphere is not just something you move through, but something that actively works against survival. Because on Venus, even the clouds are toxic. For centuries, the surface of Venus remained completely hidden, sealed beneath its thick clouds, unreachable by telescopes, invisible to the human eye, a world that existed only in imagination, where people speculated about oceans, forests, or even alien life, because without direct observation, anything seemed possible. But when we finally found a way to look beneath those clouds, everything changed. Because what we discovered was not a world of life, but a world of destruction. The first real glimpses of Venus's surface came not from human eyes, but from machines, spacecraft designed to survive, even briefly in one of the most extreme environments ever encountered, and among them were the Soviet Venera landers, missions that did something extraordinary. They landed on Venus, and what they found was something no one had ever seen before: a landscape of rock and dust, flat plains, scattered boulders, a horizon that stretched into a dim orange haze. No movement, no life, just silence. But it wasn't a peaceful silence. Because the conditions on the surface were beyond extreme, with temperatures around 460 degrees Celsius, hot enough to melt lead, and pressure so intense that it crushed anything not specifically designed to withstand it, creating an environment where survival was measured not in days but in minutes. Some of the Venera landers lasted just over an hour, others only minutes, before the heat, the pressure, the chemistry destroyed them. And yet, in that short time, they transmitted images, data, and measurements that revealed the true nature of Venus, showing us a world that is not just hostile, but fundamentally incompatible with anything we know as life. The sky, as seen from the surface, was not black like on Mercury, but a thick, glowing orange, created by the dense atmosphere scattering sunlight in a completely different way, producing a dim, almost suffocating light that never changes, never brightens, never fades, because on Venus there is no real day and night in the way we understand it. And the ground itself appeared dry, cracked, covered in rocks that had been shaped not by water or wind but by volcanic processes and chemical reactions, suggesting that the planet's history is dominated by internal heat rather than external forces, a world shaped from within rather than from above. But perhaps the most disturbing realization was this: this was not a temporary state. This was stable, permanent. The heat does not cool. The pressure does not drop. The clouds do not clear. Venus is locked in this condition, a planet that crossed a threshold and never returned. And once we saw the surface, once we understood what Venus truly was, the mystery did not disappear. It became deeper, because now the question was no longer what is Venus like, but how did it become this way? How does a planet so similar to Earth end up so completely different? If there is a single moment in the history of Venus that defines everything it is today, it is not something we can point to directly, not a specific event we observed, but a process, a chain reaction, a gradual shift that, once it began, could not be stopped, a transformation that turned a potentially Earth-like world into something entirely different. Because Venus may not have always been like this, there is growing evidence that billions of years ago, Venus could have had liquid water on its surface, oceans that existed under a much more moderate climate, a world where temperatures were lower, where the atmosphere was thinner, and where the conditions might have been, at least for a time, not entirely unlike those on early Earth. But something changed, and that change began with heat. As the sun slowly became brighter over time, Venus, being closer, absorbed more and more energy, causing its surface temperature to rise. And as the temperature increased, something critical began to happen. Water started to evaporate. At first, this may not have seemed significant because evaporation is a normal process, something that happens on Earth all the time, but on Venus it triggered something far more dangerous because water vapor is not just a gas. It is a greenhouse gas, and a very powerful one. So as more water evaporated, more heat was trapped in the atmosphere. And as more heat was trapped, more water evaporated, a feedback loop. A cycle that fed itself, growing stronger, accelerating, pushing the planet further and further away from stability. And eventually, this process reached a point where it could no longer be reversed, a tipping point where the system crossed a boundary. And once that boundary was crossed, Venus began to transform rapidly, entering what is known as a runaway greenhouse effect. At this stage, the oceans would have boiled away, completely, turning from liquid into vapor, filling the atmosphere with even more greenhouse gases, trapping even more heat, and driving temperatures higher and higher, until the surface became too hot for liquid water to exist at all. But the story does not end there. Because once water vapor rises into the upper atmosphere, it becomes exposed to intense solar radiation, particularly ultraviolet light, which breaks the water molecules apart into hydrogen and oxygen. And hydrogen, being the lightest element, does something important. It escapes, drifting into space, lost forever. And over time, this process would have stripped Venus of its water, removing it permanently, leaving behind a dry, carbon dioxide-dominated atmosphere, one that could no longer support oceans, one that could no longer cool itself, one that was locked into a state of extreme heat. And this is what makes Venus so important, because it shows us how a planet can change. Not slowly, not gently, but dramatically, irreversibly. A world that may have once had oceans, transformed into a planet where even metal melts on the surface. And when we look at Venus today, we are not just seeing what it is. We are seeing the result of what happens when a planet loses control of its climate, when feedback loops push it beyond recovery, when balance is replaced by runaway processes that reshape the entire environment. Because Venus is not just hot, it is the result of a chain reaction, a process that once started, never stopped. Once the runaway greenhouse effect began on Venus, the fate of its oceans was sealed. But what followed was not an instant disappearance, not a sudden event, but a slow and relentless process that unfolded over millions of years, gradually transforming the planet from a world that may have once held vast bodies of liquid water into one that would never see a drop again. Because as the temperature continued to rise, the oceans did not simply vanish. They turned into vapor, filling the atmosphere with water molecules, creating a thick, humid layer that trapped even more heat, pushing the system further into instability. And as this vapor rose higher into the atmosphere, it reached regions where the sun's radiation became strong enough to break it apart. This process is known as photodissociation. Ultraviolet light from the sun strikes water molecules and splits them into hydrogen and oxygen, separating the two elements that once formed the foundation of oceans. And while oxygen is relatively heavy and can remain bound to the planet, hydrogen is not. Hydrogen escapes, slowly, continuously, drifting away into space. And over time, this escape becomes permanent, a one-way process that removes water from the planet, molecule by molecule, until eventually there is none left to return. And what makes this process even more fascinating is that we can still see evidence of it today, not in the form of oceans, but in the chemistry of Venus's atmosphere, because the ratio of hydrogen isotopes, specifically deuterium to regular hydrogen, is much higher than what we see on Earth, indicating that large amounts of lighter hydrogen have been lost over time, leaving behind a signature, a kind of chemical memory of the water that once existed. It is as if Venus carries a record of its lost oceans in its atmosphere, a trace of what used to be there, a reminder of what was lost. But as the water disappeared, something else took over: carbon dioxide. With no oceans to absorb it, no geological cycles to regulate it, carbon dioxide began to accumulate in the atmosphere, building up over time, creating a thick, dense layer that trapped heat even more effectively, locking the planet into a new equilibrium, one defined by extreme temperature and pressure. A state that, once reached, became incredibly stable. And this is what makes Venus so different from Earth. Because on Earth, carbon dioxide is part of a cycle, absorbed by oceans, locked into rocks, regulated by life and geological processes, creating a system that can maintain balance over long periods of time. But on Venus, that cycle does not exist, leaving the atmosphere to evolve unchecked, driven only by physics and chemistry without any mechanism to restore equilibrium. So Venus became something else, a planet without water, without cooling, without recovery. A world where the past is written in what is missing. And this transformation is not just a detail in its history. It is the defining feature of everything it is today. Because every cloud, every degree of heat, every layer of atmosphere is connected to that loss, to the moment when Venus crossed the threshold and became a world that could no longer return to what it once was. And when we think about this, Venus becomes more than just a planet. It becomes a story of change, of loss, of transformation. A reminder that even worlds that begin in similar ways can end in completely different states, shaped by processes that, once they begin, cannot always be undone. Because on Venus, the oceans did not just disappear, they escaped forever. Even after everything Venus has gone through, after the loss of its oceans, after the transformation of its atmosphere, and after billions of years of extreme conditions, there is something about this planet that suggests it is not completely finished, not entirely static, not fully frozen in its current state, because beneath its thick clouds and scorching surface, there are signs that Venus may still be active. Because when scientists first mapped the surface of Venus using radar, they discovered something unexpected, a landscape that did not look as old as Mercury's, not as heavily cratered, not as worn by time, suggesting that something had resurfaced the planet. Something had erased older features and replaced them with newer ones, and this raised an important question. What could have done that? The answer points toward volcanoes, massive, widespread, and possibly still active, because much of Venus's surface is covered in volcanic plains, formed by ancient lava flows that spread across large areas, smoothing out the terrain and covering older impact craters, creating a surface that appears relatively young compared to other planets, indicating that Venus experienced intense volcanic activity in its past. But the real mystery is whether that activity has stopped, or if it is still happening, because recent observations suggest that Venus may still be volcanically active even today, with data showing changes in heat patterns and atmospheric composition that could be linked to ongoing eruptions, including fluctuations in sulfur dioxide levels, a gas commonly released during volcanic activity, hinting that somewhere beneath the clouds, the planet may still be releasing energy. And if this is true, then Venus is not just a static world trapped in a runaway greenhouse state. It is dynamic, still evolving, still changing, but in a way that is very different from Earth, because Venus does not appear to have plate tectonics, no shifting continents, no subduction zones, no continuous recycling of the surface. Instead, it may operate in cycles, long periods of internal heat building up beneath the surface, followed by massive global resurfacing events, where large portions of the planet are covered in lava over relatively short geological timescales, effectively resetting the surface and erasing older features. This would explain why Venus looks the way it does today: young, smooth, rewritten, a planet that may have experienced catastrophic episodes of change rather than slow, gradual evolution. And if Venus is still capable of this kind of activity, then it is not just extreme, it is unpredictable, a world where the surface we see today may not be permanent, a world that could change again, reshaped by forces we cannot directly observe, hidden beneath layers of cloud and atmosphere. But perhaps the most fascinating part is this: if Venus is still active, then it is still releasing heat, still interacting with its atmosphere, still influencing its own climate, which means that the story of Venus is not over. It is still unfolding, even now, behind those clouds, out of sight, a planet that may look still from a distance, but deep down is still alive, There is something deeply unnatural about time on Venus, something that feels almost wrong when you try to imagine it. Because on this planet, the simple idea of a day, of the sun rising in the east and setting in the west, of time moving forward in a predictable rhythm, completely breaks down, replaced by something far more confusing, far more disorienting, and far more fascinating. Because Venus does not rotate the way most planets do. In fact, it rotates backwards. While most planets in the solar system spin in the same direction that they orbit the Sun, Venus does the opposite, turning slowly in a retrograde rotation, meaning that if you could stand on its surface and somehow see the Sun through the thick clouds, you would watch it rise in the west and set in the east, reversing one of the most fundamental patterns we take for granted. But that is only the beginning. Because Venus does not just rotate differently, it rotates extremely slowly. So slowly that a single rotation, one full spin on its axis, takes about 243 Earth days, making a day on Venus longer than its year, which is only about 225 Earth days, meaning that Venus completes an entire orbit around the Sun faster than it completes a single rotation. But when you combine this slow rotation with its orbital motion, something even stranger happens. The length of a solar day, the time it takes for the Sun to return to the same position in the sky, is about 117 Earth days, meaning that if you were somehow able to observe the sky on Venus, you would experience incredibly long periods of daylight followed by equally long periods of darkness, a cycle that unfolds so slowly that it would feel almost static, almost frozen in time. And during this cycle, the motion of the Sun would not be smooth. It would hesitate, slow down, even appear to move backward briefly before continuing forward again, a result of the complex interaction between Venus's rotation and its orbit, creating a sky that behaves in ways that feel completely unfamiliar, almost broken. But why does Venus rotate this way? What caused it to reverse direction and slow down so dramatically? This is one of the great unanswered questions about the planet, and there are several theories, including the possibility of a massive collision early in its history that altered its rotation, or long-term interactions between the atmosphere and the planet's surface that gradually slowed and reversed its spin over billions of years. Because the atmosphere of Venus is so dense, so massive, that it can actually influence the rotation of the planet itself, transferring angular momentum over time, acting almost like a brake, slowing the planet down until it reached the unusual state we observe today. And this creates a world where time does not feel like it flows in the way we expect, where days are longer than years, where the Sun moves in the wrong direction, and where the passage of time becomes something that is difficult to perceive, stretched out over such long periods that it almost loses meaning. Because on Venus, time does not behave the way it should. It slows, it shifts, it reverses, and in doing so, it reminds us that even something as fundamental as a day is not universal. If the surface of Venus feels still, silent, and almost frozen in time, then the atmosphere above it is the complete opposite, because high above the dense lower layers, something extraordinary is happening, something that challenges our understanding of planetary motion, because the atmosphere of Venus is moving faster than the planet itself. This phenomenon is known as superrotation, and it is one of the most fascinating and least understood behaviors in the solar system. Because while Venus takes 243 Earth days to complete a single rotation, its upper atmosphere circles the entire planet in just about 4 Earth days, meaning that the winds are moving at incredible speeds, reaching hundreds of kilometers per hour, racing around the planet far faster than the ground beneath them. Imagine standing on the surface, where everything feels almost motionless, and above you, hidden behind thick layers of clouds, an entire system of winds is moving with relentless speed, circling the planet again and again, creating a dynamic environment that is completely disconnected from the stillness below. And this raises a fundamental question. How is this possible? How can an atmosphere move faster than the planet it surrounds? Because under normal conditions, we would expect the atmosphere to be influenced by the rotation of the planet, to move with it, to follow its motion. But on Venus, something else is happening, something that allows the atmosphere to accelerate beyond the speed of the surface, driven by a combination of solar heating, pressure gradients, and complex wave interactions within the atmosphere itself. But despite decades of study, we still do not fully understand how this system works, how the energy is transferred, how the motion is sustained, and why Venus, in particular, exhibits such an extreme version of this phenomenon, making it one of the great unsolved problems in planetary science. And within this rapidly moving atmosphere, there are patterns, swirling cloud structures, massive vortices near the poles, and dynamic systems that shift and evolve over time, creating a world that is constantly in motion, constantly changing, even though the surface below remains almost completely still. But what makes this even more unsettling is the contrast. Because Venus is a planet of opposites, a world where the surface is slow, heavy, and silent, while the sky above is fast, chaotic, and restless. Two completely different environments existing on the same planet, separated by layers of atmosphere, each one following its own rules, each one behaving in ways that are difficult to reconcile. And this contrast gives Venus a kind of dual nature, a planet that is both static and dynamic at the same time, a world where motion and stillness coexist, where energy flows through the atmosphere while the ground remains unchanged, creating a system that feels almost disconnected, almost as if the planet itself is divided into separate layers of reality. Because on Venus, the ground does not move, but the sky never stops. For a long time, Venus was considered completely lifeless, a world so extreme, so hostile, that the idea of life existing there seemed almost absurd. Because when we think about the conditions on the surface, the heat, the pressure, the toxic atmosphere, everything about it suggests that life, at least as we know it, could not survive. But then something unexpected happened, something that forced scientists to take a second look. Because high above the surface, in the upper layers of the atmosphere where conditions are less extreme, where temperatures and pressures are closer to those on Earth, there exists a narrow region that is surprisingly familiar, not comfortable, not safe, but possible. A zone where the environment is not immediately destructive, where the temperature is moderate, where pressure is manageable, and where, at least in theory, certain forms of life could exist, floating within the clouds, suspended in the atmosphere rather than living on the surface. And then came the discovery, or at least the possible discovery, a gas called phosphine, detected in the atmosphere of Venus. A molecule that on Earth is often associated with biological processes, produced by microorganisms in environments where oxygen is limited, making it a potential biosignature, something that could indicate the presence of life. But here is the problem. Phosphine should not exist on Venus, not in detectable amounts, not under known chemical processes. Because the environment of Venus does not provide an obvious way to produce it abiotically, meaning that if it is truly there, something unusual must be happening. And this is where things become uncertain. Because the detection of phosphine is still debated, with some studies supporting it and others questioning the data, suggesting that the signal may have been misinterpreted or influenced by other factors, leaving the question unresolved. But even the possibility is enough to change how we think about Venus. Because if there is even a small chance that something is happening in those clouds, something we do not yet understand, something that could be chemical, geological, or even biological, then Venus is no longer just a dead world. It becomes a mystery, a question, a place where something unexpected might exist. And this idea forces us to rethink what life could be, where it could exist, and how it might survive in environments that seem completely hostile. Because if life can adapt to extreme conditions on Earth, in deep oceans, in acidic lakes, in high radiation environments, then perhaps the limits of life are broader than we once believed. But Venus pushes those limits far beyond what we are used to. Because even in the more habitable regions of its atmosphere, the clouds are made of sulfuric acid, a substance that would destroy most known biological structures, creating a challenge that seems almost impossible to overcome. And yet, we don't know for sure, because Venus is still hiding things, still holding onto secrets, still refusing to give us a complete answer. So the question remains, is Venus truly lifeless? Or is there something in those clouds? Something we have not yet fully understood. Even after everything we have discovered about Venus, after decades of missions, data, and analysis, there is still something incomplete about our understanding of this planet, something unresolved that makes Venus feel less like a solved case and more like an open question, a world where the deeper we look, the more we realize how much we still don't know. Because Venus is not just extreme, it is complicated, in ways that we are still trying to understand. Take its atmosphere, for example, a system so dense and so dynamic that it behaves differently from anything we see on Earth, with layers that move at different speeds, chemical reactions that produce unexpected compounds, and circulation patterns that create global phenomena we cannot fully model, making it one of the most complex atmospheric systems in the solar system. And despite all our observations, we still do not fully understand how its superrotation works, how the atmosphere maintains such high speeds, and how energy is transferred between layers, leaving us with models that explain parts of the system but not the whole picture. Then there is the surface, a world we cannot see directly, a landscape we can only observe through radar. And while we have mapped it, we still do not know exactly how active it is, whether volcanoes are still erupting, how often resurfacing events occur, and how heat escapes from the interior, because without plate tectonics, Venus must operate under a completely different system, one that we are still trying to define. And even its history remains uncertain. We believe Venus may have once had oceans, but we do not know for how long. We believe it underwent a runaway greenhouse effect, but we do not know exactly when it crossed that threshold. We believe it lost its water through photodissociation, but we are still refining the details of how that process unfolded over time. And then there is the question of life, not confirmed, not ruled out, just unanswered. Because the detection of phosphine, whether real or not, has shown us that there are still signals we cannot fully explain, still observations that do not fit neatly into our models, still possibilities that remain open, even if they seem unlikely. And this is what makes Venus so important, because it represents a type of planet that may be far more common than Earth-like worlds, especially when we look beyond our solar system, where many exoplanets are found in conditions that are closer to Venus than to Earth, meaning that understanding Venus is not just about understanding one planet. It is about understanding an entire category of worlds. But to do that, we need more data, more missions, more exploration, because right now, Venus is still holding back, still hiding behind its clouds, still refusing to reveal everything. And this is why new missions are being planned, why scientists are preparing to return, to send probes, orbiters, and maybe even aerial platforms into its atmosphere, to study it in ways we have never done before, to gather the data that could finally answer some of these long-standing questions. Because Venus is not just a planet we have explored. It is a planet we have only begun to understand. And somewhere within that thick, toxic atmosphere, there are still answers waiting. When we look at Venus from a distance, glowing brightly in the sky, it is easy to forget what it truly is, easy to see it as just another planet, another point of light, something beautiful and distant. But when we understand what lies beneath those clouds, something changes, because Venus stops being just a planet. It becomes a warning, because Venus and Earth began in almost the same way. Similar size, similar mass, similar composition. Two planets forming side by side in the early solar system, shaped by the same processes, exposed to the same environment. And yet, over billions of years, they took completely different paths, ending in two entirely different outcomes. Earth became a world of oceans, life, and balance. Venus became a world of heat, pressure, and irreversible change. And the difference between them may not have been something dramatic, not a single event, but a shift, a gradual change in temperature, a slow buildup of greenhouse gases, a feedback loop that once started could not be stopped. Because the story of Venus is not just about what happened, it is about how it happened, a chain reaction. One that pushed the planet past a tipping point, beyond recovery, into a new state that has remained stable ever since. A state where the atmosphere traps heat so effectively that the surface never cools, where the conditions are locked in place, and where the planet cannot return to what it once was. And this is what makes Venus so important to us, because it shows us that planetary climates are not always stable, that they can change, that they can shift, and that under certain conditions those changes can become irreversible. Because when we study Venus, we are not just studying another world. We are studying a possibility, a scenario, an outcome that could happen to planets that seem stable, that seem balanced, that seem permanent. And while Earth is very different, with systems that regulate its climate, with oceans that absorb carbon dioxide, with life that interacts with the environment, maintaining a kind of equilibrium, the existence of Venus reminds us that this balance is not guaranteed, that it can change, that it can be lost, and that once it is lost, it may not return. But there is also something else. Because Venus is not just a warning, it is a contrast, a way of understanding what makes Earth unique, what keeps it stable, and what allows life to exist by comparing it to a world where those conditions are absent, where the balance has been broken, and where the system has moved into a completely different state. So Venus becomes a reference point, a mirror, not of what Earth is, but of what it could have been, or what it could become under different circumstances. And that is why Venus matters, not just as a planet, but as a lesson, written in clouds, hidden beneath acid skies, a story of how a world changed, and never changed back. When we look at Venus and Earth together, side by side in our minds, something feels almost unsettling, because these two worlds are so similar in their origins, so closely linked in their beginnings, and yet the outcomes are so dramatically different that it forces us to ask a deeper question, not just about these planets, but about planets in general. Why do worlds evolve the way they do? Because Venus and Earth are not just two separate planets. They are two different paths, two outcomes of the same initial conditions, shaped by small differences that over time grew into something much larger, something that ultimately determined whether a planet would become stable, habitable, and alive, or extreme hostile, and locked into a state of permanent heat. And what makes this even more fascinating is that the difference may not have been obvious in the beginning, because early Venus may have looked very similar to early Earth, with water, with a developing atmosphere, with the potential for complex processes to emerge. But somewhere along the way, something shifted. A threshold was crossed. A balance was lost. And once that happened, the two planets began to diverge, moving further and further apart in their evolution, until they became what we see today, one a living world, the other a planet where even survival is impossible. But this idea of divergence is not limited to Venus and Earth. It is something that may happen throughout the universe, in countless planetary systems, where planets form under similar conditions but evolve in different ways, depending on factors like distance from their star, atmospheric composition, geological activity, and random events that can alter the course of their history. And this means that Venus is not just an exception. It may be common. Because when we look at exoplanets, the worlds we have discovered around other stars, many of them exist in conditions that are closer to Venus than to Earth, suggesting that Venus-like planets may actually be more typical, more representative of what a rocky planet becomes when it does not maintain the delicate balance required for long-term stability. And if that is true, then Earth becomes something rare, something unusual, a planet that managed to stay within a narrow range of conditions that allowed life to emerge and persist, while many others may have followed a path more similar to Venus, becoming worlds that are stable, but in a completely different and far more extreme way. But there is also something philosophical about this, something that goes beyond science, because when we think about Venus, we are not just thinking about a planet that changed. We are thinking about a path that could have been different, a world that might have been, a version of Earth that never came to exist. And this idea that small changes can lead to completely different outcomes, that systems can diverge over time, that stability is not guaranteed, is something that applies not just to planets but to systems in general, from climates to ecosystems to even human history. Because Venus reminds us that outcomes are not fixed. They are shaped by processes, by interactions, by thresholds that once crossed cannot always be reversed. So when we look at Venus, we are not just looking at a planet that is different from Earth. We are looking at a possibility, a path, a world that followed a different trajectory. And in doing so, it reveals something fundamental about the universe, that similar beginnings do not guarantee similar endings. After decades of exploration and long periods of silence, there is now a growing sense that Venus is calling us back, not because it has become easier to explore, but because we have realized how much we still don't know, how many questions remain unanswered, and how important this planet is for understanding not just our solar system, but planetary systems everywhere. Because for a long time, Venus was overlooked, ignored in favor of Mars, focused away from in favor of worlds that seemed more promising, more accessible, more likely to hold life. But now that perspective is changing, because Venus represents something different, something essential. A planet that can teach us about climate, about atmospheric evolution, about extreme environments, and about the limits of habitability, making it one of the most important targets for future exploration. And this is why new missions are being planned, more advanced, more precise, designed not just to observe but to understand. Missions like NASA's DAVINCI and VERITAS, and ESA's Envision, all aiming to study Venus in ways we have never done before, to analyze its atmosphere in detail, to map its surface with higher resolution, and to investigate its internal structure, providing data that could answer some of the most persistent mysteries surrounding the planet. Because we are not just going back to Venus to confirm what we already know. We are going back to discover what we do, to understand how its atmosphere works, to determine whether it is still geologically active, to investigate the possibility, however small, that something unusual exists in its clouds, and perhaps even to answer the biggest question of all: how did it become this way? But Venus is not an easy place to explore, because every mission must overcome extreme challenges: heat that destroys electronics, pressure that crushes structures, chemical environments that corrode materials. Meaning that any spacecraft sent there must be carefully designed to survive, even for a short time, in conditions that are among the harshest in the solar system. And yet, despite these challenges, there is even discussion of more ambitious ideas: floating platforms, aerial probes, balloon-like habitats that could operate in the upper atmosphere, where conditions are less extreme, exploring Venus not from the surface, but from within its clouds, drifting through the atmosphere, studying it in real time, opening a new way of exploring a planet that is otherwise nearly impossible to reach. And when we think about this, the idea becomes almost surreal, not landing on Venus, but floating above it, living, or at least operating within its atmosphere, exploring a world that was once considered completely unreachable, because Venus is no longer just a planet we observed from afar. It is becoming a destination again, a challenge, a frontier, a place where the next generation of exploration will push the limits of technology and understanding. And as we prepare to return, we are not just going back to Venus. We are going back with new questions, new tools, and a new perspective, because this time, we know how much we've been missing. Imagine for a moment that humanity decides to go to Venus, not just to observe it from orbit, not just to send robotic probes, but to truly explore it, to experience it, to enter its atmosphere and see what this world is like up close. Because while this may sound impossible at first, the idea itself reveals just how different Venus is from any place we have ever considered visiting. Because landing on Venus, standing on its surface, is not just difficult, it is almost unimaginable. The temperature alone would destroy most materials within minutes. The pressure would crush anything not specifically engineered to survive extreme depths. And the atmosphere itself, filled with carbon dioxide and clouds of sulfuric acid, would create an environment where survival, even for machines, is incredibly limited. But what if we didn't go to the surface? What if we stayed above it? Because high in the atmosphere of Venus, at altitudes between 50 and 60 kilometers, conditions begin to change, not dramatically, but enough to create a region where temperature and pressure are surprisingly similar to those on Earth. A narrow band where the environment is no longer instantly destructive, where something could exist, where something could float. And this is where the idea becomes interesting, because instead of landing, we could float, cities in the clouds, stations suspended in the atmosphere, exploring Venus not from below, but from within. Because at these altitudes, the pressure is manageable, the temperature is moderate, and while the atmosphere is still composed of carbon dioxide and sulfuric acid clouds, the conditions are far less extreme than on the surface, making it one of the few places in the solar system, outside of Earth, where a human-made environment could potentially exist without being instantly destroyed. And what makes this even more fascinating is that, due to the density of Venus's atmosphere, structures filled with breathable air would naturally float, because oxygen and nitrogen are lighter than carbon dioxide, meaning that a habitat filled with Earth-like air could act like a buoyant structure, rising and staying suspended within the atmosphere without the need for constant propulsion. But even in this more habitable region, the environment would still be alien. The sky would not be blue. The light would be filtered through thick clouds. The horizon would be obscured by layers of haze. And beyond the edges of that narrow zone, above and below, the conditions would quickly become extreme again, creating a world where habitable space exists only within a thin layer, surrounded by environments that are completely inhospitable. And this creates a strange and almost surreal possibility: a human presence on Venus that is not grounded, not fixed, but floating, drifting through the clouds of another planet, exploring a world that cannot be touched, only approached. Because on Venus, the surface is not where exploration would happen, it is where it would end, and everything above it is where the future might be. There is something deeply unsettling about Venus when you begin to realize that what we are seeing today is not a temporary state, not a phase that the planet will eventually move beyond, but a condition that is stable, self-sustaining, and incredibly difficult, if not impossible, to reverse. Because Venus is not just hot, it is locked into being hot, a world that has reached a point where its own atmosphere maintains the very conditions that created it. Because once the runaway greenhouse effect took hold, once the oceans were gone and the atmosphere became dominated by carbon dioxide, the system began to regulate itself in a very different way, not toward balance but toward permanence, trapping heat so effectively that even if external conditions changed slightly, the planet would remain in its current state, unable to cool, unable to recover, unable to return to anything resembling its past. And this is what makes Venus so different from Earth, because on Earth, there are systems that push back against change, oceans that absorb heat and carbon dioxide, geological cycles that regulate the atmosphere, biological processes that interact with the environment, creating feedback loops that help maintain stability. But on Venus, those systems are gone. There is no ocean, no carbon cycle, no biological regulation, only atmosphere and heat, a system that reinforces itself continuously. And this creates a kind of finality, because Venus is not just extreme, it is stable in its extremeness. A world that has settled into a state that is unlikely to change for billions of years, unless something external happens on a massive scale, something powerful enough to disrupt the entire system. But even then, it is unclear whether such a change could ever restore Venus to a more moderate state, because once the water is gone, once the atmosphere has evolved into its current form, the pathways back become incredibly limited, requiring processes that we do not currently see occurring naturally. And this leads to a deeper realization, because when we look at Venus, we are not just seeing a planet that changed. We are seeing a planet that reached an endpoint. A state where evolution has slowed, where the major transitions have already occurred, and where what remains is a long period of stability under extreme conditions, a kind of equilibrium that, while hostile, is also consistent, predictable, and enduring. But there is also something else. Because even in this locked state, Venus is not entirely static. Its atmosphere still moves. Its surface may still experience volcanic activity. Its internal heat still exists, meaning that while the overall conditions remain stable, the details continue to evolve, creating a world that is both fixed and dynamic at the same time, a planet where change happens within limits, but the overall system remains unchanged. And this dual nature makes Venus feel almost trapped. A world that is still active, still moving, still changing in small ways, but unable to escape the larger state it has entered. A planet that has lost its flexibility, its ability to shift back towards something different. Because Venus is no longer becoming something new. It has already become what it will be. A world defined by heat, by pressure, by a past that cannot be undone, When we look at Venus in isolation, it feels extreme, unusual, almost like an outlier in our solar system, a world so different from Earth that it seems rare, something exceptional, something that does not represent the norm. But when we begin to look beyond our solar system, when we start to study the planets orbiting other stars, something surprising begins to emerge. Venus might not be unusual at all. In fact, it might be one of the most common types of planets in the universe. Because as we discover more and more exoplanets, worlds orbiting distant stars, we are finding that many of them exist in conditions that are closer to Venus than to Earth. Planets that orbit relatively close to their stars, receiving large amounts of energy, developing thick atmospheres, and potentially experiencing runaway greenhouse effects similar to what we see on Venus. These are often referred to as super-Venus worlds. Planets that may be larger, hotter, and even more extreme, but fundamentally similar in the processes that shape them, suggesting that the path Venus took may not be rare but typical, a common outcome for rocky planets that exist within certain regions of their systems. And if that is true, then Earth becomes the exception, not Venus. Because maintaining a stable climate, retaining liquid water, and avoiding runaway greenhouse conditions requires a delicate balance. A combination of distance from the star, atmospheric composition, geological activity, and possibly even chance, all working together to keep a planet within a narrow range of conditions that allow stability over long periods of time. But if that balance is disrupted, even slightly, the system can shift. And once it shifts far enough, it may follow a path similar to Venus, moving toward a hotter, denser, more extreme state, one that becomes stable in its own way, but no longer capable of supporting the kinds of environments we associate with habitability. And this changes how we think about the universe. Because instead of asking how many Earth-like planets are out there, we begin to ask how many Venus-like planets exist, how many worlds have undergone similar transformations, how many planets are locked in states of extreme heat and pressure, hidden beneath thick atmospheres, orbiting their stars in ways that make them difficult to observe directly. And the answer may be a lot, because the conditions that lead to Venus-like outcomes may be easier to achieve than the conditions required for Earth-like stability, meaning that Venus is not just a curiosity, not just a warning, but a representation of what many planets may become. And this gives Venus a new kind of importance, because by studying it, we are not just learning about one planet. We are learning about a category of planets, a class of worlds that may dominate the galaxy, planets that are stable but not habitable, active but not alive, complex but hidden beneath layers we cannot easily see. So Venus becomes more than just Earth's twin that went wrong. It becomes a prototype, a model, a window into what planets often become when conditions push them beyond balance. And in that sense, Venus is not just part of our solar system. It is part of a much larger story, one that extends far beyond our Sun. Even after everything we have learned about Venus, even after missions, radar maps, atmospheric studies, and decades of analysis, there is still a feeling that we are only seeing part of the picture, that there are layers of this planet that remain hidden, not just physically beneath the clouds, but scientifically beyond our current understanding, as if Venus is still holding something back. Because the truth is, We have never truly explored Venus in detail. We have visited it. We have observed it. We have measured it. But we have not experienced it in the way we have explored Mars or the Moon, where rovers move across the surface, where long-term missions provide continuous data, where we can watch changes unfold over time. Venus does not allow that. It resists it. Because every attempt to explore its surface is limited by time, by technology, by the extreme environment that destroys anything we send, meaning that most of what we know comes from short-lived missions, brief moments of data, snapshots rather than continuous observation. And this leaves gaps, unanswered questions, unexplored regions. Because even though we have mapped the surface, we do not know exactly how it behaves over time, whether volcanic activity is ongoing everywhere or only in certain regions, whether there are slow changes happening that we cannot detect with current data, or whether the planet undergoes sudden, large-scale events that reshape it in ways we have yet to witness. And then there is the atmosphere, a system so complex that we are still trying to understand how all its parts connect, how energy moves through it, how chemical reactions evolve, and how processes like superrotation are sustained over long periods. Because while we can observe the results, we do not fully understand the mechanisms behind them. But perhaps the most intriguing mystery is the possibility that there are phenomena on Venus that we have not yet detected at all, processes that are either too subtle, too rare, or too difficult to measure with current technology, meaning that the planet may still be hiding entire aspects of its behavior, things that could change how we understand it once they are discovered. Because every time we have looked at Venus in a new way, with better instruments, with different methods, we have found something unexpected, something that did not fit our previous assumptions, something that forced us to rethink what we thought we knew. And this pattern suggests something important, that Venus is not finished surprising us, that there are still discoveries waiting, still secrets hidden, still questions that have not even been asked yet, because Venus is not just a planet we have studied. It is a planet we are still uncovering, layer by layer, cloud by cloud, mystery by mystery, and somewhere within those thick, reflective clouds, there may still be something we have not yet seen. As we begin to reach the end of our journey across Venus, there is a shift in perspective that starts to happen, because after exploring its atmosphere, its surface, its history, and its mysteries, the planet begins to feel less like a distant object and more like something familiar, something connected to us in a way that is difficult to ignore. Because Venus is not just another planet. It is a version of a possibility, a world that in many ways began like Earth and ended somewhere completely different, and that idea carries a certain weight. Because when we think about Venus, we are not just thinking about what it is, but what it could have been, a planet that may have once had oceans, clouds made of water instead of acid, a climate that was stable enough to support complex processes, perhaps even conditions where life could have emerged, just as it did on Earth. But that version of Venus no longer exists. If it ever did, it is gone, replaced by something else, something hotter, denser, more extreme. A world that crossed a threshold and never returned. And this creates a kind of contrast that is difficult to ignore, because it forces us to think about how small differences, changes in distance, composition, or timing, can lead to completely different outcomes. How two planets that start in similar ways can evolve into worlds that are almost unrecognizable from one another. But there is also something else, because Venus does not just represent a lost possibility. It represents a completed path, a direction that a planet can take, a state that is stable even if it is extreme. Because Venus is not unstable, it is not chaotic, it is consistent, locked into its current condition, maintaining its heat, its pressure, its atmosphere in a way that has remained unchanged for millions of years, suggesting that once a planet reaches this state, it becomes incredibly difficult to leave it. And that idea carries a certain finality, because it means that the processes that shaped Venus are not temporary. They are permanent, at least on timescales that matter to us. So when we look at Venus, we are not just looking at a planet. We are looking at a path that was taken to its conclusion, a system that evolved to its endpoint, a world that shows us what happens when balance is lost and replaced by something else. And in that sense, Venus becomes something more than just a scientific object. It becomes a story of transformation, of divergence, of a world that could have been one thing and became another. And as we prepare to leave Venus behind to move on to the next planet, that story stays with us, not just as knowledge but as perspective, a reminder that planets are not fixed, that they change, that they evolve, and that their outcomes are shaped by processes that can lead them in very different directions. Because Venus is not just a planet we visited, it is a planet that makes us think. As we take one last look at Venus, glowing softly in the sky, covered in its endless clouds, it is easy to forget everything that lies beneath, easy to see it as just another bright object, another planet, something distant and beautiful, but now we know better. Because Venus is not just a planet, it is a transformation. A world that began with potential, with similarity to Earth, with the possibility of oceans, of balance, of something familiar. And yet over time it became something entirely different, shaped by processes that pushed it beyond a point of return, locking it into a state that has remained stable ever since. A world where heat never fades, where pressure never lifts, where clouds never clear, and where the surface remains hidden, unreachable, and unforgiving. But what makes Venus truly important is not just what it is what it represents. Because Venus shows us that planets can change, that systems can shift, that balance is not guaranteed, and that once certain thresholds are crossed, the outcome can be permanent, shaping a world in ways that cannot easily be undone. And yet, despite everything, Venus is not silent. It is still active. Its atmosphere still moves. Its surface may still change. Its story is still unfolding, even if the overall state remains the same, reminding us that even a world that seems fixed can still hold complexity, still hold motion, still hold secrets waiting to be uncovered. And perhaps that is what makes Venus so compelling. Not just its extremes, not just its mystery, but the fact that it still has something to tell us. Because every planet in our solar system is a chapter in a larger story, and Venus is one of the most powerful chapters of all. A story of how similar beginnings can lead to completely different endings. A story written in heat, in clouds, and in the absence of water. A story that forces us to look at planets not just as they are, but as they could become. So as we move on, leaving Venus behind and continuing our journey outward, we carry that story with us, using it to understand the next world and the next, building a picture of the solar system that is not just a collection of planets, but a system of possibilities, each one shaped by its own path, its own history, and its own outcome. Take one last look at Venus. Bright, beautiful, and hiding one of the most extreme environments we have ever discovered. Because beneath those clouds, the truth remains. What if everything about our planet is actually unlikely? What if the world you are sitting on right now, the air you are breathing, the oceans that cover most of its surface, and even the fact that life exists at all, is not something that was guaranteed, but something that emerged from a very specific and very fragile set of conditions? Conditions that, when we look at the rest of the solar system, seem almost impossible to replicate. Because Earth is not just another planet. It is the only place we know where life exists, and that alone makes it different. But when we begin to compare Earth to the other planets we have already explored, something even more surprising begins to appear, because Earth does not just support life, it maintains it over billions of years through changes, through events, through processes that should have disrupted it, and yet somehow the system remains stable. Because Earth exists in a very narrow region around the Sun. Not too close, not too far. A region where temperatures allow water to remain liquid on the surface, something that sounds simple, but is actually incredibly rare when we look at how planets behave, because being slightly closer could lead to conditions like Venus, where heat becomes uncontrollable, and being slightly farther could lead to conditions like Mars, where the atmosphere thins and water disappears. And yet Earth sits right in between, balanced, stable, but distance alone is not enough to explain it. Because Earth also has an atmosphere that does something very specific. It protects the surface from harmful radiation, regulates temperature through greenhouse gases, and allows complex chemical interactions to occur, creating a system that is dynamic but controlled, constantly adjusting, constantly balancing itself. And then there is water, liquid water, covering over 70% of the planet's surface, acting as a regulator, absorbing heat, transporting energy, supporting life, and interacting with the atmosphere in ways that create weather, climate, and long-term stability, something that we have not observed anywhere else in the solar system in the same way. But perhaps the most important factor is something we cannot see directly: Earth's magnetic field. An invisible shield generated deep within the planet, protecting it from the solar wind, preventing the atmosphere from being stripped away, preserving the conditions necessary for life to exist, something that planets like Mars have lost, and something that Venus, despite its size, does not have in the same way. And when we begin to put all of this together, the distance, the atmosphere, the water, the magnetic field, the geological activity, something becomes clear. Earth is not just lucky. It is specific. A combination of factors that work together to create a stable system, one that has remained within a narrow range of conditions for billions of years, allowing life not only to appear, but to evolve, to become complex, and eventually to become aware. Because Earth is not just a planet where life exists, it is a planet where life can think, and that changes everything. Because now the system is observing itself, understanding itself, questioning itself, And that makes Earth not just part of the solar system, but something entirely different. A world that should not be this stable, a planet that should not be this alive. And yet, it is. Right now, without thinking about it, you are breathing. Inhale, exhale. A constant, effortless process that feels so natural, so automatic that we rarely stop to consider what it actually means, or how unusual it truly is, because the air that surrounds Earth, the atmosphere that makes life possible, is not something that was always here. In fact, it shouldn't exist like this at all. Because if we go back to the early Earth, billions of years ago, the atmosphere was completely different, a toxic mixture of gases with little to no oxygen, a world where the air was unbreathable, where the conditions were harsh, unstable, and completely unsuitable for the kinds of life we know today. And yet somehow that changed. Because at some point in Earth's history, something began to produce oxygen, not in small amounts, but continuously, gradually, over millions of years. And that something was life itself, tiny organisms, microscopic, living in the oceans, using sunlight to perform a process we now call photosynthesis, converting carbon dioxide and water into energy, and releasing oxygen as a byproduct, slowly filling the atmosphere with a gas that would eventually transform the entire planet. But this transformation was not immediate, and it was not harmless. Because oxygen in high concentrations is actually toxic to many forms of early life, meaning that when it began to accumulate in the atmosphere, it caused one of the most dramatic events in Earth's history, known as the Great Oxygenation Event, a period where the environment changed so drastically that many existing organisms could not survive. An extinction, caused not by lack of resources, but by the introduction of something new, something powerful, something that would eventually make complex life possible, because oxygen does something important. It allows for more efficient energy production. It enables organisms to develop more complex structures, more advanced systems, and over time, this led to the evolution of multicellular life, of plants, of animals, of ecosystems that interact with one another in ways that create balance, diversity, and stability. But the atmosphere does more than just provide oxygen. It also protects, because high above the surface, in a region known as the ozone layer, oxygen molecules absorb harmful ultraviolet radiation from the sun, preventing it from reaching the surface in large amounts, shielding life from radiation that would otherwise damage DNA and make survival far more difficult. And at the same time, the atmosphere regulates temperature, trapping just enough heat to keep the planet warm, but not so much that it becomes unstable, creating a balance that allows liquid water to exist, a balance that, as we have seen on Venus, is not guaranteed. But perhaps the most fascinating part is this: the atmosphere is not static, it is alive. Not in the biological sense, but in the sense that it is constantly changing, constantly interacting with the surface, the oceans, and life itself, creating a system where gases are exchanged, where cycles operate, where everything is connected. Because every breath you take is part of that system. Oxygen produced by plants, carbon dioxide released by animals, a continuous exchange that links life to the atmosphere and the atmosphere to life, creating a feedback loop that has existed for millions of years. And when we step back and look at this, something becomes clear. The air we breathe is not just a resource. It is a result, a product of life, a system that exists because life created it and continues to maintain it, which means that Earth is not just a planet with an atmosphere. It is a planet where the atmosphere and life are connected, dependent on each other, evolving together, and that is something we have not seen anywhere else. If there is one thing that makes Earth fundamentally different from every other planet we have explored so far, it is not its size, not its position, and not even its atmosphere. It is water, liquid water. Because while water itself is not rare in the universe, we have found it as ice on comets, as vapor in distant atmospheres, and even hidden beneath the surfaces of moons. The presence of liquid water on the surface of a planet is something entirely different, something far more difficult to maintain, something that requires a very specific balance of conditions. And Earth has that balance. Because here, water does not just exist. It flows, it moves, it cycles, covering more than 70% of the planet's surface, forming oceans that are not just passive bodies of liquid, but active systems that interact with the atmosphere, the land, and life itself, creating a dynamic environment that constantly redistributes heat, energy, and nutrients across the planet. Because water is not just a liquid, it is a regulator. It absorbs heat during the day and releases it slowly over time, preventing extreme temperature swings, smoothing out differences between regions, and creating a climate that is far more stable than it would be otherwise, something that is essential for maintaining long-term habitability. And at the same time, water participates in a cycle, an endless loop: evaporation, condensation, precipitation, where water rises into the atmosphere, forms clouds, falls back to the surface, and repeats the process again and again, shaping weather patterns, influencing climate, and connecting different parts of the planet into a single global system. But what makes water even more unique is its ability to exist in all three states, solid, liquid, and gas, under the conditions found on Earth, something that allows it to move between environments, to interact with the atmosphere, to shape the surface through erosion, and to create habitats where life can exist and evolve. And this is where things become even more important, because water is not just part of the environment. It is part of life. Every known form of life depends on it. Cells, chemical reactions, energy transfer. All of it requires liquid water, making it one of the key ingredients for life as we understand it, and one of the primary factors scientists look for when searching for habitable worlds beyond our own. But here is the part that is easy to overlook. Earth should not necessarily have this much water, because being in the habitable zone allows water to remain liquid, but it does not guarantee that a planet will have it in the first place, and this raises an important question. Where did Earth's water come from? One possibility is that it was delivered, brought here by comets and water-rich asteroids during the early stages of the solar system, impacting the young Earth and depositing water over time, gradually building up the oceans we see today. Another possibility is that some of it was already present in the materials that formed Earth, released through volcanic activity and outgassing, contributing to the early atmosphere and eventually condensing into liquid water as the planet cooled. And the truth may be a combination of both. A process that took millions of years, a process that required the right conditions, the right timing, the right environment. And when we consider how many things had to align for Earth to have stable, long-lasting oceans, it becomes clear that this is not something that happens easily. Because too close to the sun and water evaporates, too far and it freezes, too little atmosphere and it escapes into space, too much greenhouse effect and it disappears forever like on Venus. But Earth found the balance, maintained it for billions of years. And that is what makes it extraordinary, because water is not just present here, it is stable, persistent, a defining feature of the planet, and without it, everything changes, because Earth without water is not Earth anymore. There is something protecting you right now that you cannot see, cannot feel directly, and likely never think about. And yet without it, everything on this planet would be completely different, because Earth is surrounded by an invisible force, a field that extends far beyond the surface, stretching into space, forming a barrier between our planet and the constant of energy coming from the sun. This is Earth's magnetic field, an invisible shield generated deep within the planet, created by the movement of molten metal in the outer core, where liquid iron flows and circulates, producing electric currents that, in turn, generate a magnetic field that surrounds the planet and extends thousands of kilometers into space. And this field does something essential. It protects us. Because the sun is not just a source of light and heat, it is also constantly emitting a stream of charged particles, known as the solar wind, particles that travel at incredible speeds and carry enough energy to strip away atmospheres, damage biological systems, and alter planetary environments over time. Without protection, these particles would interact directly with Earth's atmosphere, gradually eroding it, removing gases and exposing the surface to high levels of radiation, creating conditions that would make life far more difficult, if not impossible. But Earth's magnetic field deflects most of these particles, redirecting them, guiding them around the planet, creating a region known as the magnetosphere, a protective bubble that absorbs and redirects solar energy, preventing the majority of it from reaching the surface. And sometimes, a small fraction of these particles manage to enter the atmosphere near the poles, where they interact with gases in the upper layers, producing one of the most beautiful natural phenomena on Earth: the auroras, waves of light, green, red, purple, dancing across the sky, a visible reminder of an invisible shield doing its work. But the importance of the magnetic field goes far beyond beauty, because without it, Earth might have ended up like Mars, a planet that once had a thicker atmosphere, possibly even liquid water on its surface, but lost its magnetic field over time, allowing the solar wind to gradually strip away its atmosphere, leaving behind a cold, dry world with only traces of its past. And this comparison shows just how critical the magnetic field is, not just for protecting life, but for maintaining the entire system that supports it, preserving the atmosphere, stabilizing the environment, and allowing conditions to remain suitable for billions of years. But what makes this even more fascinating is that the magnetic field is not constant. It changes, it shifts, it even reverses. Over long periods of time, the north and south magnetic poles can flip, a process that has happened many times throughout Earth's history, recorded in the alignment of minerals in ancient rocks, showing that the magnetic field is dynamic, evolving, and not as stable as it might seem. And yet, despite these changes, it continues to exist, continuously generated, continuously protecting, continuously shaping the interaction between Earth and space. Because Earth is not just a planet sitting in isolation. It is part of a system where the sun constantly sends energy outward, and where the planet responds with its own defenses, its own structures, its own ways of maintaining balance. And the magnetic field is one of the most important of those defenses, an invisible shield, a silent protector, a force that has allowed life to exist and evolve on this planet for billions of years. And without it, Earth would be a very different place. It might not feel like it, sitting where you are right now, everything around you stable, solid, unmoving, but the ground beneath you is not fixed. It is moving, slowly, continuously, over time scales so vast that we do not notice it, and yet powerful enough to reshape the entire planet. Because Earth is not just a solid sphere of rock, it is a dynamic system. A planet whose surface is broken into massive pieces known as tectonic plates, enormous sections of crust that float on top of a slowly flowing layer beneath them, moving, colliding, separating and sliding past one another, driven by heat from deep within the planet. And this movement changes everything. Because where plates move apart, new crust is formed, magma rising from below, cooling and creating new land, slowly pushing the plates away from each other, expanding ocean floors, reshaping continents over millions of years. And where plates collide, something even more dramatic happens. One plate is forced beneath another, subducted, pulled down into the mantle, where it melts and becomes part of the interior again, recycling material, reshaping the surface, and creating some of the most powerful geological features on Earth. Mountains, volcanoes, earthquakes, all of them connected to this movement, all of them part of a system that is constantly changing the face of the planet. But what makes plate tectonics truly unique is not just the movement itself. It is what that movement allows, because this process acts as a regulator, a stabilizer, controlling the levels of carbon dioxide in the atmosphere over long periods of time, through a cycle where carbon is absorbed into rocks, carried into the mantle through subduction, and later released again through volcanic activity, creating a balance that helps maintain Earth's climate. And this is something we have not observed on other planets in the same way. Because without plate tectonics, a planet loses one of its most important mechanisms for regulating temperature and atmospheric composition, something that may have played a crucial role in keeping Earth stable while other planets like Venus moved into extreme states. But there is also something deeper, because plate tectonics makes Earth feel alive, not in the biological sense, but in the sense that it is constantly renewing itself, recycling its surface, reshaping its continents. A planet that is never finished, never static, always changing. Because if you go back far enough in time, the continents we know today did not exist in their current form. They were connected, split apart, reformed, drifting across the surface in a slow, continuous motion that has been happening for billions of years. And if you go far enough into the future, they will change again. New configurations, new oceans, new landscapes, because the surface of Earth is temporary, a snapshot, a moment in an ongoing process. And this is what makes Earth so different from planets like Mercury or even Venus. Because while those worlds may appear frozen in time, Earth is constantly rewriting itself, erasing old features, creating new ones, evolving in ways that are both gradual and at times sudden. So the ground beneath you is not still. It is part of a system that has been moving for billions of years. A system that shapes mountains, triggers earthquakes, and drives the cycles that keep the planet stable. Because Earth is not just a place, it is a process, a planet that moves, and in that movement, everything changes. At some point in Earth's distant past, long before animals, before plants, before anything recognizable as life existed, something happened that changed everything. Something so fundamental that it transformed a lifeless planet into one filled with complexity, diversity, and eventually consciousness. Life began. But the truth is, we don't know exactly how. Because the origin of life is still one of the greatest mysteries in science, a question that has not yet been fully answered despite decades of research, experiments, and theories. And yet, we do know something important. It did not begin suddenly. It emerged, gradually, from chemistry. Because early Earth was a very different place, a world of oceans, volcanic activity, lightning, radiation, and a mix of simple molecules interacting in ways that created increasingly complex structures, a kind of natural laboratory where the conditions allowed chemistry to become something more. And at some point, those chemical systems crossed a threshold. They became self-replicating. Molecules that could make copies of themselves, systems that could store information, structures that could evolve. And this is where the line between non-life and life begins to blur, because there is no clear moment where one becomes the other, only a transition, a gradual increase in complexity until something emerges that behaves like life. But where did this happen? One possibility is the oceans. Specifically, deep beneath the surface, near hydrothermal vents, where hot, mineral-rich water flows from the seafloor, creating environments with energy, chemical gradients, and the building blocks necessary for complex reactions. Places where life could have formed and evolved in isolation from the harsh conditions at the surface. Another possibility is shallow pools, where cycles of evaporation and concentration could have driven chemical reactions, allowing molecules to interact more frequently, increasing the chances of forming complex structures. And there are other ideas as well, but no single answer has been confirmed, because the origin of life is not something we can observe directly. It is something we have to reconstruct, piece by piece, from evidence that is billions of years old. But what we do know is that once life began, it did not remain simple. It evolved, adapted, changed. Because those early organisms, microscopic and fragile, began to interact with their environment, consuming energy, reproducing, and eventually influencing the planet itself, setting the stage for everything that would come later. And this is what makes the origin of life so powerful, because it is not just the beginning of biology. It is the beginning of a new kind of system. One where the planet and life become connected, where the environment shapes life, and life begins to shape the environment, creating feedback loops that drive further evolution, further complexity, further change. And over billions of years, this process leads to something extraordinary. From simple molecules to cells, from cells to ecosystems, from ecosystems to intelligence. Because at some point, life did something even more unexpected. It became aware. And that awareness is sitting here right now, listening, thinking, trying to understand how it all began, because Earth is not just a planet where life exists, it is a planet where life started, and that moment changed everything. Once life began on Earth, it did not remain simple for long because evolution is not a static process. It is something that moves forward, constantly experimenting, constantly adapting, constantly creating new forms while eliminating others, shaping the planet in ways that are both gradual and at times sudden. Because for hundreds of millions of years, life existed only in simple forms, microscopic organisms dominating the oceans, slowly changing the atmosphere, preparing the planet for something more complex, something that would eventually lead to a completely different kind of world. And then, something changed. Life became visible. Multicellular organisms began to appear, forming structures, developing functions, interacting with each other in new ways, leading to an explosion of diversity known as the Cambrian explosion, a period where life evolved rapidly, producing a wide range of organisms with different shapes, behaviors, and strategies for survival. And from that point on, Earth was no longer just a planet with life. It was a planet shaped by life. Because organisms began to influence the environment, altering ecosystems, creating food chains, driving competition, and pushing evolution forward, leading to the emergence of plants, animals, and eventually entire ecosystems that spread across both the oceans and the land. But evolution is not just about growth. It is also about loss, because throughout Earth's history, life has not followed a smooth path. It has been interrupted, multiple times, by events that changed everything. Mass extinctions, periods where large percentages of life on Earth disappeared in relatively short periods of time, caused by factors such as volcanic activity, climate shifts, changes in ocean chemistry, and even impacts from objects in space. And one of the most well-known of these events occurred around 66 million years ago, the extinction of the dinosaurs, triggered most likely by a massive asteroid impact, an event that released enormous amounts of energy, altering the climate, blocking sunlight, disrupting ecosystems, and ultimately leading to the collapse of food chains that had supported large species for millions of years. But what makes this event so important is not just what it ended, it is what it allowed. Because with the disappearance of dominant species, new opportunities emerged, new niches, new pathways for evolution. And in the aftermath of that extinction, mammals, which had previously been small and relatively insignificant, began to diversify, to expand, to evolve into larger, more complex forms, and eventually into something else, something capable of thought, of awareness, of reflection, because evolution does not have a goal. It does not aim for intelligence. But through a series of changes, adaptations, and events, it can lead to outcomes that are difficult to predict, outcomes that reshape the entire system in ways that could not have been anticipated at the beginning. And this is what makes Earth's history so fascinating, because it is not a straight line. It is a story of rises and falls, of creation and destruction, of systems that grow, collapse, and rebuild, because every extinction is also a beginning. Every ending creates space for something new. And when we look at Earth today, we are not just seeing the result of evolution. We are seeing the result of everything that survived, everything that adapted, everything that continued through events that could have ended it, because life on Earth is not just persistent. It is resilient, able to recover, to evolve, to change, even after the most dramatic events. And that is why Earth is not just a planet with life. It is a planet where life endures, through time, through change, through extinction. And in that endurance, it becomes something more. For billions of years, life on Earth evolved without awareness, without intention, without any understanding of the system it was part of, organisms adapting, surviving, competing, and disappearing, driven only by natural processes, until something happened that had never happened before. A species emerged that could understand, not just react, not just survive, but think. Because at some point in Earth's history, a branch of life developed the ability to reflect, to observe its surroundings, to ask questions, and to search for answers, creating something entirely new in the history of this planet: intelligence. And with it, everything began to change, because humans did not just adapt to their environment, they began to reshape it. At first, the changes were small, localized, limited to immediate surroundings. But over time, as knowledge grew, as tools improved, as societies formed, those changes became larger, more complex, and more widespread, eventually reaching a point where a single species began to influence the entire planet, altering landscapes, changing ecosystems, affecting the atmosphere, and even impacting the climate, because humans developed the ability to extract resources, to use energy stored over millions of years to build structures, to create systems that extend far beyond natural processes, creating a layer of activity that sits on top of the planet's natural systems, interacting with them in ways that are both powerful and, at times, unpredictable. But what makes this even more unique is not just the ability to change the planet. It is the ability to understand that change, to measure it, to analyze it, to predict its consequences. Because for the first time in Earth's history, the system is not just being influenced by life. It is being observed by it, studied, questioned, and that creates something entirely new: responsibility. Because humans are not just part of the system, they are aware of it, aware of how it works, aware of how it can change, aware of how fragile it can be. And this awareness creates a new dynamic, one where actions are no longer just driven by survival, but by choices, decisions that can influence the future of the planet in ways that no other species has ever been able to do. But there is also something deeper, because humans are not just changing Earth. They are leaving it, exploring beyond it, looking at their own planet from space, seeing it as a whole for the first time, a small blue sphere in a vast, empty environment, something that changes perspective completely. Because when you see Earth from space, you no longer see borders, countries, or divisions. You see a system, connected, fragile, finite. And this realization has led to something else. A question, not just how did we get here, but what do we do next? Because Earth is no longer just a planet that supports life. It is a planet that contains a species capable of altering its own future, capable of understanding the processes that shaped it, and capable of deciding, to some extent, how those processes will continue. And that makes this moment in Earth's history different from anything that came before. Because for the first time, the future of the planet is not just determined by natural forces. It is influenced by something that can think about it. And that changes everything. When we think about Earth, it is easy to assume that everything we see, the oceans, the atmosphere, the climate, the systems that support life, are stable, permanent, something that will continue as they are indefinitely. But when we look closer, when we compare Earth to other planets, something becomes clear. This balance is not guaranteed, because Earth's climate is not fixed. It is the result of a complex interaction between the atmosphere, the oceans, the land, and life itself. A system of feedback loops that regulate temperature, control the flow of energy, and maintain conditions within a range that allows life to exist. But those feedback loops can change. They can shift, and under certain conditions they can break. Because we have already seen what happens when a planet loses control of its climate. We have seen it on Venus, a world that may have once had water, a more moderate environment, a system that could have supported stability. And yet, over time, something changed. Something pushed it beyond a tipping point, triggering a runaway greenhouse effect that transformed the entire planet into what it is today. And when we look at Earth, we see a system that is different, more complex, more regulated, but still based on the same fundamental principles. Greenhouse gases trap heat. Energy from the sun drives the climate. The balance between incoming and outgoing energy determines the overall temperature of the planet. And as long as that balance is maintained, the system remains stable. But if it shifts too far, the outcome can change. Because Earth has experienced climate changes in the past, ice ages, warming periods, shifts in atmospheric composition, all part of the natural variability of the system, showing that the climate is capable of changing over time, even without external influence. But what makes the present moment different is the rate, the speed at which changes are occurring. Because when changes happen gradually, over thousands or millions of years, systems have time to adapt, to adjust, to find new forms of balance. But when changes happen quickly, over decades or centuries, the system can be pushed out of equilibrium before it has time to respond. And this creates uncertainty, because we are not just observing the climate, we are influencing it. Adding greenhouse gases to the atmosphere, altering the balance, shifting the system. And while Earth has mechanisms that can regulate change, those mechanisms have limits, thresholds beyond which the system may begin to behave differently, entering new states that are difficult to reverse. But this is where the comparison to Venus becomes important, not because Earth is becoming Venus, but because Venus shows us what happens when a system goes too far, when feedback loops become self-reinforcing, when balance is replaced by runaway processes. And while Earth is far from that state, the existence of Venus reminds us that planetary climates are not fixed, that they can change, and that under certain conditions, those changes can become permanent. But there is also something else. Because Earth is not just a system, it is a system with awareness, A system where one of its components, humanity, understands the processes that shape it, understands the potential consequences, and has the ability to respond. And that creates a difference. Because unlike Venus, Earth has the potential to recognize changes before they become irreversible, to adjust, to act, to maintain the balance that allows life to exist. But that potential depends on choices, on understanding, on action. Because balance is not something that exists automatically. It is something that must be maintained. And when we look at Earth, we are not just looking at a stable planet. We are looking at a system that can remain stable or change, depending on what happens next, because Earth is not guaranteed. It is balanced, and balance can be broken. There is a moment that astronauts often describe when they leave Earth and look back at it from space, a moment that is difficult to explain, not because it is complex, but because it is so simple, so clear, that it changes the way they see everything. Because from space, Earth does not look like a collection of places. It does not look like countries, cities, or borders. It looks like one thing, a single, continuous system. A sphere of blue, white, and green, suspended in darkness, surrounded by nothing, with no visible boundaries, no divisions, no signs of the complexity we associate with life on the surface. And this perspective creates something known as the overview effect, a shift in perception where the planet is no longer seen as a place you live on, but as a system you are part of, a realization that everything on Earth, the atmosphere, the oceans, the land, and life itself, is connected, existing within a thin layer that surrounds the planet. Because when you look closely, you notice something else. The atmosphere, not as something you breathe, but as a thin, fragile layer, barely visible. A faint glow along the edge of the planet, so small compared to the size of Earth that it becomes almost unbelievable that everything we know, every breath, every weather system, every cloud, every storm exists within that narrow band. And beyond it, nothing, no air, no protection, just space. And this changes how you think about the planet. Because from that perspective, Earth does not feel large. It feels small, finite, contained. A world that exists within limits. And those limits become clear when you see how thin the atmosphere is, how shallow the oceans are compared to the size of the planet, how narrow the range of conditions is that allows life to exist, creating a system that is both stable and fragile at the same time. But there is also something else. Because when astronauts describe this experience, they often talk about a feeling of unity, a sense that everything on Earth is connected, that the divisions we create are not visible from above, that the planet functions as a single system regardless of how we organize it. And this leads to a deeper realization. Because when you see Earth from space, you understand that there is nowhere else like it, not in the solar system, not in anything we have observed so far. A planet with liquid water, a breathable atmosphere, active geology, and life, all existing together in a way that is both complex and stable, creating something that is incredibly rare. And this perspective changes priorities. Because problems that seem large from the surface can feel smaller when you see the planet as a whole, and at the same time, the importance of protecting that system becomes more clear. Because when you see how thin and limited it is, you realize how dependent everything is on maintaining it. Because Earth is not just where we live, it is all we have. at least for now. And that realization creates a different kind of understanding, one that goes beyond science, beyond data, beyond observation, something that is more intuitive, more immediate. Because when you see Earth from space, you don't just understand it, you feel it. A small, bright world in a vast, dark universe, and everything we are exists there. At some point, a question begins to form when we look beyond Earth, when we explore the Moon, send missions to Mars, and imagine futures where humanity exists on multiple worlds. And that question is simple. Can we leave? Because for the first time in Earth's history, a species has developed the ability to move beyond the planet that created it, to travel through space, to land on other celestial bodies, and to consider the possibility of living somewhere else, turning what was once science fiction into something that is slowly becoming reality. But when we look closer, when we compare Earth to every other place we have seen, something becomes clear. Leaving Earth is not the same as replacing it. Because Earth is not just a location. It is a system, a very specific system. With the right gravity, the right atmosphere, the right temperature, the right chemistry, and the right balance of processes that all work together to support life, creating an environment that is incredibly difficult to replicate. Because when we look at other planets, we see challenges. Mars has a thin atmosphere, low pressure, and extreme temperatures. The Moon has no atmosphere at all. Venus is too hot, too dense, too hostile. And even the most promising environments we have found, like subsurface oceans on distant moons, are still completely different from Earth, requiring technology, protection, and constant support just to survive. Which means that any attempt to live beyond Earth would not be natural. It would be artificial, dependent on systems we create, maintain, and control, environments that exist only because we build them, rather than because the planet itself provides them. And this raises an important point. Because while we can leave Earth, while we can explore, travel, and even establish a presence elsewhere, we cannot easily recreate what Earth provides. Not completely. Not yet. Because Earth is not just a place we live. It is the reason we can live at all. And this leads to a deeper realization. Because when we talk about becoming a multiplanetary species, we are not talking about replacing Earth. We are talking about extending beyond it, carrying what we need with us, adapting to new environments, but always relying in some way on the system that originated here. Because even if we build habitats, even if we develop technologies that allow us to survive in space or on other planets, those systems will still be based on the principles we learned from Earth, the cycles, the balances, the interactions that make life possible. And that means something important, because Earth is not just our starting point. It is our reference, the standard by which we measure all other environments, the only place we know that works naturally. And until we find another world that can support life in the same way or develop the ability to create such systems independently, Earth remains unique, essential, irreplaceable. So the question is not just can we leave Earth? It is what happens if we do, because leaving is possible, but replacing is something else entirely. And that is what makes Earth so important, because no matter how far we go, it is still the only world we truly belong to. When we think about Earth, we often think in human terms, decades, centuries, maybe even thousands of years. But the planet itself exists on a completely different timescale, one measured in millions and billions of years, a scale so vast that it becomes difficult to truly comprehend. Because Earth has already existed for over 4 or 5 billion years, and it will continue to exist long after everything we know today is gone. But that does not mean it will remain the same, because the future of Earth is tied to something much larger, the Sun. A star that is not static, not unchanging, but evolving over time, gradually increasing in brightness as it ages, releasing more energy, altering the balance of the entire solar system in ways that are slow but inevitable. And as the sun becomes brighter, Earth will begin to change. Not suddenly, not dramatically at first, but gradually. Because even a small increase in solar energy can affect the climate, raising temperatures, altering weather patterns, and shifting the balance that currently allows liquid water to exist on the surface. And over hundreds of millions of years, this process will continue. The oceans will begin to warm. Evaporation will increase. Water vapor, a greenhouse gas, will accumulate in the atmosphere, amplifying the warming effect, creating feedback loops that push the system further away from its current state. And eventually, Earth may begin to resemble something else, not immediately like Venus, but moving in that direction. Because if the process continues long enough, the oceans could start to disappear, not all at once, but gradually evaporating, breaking apart in the upper atmosphere with hydrogen escaping into space, a process similar to what may have happened on Venus billions of years ago. And this is not speculation. It is a likely outcome, given enough time, because stars evolve and planets respond. And this means that Earth's current state is not permanent, it is temporary, a phase. A period in its history where conditions happen to allow life to exist. A window of stability that, while long on human timescales, is limited when viewed across the full lifespan of the planet. But this does not make Earth less special. In fact, it makes it more so. Because it means we exist during a very specific moment in time, a period where conditions are just right, where the balance has been maintained, where life has not only survived, but evolved into something capable of understanding all of this. And that is what makes this moment unique, because Earth is not always like this. It was different in the past, and it will be different in the future. But right now, it is exactly what it needs to be for us to exist. And that realization adds a new layer to how we see the planet. Because it is not just stable, it is temporarily stable. A balance that exists within a larger process, one that is slowly changing, one that will eventually lead to a different state, one where the conditions we depend on may no longer exist. But that is far in the future, far beyond anything we will experience. And yet it is part of the story, because Earth is not just a planet in the present. It is a planet with a past and a future, and that future is already unfolding. When we think about exploration, we often look outward toward space, toward distant planets, toward galaxies far beyond our own, imagining unknown worlds waiting to be discovered. But there is something strange about this, because one of the least explored places we know is right here on Earth. Because despite all our technology, all our knowledge, all our satellites and instruments, There are vast regions of our own planet that remain largely unexplored, places where we have limited data, limited access, and in some cases, almost no direct observation at all. And the most extreme of these places lies beneath the surface, the deep ocean. A world that covers most of the planet, yet remains one of the least understood environments we have ever encountered, because exploring it is incredibly difficult, requiring technology that can withstand immense pressure, total darkness, and conditions that are completely different from anything on the surface. Because as you descend into the ocean, everything changes. Light disappears, temperature drops, pressure increases, until you reach depths where the environment becomes almost alien, a place where sunlight never reaches, where the only sources of energy come from chemical reactions or rare biological processes, creating ecosystems that function in ways that are fundamentally different from those on the surface. And within these depths, life exists. Not just simple organisms, but complex ecosystems, creatures that have adapted to complete darkness, to high pressure, to limited resources, evolving in isolation, developing forms and behaviors that seem almost unreal, as if they belong to another planet rather than our own. Some produce their own light, bioluminescence, glowing in the darkness, communicating, hunting, surviving, in ways that we are only beginning to understand. And then there are places even more extreme, hydrothermal vents, where hot, mineral-rich water flows from the seafloor, creating environments where life is not powered by sunlight, but by chemical energy, a completely different system, one that may resemble the conditions under which life first began on Earth. And this raises an important question. Because if life can exist in these extreme environments, in complete darkness, under immense pressure, relying on chemical energy instead of sunlight, then the range of conditions that can support life may be much broader than we once thought. Which means that when we search for life beyond Earth, we are not just looking for Earth-like environments. We are looking for systems, energy sources, conditions that allow complexity to emerge, even if they look nothing like what we are familiar with. But there is something else, because despite all we have discovered, a large portion of the ocean floor remains unmapped in detail, unexplored, unobserved, meaning that there are still areas where we do not know what exists, where new species, new ecosystems, and new processes could still be waiting to be discovered. And this creates a strange contrast. Because while we send missions to Mars, while we explore the outer planets, while we search for life on distant moons, there are parts of our own planet that remain just as mysterious, just as unknown, just as unexplored, because Earth is not fully known, not completely understood. It still holds secrets, hidden beneath the surface, in places we cannot easily reach, in environments that challenge our ability to explore them. And this makes Earth something unexpected, not just familiar, but mysterious, a world that we live on, but do not fully know. When we think about Earth, we often imagine it as a comfortable place, a world where conditions are stable, where life thrives in balanced environments, where everything feels familiar and predictable. But this is only part of the story, because Earth is not just a habitable planet. It is also a planet of extremes. A world where, in certain places, the conditions are so harsh, so far from what we consider normal that they begin to resemble environments we would expect to find on other planets rather than our own. Because on Earth, there are regions where temperatures rise above 50 degrees Celsius, deserts where water is almost non-existent, where life survives only through extreme adaptation, conserving energy, minimizing exposure, existing at the edge of what is possible. And at the same time, there are places where temperatures drop below -80 degrees Celsius, polar regions where ice dominates the landscape, where darkness can last for months, where life persists despite the cold, adapting to conditions that seem almost uninhabitable. But temperature is only one factor. Because there are environments where pressure becomes extreme, deep beneath the ocean, where organisms live under conditions that would crush most forms of life, and yet they survive, not just enduring the pressure, but depending on it, evolving structures that function only under those conditions. And then there are places where acidity reaches levels that would destroy most biological systems, lakes filled with chemicals that are toxic to nearly all known organisms. And yet even there, life exists, microorganisms that have adapted to survive in environments that seem completely incompatible with life as we understand it. These are known as extremophiles, organisms that live at the limits of what is possible, in heat, in cold, in pressure, in acidity, in radiation, expanding our understanding of where life can exist, showing us that the boundaries we once believed were fixed are actually much wider than we thought. And this has changed the way we look at the universe. Because if life can exist in these extreme environments on Earth, then perhaps it can exist in similar conditions elsewhere, in places we once considered uninhabitable, such as the subsurface oceans of icy moons, the atmospheres of distant planets, or even environments that do not resemble Earth at all. But there is also something deeper here, because these extreme environments remind us that Earth is not uniformly comfortable. It is not uniformly stable. It is a planet with a wide range of conditions, a spectrum that includes both the environments where life thrives easily and those where survival requires constant adaptation. And this creates a kind of contrast, because while Earth supports life, it also challenges it. It creates conditions that push organisms to their limits, driving evolution, forcing adaptation, shaping the diversity of life we see today. And in that sense, Earth is not just a place where life exists. It is a place where life is tested, continuously, across environments that range from ideal to extreme. And this testing is what drives change, what drives evolution, what drives the development of systems that can survive in conditions that would otherwise be impossible. Because Earth is not just one environment. It is many, a collection of worlds within a single planet, each with its own conditions, each with its own challenges, each pushing life in different directions, and together they create something extraordinary, a planet that is not just habitable, but diverse, complex, and constantly evolving. For a long time, it has felt like humanity has gained control over Earth, shaping landscapes, building cities, altering rivers, influencing the atmosphere, creating systems that extend far beyond what any other species has ever done. And in many ways, that is true. We can modify environments. We can predict weather patterns. We can extract resources. We can build structures that change the surface of the planet, and from that perspective, it can feel as if we are in control. But when we look deeper, when we consider the full scale of Earth systems, something becomes clear. That control is limited, because Earth operates on forces that are far larger than anything we can fully manage, systems driven by energy from the sun, by heat from the planet's interior, by interactions between the atmosphere, oceans, and land, processes that have been shaping the planet for billions of years, long before humans existed, and that will continue long after. Because no matter how advanced our technology becomes, we cannot stop tectonic plates from moving. We cannot prevent volcanic eruptions from occurring. We cannot fully control the climate system in the way we control machines or structures. We can influence it. We can alter it. But we are still part of it, not separate from it. And this creates an important distinction, because there is a difference between influence and control. Influence means we can change aspects of the system. Control would mean we can fully manage it. And Earth is too complex for complete control, because it is not a single system. It is many systems interacting at once, each with its own dynamics, its own feedback loops, its own thresholds, creating a network of processes that respond to changes in ways that are not always predictable. And sometimes, those responses can be sudden, unexpected, because systems that appear stable can shift when certain conditions are met, when thresholds are crossed, when feedback loops begin to amplify changes rather than stabilize them. And this is where the illusion of control becomes clear, because even though we can influence Earth, we cannot fully determine how it will respond. We can act, but the system reacts in its own way, on its own terms. And this does not mean that human actions are insignificant. In fact, they are powerful, capable of altering the balance, capable of creating changes that can affect the system over long periods of time. But it does mean that we are not outside the system. We are within it, part of it, subject to the same forces that shape everything else on the planet. And this creates a different kind of understanding. Because instead of seeing Earth as something we control, we begin to see it as something we interact with, something we influence but do not dominate, a system that requires balance, not control, understanding, not assumption. Because Earth is not a machine. It is not something that can be fully directed. It is a complex, dynamic system, and we are part of that system, not above it, not separate from it. And once that becomes clear, the perspective changes. Because the question is no longer how do we control Earth, but how do we live within it, without breaking the balance that allows it to function. At some point, when you step back far enough, when you move beyond the details of atmosphere, oceans, geology, and even life itself, a different kind of question begins to appear, one that is not purely scientific but also philosophical, a question that does not have a simple answer and yet feels impossible to ignore. Why are we here? Because when we look at Earth, we see a chain of events, a sequence of processes that led from the formation of the planet to the emergence of life, to the evolution of complex organisms, to the development of intelligence, and finally to a point where that intelligence is able to look back and ask how it all happened. And that chain is long, extremely long, filled with events that could have gone differently, conditions that could have shifted, moments that, if changed even slightly, might have led to a completely different outcome. Because if Earth had formed slightly closer to the Sun, the oceans might never have existed. If the atmosphere had developed differently, life might not have emerged. If certain extinction events had not occurred, the path of evolution might have taken a completely different direction. And if even one of these factors had been different, we might not be here at all, which raises a deeper idea. Because our existence is not just the result of a single event, it is the result of a sequence. A chain of conditions, processes, and moments that all had to align in a way that allowed life to not only begin, but to continue, to evolve, to become complex enough to reach this point. And that makes Earth feel less like a random place and more like a very specific outcome. But that does not mean it was planned. It does not mean it was designed. It means it was possible. And given enough time, enough variation, enough processes, that possibility became reality. Because the universe is not static. It is full of systems interacting, changing, evolving, creating conditions where complexity can emerge, where structures can form, where life can appear under the right circumstances. And Earth happens to be one of those places. A location where the conditions aligned, where the processes worked together, where the chain continued long enough to produce something capable of asking these questions. But what makes this even more interesting is that the question itself is part of the system, because the universe has no inherent need to understand itself. But through life, through intelligence, it gains that ability, a way to observe, to reflect, to analyze, meaning that when we ask why we are here, we are not just asking a question, we are part of the answer. Because we are the result of the processes we are trying to understand, a system becoming aware of itself. And that creates a kind of loop, because we study the universe, but we are also part of it. We try to understand Earth, but we are also shaped by it. We ask how life began, but we are living examples of that beginning. And this changes the perspective, because Earth is not just a planet where life exists. It is a place where the universe has become aware, where matter has organized itself into structures that can think, question, and explore, creating a connection between the physical processes of the planet and the abstract concepts of thought and understanding. And that is something extraordinary, because it means that Earth is not just part of the universe. It is a place where the universe is thinking about itself. For most of Earth's history, the future was something that simply happened, shaped by natural processes, by evolution, by geological forces, by events that no organism could predict or control. But now, for the first time, the future is becoming something different, something directed, something influenced by a species that not only exists within the system, but understands it, studies it, and is beginning to shape it in ways that extend far beyond natural evolution. Because humanity is no longer just adapting to Earth, it is modifying it, altering environments, engineering systems, creating technologies that change how energy flows, how resources are used, and how information moves across the planet, building a layer of complexity that did not exist before. And this layer is growing rapidly, because technological development is not linear. It accelerates, each advancement building on the previous one, creating a feedback loop of innovation that increases the speed at which change occurs, leading to a world that is evolving not just biologically, but technologically. And within this evolution, something new is emerging: artificial systems, intelligence that is not biological, systems that can process information, learn, adapt, and interact with the world in ways that were once limited to living organisms, creating a new kind of entity within the system, one that is fundamentally different from anything that has existed before. And this raises new questions. Because if intelligence is no longer limited to biology, if systems can be created that can think, analyze, and evolve in their own way, then the nature of life, of intelligence, and of the system itself begins to change. Because now the future of Earth is not just shaped by natural evolution. It is shaped by decisions, by design, by systems that can be created intentionally. And this creates uncertainty. Because while technology can solve problems, improve efficiency, and expand possibilities, it can also introduce new challenges, new dynamics, new interactions that are not always fully understood. Because complex systems can behave in unexpected ways. They can evolve. They can interact with existing systems in ways that produce outcomes that were not anticipated. And this means that the future is no longer just unknown because of natural processes. It is unknown because of what we create, because every advancement opens new possibilities, new directions, new paths that the system can take. And some of those paths may lead to outcomes that are very different from what we expect. But there is also something else. Because for the first time, the future of Earth includes the possibility of extending beyond the planet, of creating systems that exist in space, on other worlds, or even independent of planetary environments, meaning that the influence of life originating on Earth could expand beyond its original system, becoming part of a much larger context. And this changes the scale of the question, because now the future is not just about Earth. It is about what comes after. What happens when a planet that produced life begins to produce systems that can leave it, that can operate beyond it, that can continue evolving in environments that are completely different from the one where they originated. And this leads to a final thought, because the future is not something that is waiting to happen. It is something that is being created right now, through decisions, through actions, through systems that are already in motion. And the direction it takes is not fixed, because for the first time in Earth's history, the future is not just happening, it is being shaped. When we look out into the universe, when we observe distant stars, galaxies, and planets far beyond our solar system, one question keeps returning again and again, a question that feels simple but carries a weight that is difficult to fully understand. Are we alone? Because Earth, as far as we know, is the only place where life exists, the only planet where biology has emerged, evolved, and reached a level of complexity that allows it to think, to communicate, to ask this very question. And yet, when we look at the scale of the universe, the number of stars, the number of planets, the vastness of space itself, it seems almost impossible that Earth would be the only place where this has happened, because there are hundreds of billions of galaxies, each containing hundreds of billions of stars, and around many of those stars there are planets, worlds, environments, some of them potentially similar to Earth. which means that the conditions that allowed life to emerge here could, in theory, exist elsewhere. And if they exist elsewhere, then life might exist elsewhere. But here is the problem. We have not found it. Not yet. Despite decades of searching, despite listening for signals, analyzing atmospheres, studying distant worlds, we have not detected clear evidence of life beyond Earth, and this creates something known as the Fermi paradox, a contradiction between the high probability that life should exist somewhere in the universe and the lack of evidence that it does. And this paradox leads to many possibilities. Maybe life is rare. So rare that Earth is one of the few places where it has emerged. Or maybe life is common, but intelligent life is rare, meaning that simple organisms might exist in many places, but the development of complex thinking beings is much less likely. Or maybe life exists, but it is too far away, too different, or too quiet for us to detect with our current technology. Or, in a more unsettling possibility, maybe civilizations do not last long. Maybe the stage we are in right now is brief, temporary, a small window in time where a species becomes advanced enough to explore and communicate, but not stable enough to persist for long periods. And if that is the case, then the silence we observe is not because life does not exist, but because it does not last. But there is also another possibility, that we are early, that the universe is still in a stage where life is just beginning to emerge, that Earth is not late in the timeline, but among the first, meaning that the absence of other civilizations is not because they are gone, but because they have not yet formed. And this idea changes the perspective completely, because it means that Earth is not just one of many. It might be one of the first, a starting point, a place where life has reached a level of complexity that has not yet become common across the universe. And if that is true, then the question is not just are we alone? It is what comes next. Because if we are early, then the future of life in the universe may depend in part on what happens here, on how life evolves, how it expands, how it interacts with the cosmos beyond its home planet. And this makes Earth feel even more significant, not just as a place where life exists, but as a place where the future of life in the universe could begin. But we do not know. Not yet, because the universe is vast, silent, and full of possibilities, and somewhere out there may be something else, or there may be nothing at all, and until we find an answer, the question remains. After everything we have explored, from the formation of Earth to the origin of life, from the rise and fall of species to the emergence of intelligence, from the balance of climate to the vast unknown of the universe, something begins to settle in, a realization. Because no matter how far we look, no matter how much we discover, no matter how many planets we find or how many systems we explore, there is one thing that remains unchanged. This is the only world we know that works. Because Earth is not just habitable, it is active, balanced, connected in ways that are difficult to replicate, with systems that interact across scales, from microscopic organisms to global climate, from chemical cycles to biological processes, creating a network that sustains life continuously. And within that network, we exist, not separate, not independent, but as part of it, because everything we are depends on this planet, the air we breathe, the water we drink, The systems that regulate temperature, provide resources, and allow life to continue. All of it is connected to Earth. And this creates something that is easy to overlook: dependence. Because no matter how advanced we become, no matter how far we explore, no matter how much technology we develop, we are still tied to the systems that originated here, systems that we do not fully control, systems that operate on scales and complexities that go beyond any single species. And this makes Earth more than just a place. It makes it a foundation, a system that supports everything we know, everything we have built, everything we understand. And when we compare it to the rest of the solar system, the difference becomes even more clear. Mercury is too hot and unstable. Venus is too extreme and irreversible. Mars is too cold and thin. The outer planets are gas giants with no solid surface to stand on. And while there are moons and distant worlds that may hold potential, none of them offer what Earth does naturally: a complete system, working together, maintaining balance, allowing life to exist without constant external support. And that is what makes Earth unique, not just because life exists here, but because life can exist here without constant intervention, because the planet itself provides what is needed. And this is something we have not found anywhere else. And maybe we will. Maybe one day we will discover another world like this, another planet with oceans, atmosphere, and life, another system that works in the same way. But until that happens, this is it. This is the only example we have, the only known case of a planet that supports life in this way, and that realization changes how we see it, because Earth is no longer just familiar. It is rare, possibly extremely rare, and that rarity gives it value, not just scientifically, but fundamentally, because it means that what exists here does not exist everywhere, and that makes it something worth understanding, something worth protecting, something worth remembering, because no matter how far we go, this is where it all began. As we come to the end of our journey across Earth, something becomes clear that was not obvious at the beginning, something that only emerges when you step back and look at the entire picture, from the formation of the planet to the present moment. Earth is not just a place. It is a story that began billions of years ago, with dust and gas coming together, forming a planet, a world that was once hostile, unstable, and lifeless, and that slowly, over time, transformed into something completely different, something capable of supporting oceans, atmosphere, and life. A story that continued as life emerged, evolved, and adapted, moving through stages of simplicity and complexity, through periods of stability and extinction, through changes that reshaped the planet again and again. A story that reached a point where life became aware, where a species began to understand the system it was part of, began to explore, to question, to look beyond its own world and into the larger universe. And that story is still ongoing, because Earth is not finished, it is not complete. It is still evolving, still changing, still moving through time, shaped by the same processes that have always defined it, and now also by something new, something that has never existed before in the history of this planet. Conscious influence. A species that can understand the system, that can observe its own impact, that can make decisions that affect the future. And this adds a new layer to the story. Because for the first time, The direction of the story is not determined only by natural forces. It is influenced by choice, by awareness, by actions that can shape what comes next. But at the same time, Earth remains what it has always been: a system, complex, dynamic, connected, operating on scales that go far beyond human perception, reminding us that while we can influence it, we are still part of something much larger. And as we prepare to move on, to leave Earth behind and continue our journey through the solar system, there is one final thought that remains. Because every planet we explore tells a different story. Mercury shows us extremes of temperature and isolation. Venus shows us what happens when balance is lost. And Earth shows us what happens when everything aligns. When conditions come together in just the right way to allow something extraordinary to happen. Because Earth is not just another planet in the solar system. It is the only place where the universe has become aware of itself, at least as far as we know, a world where matter has organized into life, life into intelligence, and intelligence into something that can look back and understand the process. And that makes it more than just a chapter. It makes it a turning point. Because from here, the story can go anywhere, outward, into space, to other worlds, to new systems, to new possibilities, but no matter where it goes. It started here, on a small blue planet, orbiting an ordinary star in a vast universe. And that is what makes Earth unforgettable. What if Mars wasn't always like this? What if the cold, dry, silent world we see today is not what Mars was meant to be, but what remains after something went wrong? Something that changed the planet so completely that it turned from a world that may have once been alive into the empty landscape we see now. Because when we look at Mars today, we see a desert, endless red dust, frozen ground, a thin atmosphere that barely holds onto heat. A planet where liquid water cannot exist on the surface for long, where temperatures drop far below freezing, and where the environment feels more like a memory than a living system. But Mars was not always like this. Because when we study its surface, when we analyze its geology, something unexpected appears, something that does not belong to the Mars we see today. Evidence of water, not small amounts, not isolated traces, but vast systems. Ancient river valleys carved into the surface, dried up lake beds, minerals that can only form in the presence of liquid water, and even structures that resemble shorelines, suggesting that Mars may have once had oceans. A planet that billions of years ago might have looked very different, not red and empty, but blue, flowing, active. Because if liquid water existed on Mars, then the planet must have had a thicker atmosphere, one capable of trapping heat, maintaining pressure, and allowing water to remain stable on the surface, creating conditions that, at least for a time, could have supported something more. And that raises a question. If Mars once had water, what happened to it? Because today that water is gone, not completely but mostly, locked away in ice, hidden beneath the surface, trapped at the poles, no longer part of an active system, no longer shaping the planet in the way it once did. And the answer may lie in something Mars lost, its magnetic field. Because just like Earth, Mars once had a magnetic field, an invisible shield that protected its atmosphere from the solar wind, preserving the conditions needed for stability. But at some point in its history, that field disappeared. And when it did, everything changed. Because without that protection, the solar wind began to interact directly with the atmosphere, slowly stripping it away molecule by molecule over millions of years, reducing the pressure, lowering the temperature, and making it increasingly difficult for liquid water to exist on the surface. And as the atmosphere thinned, the planet cooled, the water disappeared, the system collapsed, leaving behind what we see today, a planet that did not just change, but lost something essential. And that is what makes Mars so different from Earth, because Earth maintained its magnetic field, maintained its atmosphere, maintained its oceans, but Mars did not. And when we look at it now, we are not just seeing another planet. We are seeing the remains of a system that once worked and then stopped, a world that may have been alive in its own way and is now silent. And that silence raises one of the most important questions we can ask. Did life ever exist there? Or did Mars lose everything before it had the chance? If Mars once had water, then it wasn't just a few scattered streams or temporary flows, because the evidence we see today suggests something much larger, something that changes how we imagine this planet entirely. An ocean. Because when scientists map the surface of Mars, they find patterns that look strikingly familiar. Vast lowlands in the northern hemisphere, smooth and wide, surrounded by higher terrain, almost like a basin, a region that could have held an enormous body of water, covering a significant portion of the planet. And along the edges of this region, there are features that resemble ancient shorelines, contours that follow consistent elevations, stretching across thousands of kilometers, as if marking the boundary of something that once existed there. Something that is no longer there now. But the evidence goes deeper. Because scattered across the surface are minerals that only form in the presence of water, clays, sulfates, compounds that require long-term interaction with liquid water to develop, suggesting that water was not just present briefly, but existed for extended periods of time, shaping the chemistry of the planet. And then there are the river valleys. Channels carved into the surface, branching networks that look almost identical to river systems on Earth, complete with tributaries, erosion patterns, and flow directions, indicating that water once moved across the planet, not randomly but as part of a system. A cycle: rainfall, flow, collection, evaporation. A hydrological system that may have once existed on Mars, connecting the atmosphere, the surface, and the interior in a way that is very similar to what we see on Earth today. But if all of this existed, if Mars once had rivers, lakes, and possibly even oceans, then something must have sustained it, because liquid water requires pressure, it requires temperature, it requires an atmosphere thick enough to prevent it from immediately evaporating or freezing, which means that early Mars was not just wet, it was different, warmer, denser, more active, a planet that, at least for a time, may have looked more like a smaller version of Earth than the frozen desert we see today. But then something changed, because whatever system allowed water to exist on Mars collapsed. And when it collapsed, the effects were irreversible. Because as the atmosphere thinned, the pressure dropped, and without sufficient pressure, liquid water cannot remain stable on the surface. It either freezes or evaporates almost instantly, meaning that even if water were present, it could not exist in the form we associate with rivers or oceans. And so the water disappeared, not all at once, but gradually, over millions of years. Some of it escaped into space. Some of it froze into ice. Some of it may still exist underground. But the system that once allowed it to flow, to move, to shape the planet, was gone. And this is what makes Mars so fascinating. Because when we look at it today, we are not just seeing what it is. We are seeing what remains. A surface that still carries the marks of something that is no longer active, a record of a time when Mars was different, when it had conditions that could have supported something more. Because water is not just important, it is essential for chemistry, for stability, for life. And where there was water, there is always a possibility that something else was there too, something we have not yet found, something that may still be hidden beneath the surface. If water once flowed across Mars, if rivers carved valleys and oceans filled basins, then there must have been something holding it there, something keeping the planet warm enough, pressurized enough, stable enough for liquid water to exist. That something was the atmosphere. But today, Mars barely has one. A thin layer of gas, mostly carbon dioxide, so weak that it cannot retain heat, cannot support stable liquid water, and cannot protect the surface from radiation in the way Earth's atmosphere does. So the question becomes unavoidable. What happened to it? Because atmospheres do not simply disappear overnight. They are lost, slowly, over time, and on Mars that loss may have been driven by a single critical event, the disappearance of its magnetic field. Because early in its history, Mars likely had a magnetic field similar to Earth's, generated by movement in its core, creating an invisible shield that protected the atmosphere from the constant stream of charged particles coming from the sun. But at some point, that shield faded, the core cooled, the dynamo stopped, and the magnetic field weakened and then disappeared. And when it did, Mars was exposed. Because without that protection, the solar wind, a continuous pair of high-energy particles emitted by the sun, began to interact directly with the atmosphere, transferring energy, stripping away molecules, and gradually eroding the entire system. Not violently, not suddenly, but relentlessly, over millions of years. Because every second, small amounts of gas were lost, carried away into space, too little to notice in the moment, but enough to matter over time. And as the atmosphere thinned, everything else began to change, because pressure dropped, temperature dropped, water became unstable. And once those changes began, they reinforced each other, creating a cascade, a chain reaction where each loss made the next one more likely. Less atmosphere meant less heat retention. Less heat meant more freezing. More freezing meant less active water. And less water meant fewer processes that could support atmospheric stability. Until eventually, the system collapsed, leaving Mars in the state we see today. Cold, dry, exposed. A planet where the surface is directly affected by radiation, where the sky is thin, where the conditions that once allowed water to exist are no longer present. But what makes this even more powerful is that this process is still happening. even now. Because Mars is still losing its atmosphere slowly, continuously, with particles escaping into space, carried away by the solar wind, a process that has not stopped, a process that continues to shape the planet even today. And this gives Mars a kind of timeline, a story of loss. Because when we look at it, we are not just seeing a static world. We are seeing a planet in decline, a system that once had more, and now has less. And that raises a deeper question. Because if Mars lost its atmosphere, if it lost its water, if it lost its stability, then what else did it lose? Because where there is water, there is always the possibility of life. And if Mars once had the conditions for water to exist, then maybe, just maybe, it had the conditions for something else too. Something that disappeared along with everything else, or something that is still there, hidden, waiting to be found. If you could stand on the surface of Mars right now, if you could somehow survive the cold, the thin atmosphere, and the radiation, the first thing you would notice would not be what you see. It would be what you hear, or rather, what you don't, because Mars is silent. Not completely silent, but close enough that the difference becomes unsettling, because with such a thin atmosphere, sound does not travel the way it does on Earth. It is weaker, quieter, more distant, as if the world itself is absorbing it, dampening it, reducing everything to a faint presence rather than a clear experience. And this creates an environment that feels empty, not just visually, but physically. Because when you look around, you would see a landscape that stretches endlessly, covered in red dust, broken rocks, and wide, open plains, a surface shaped by ancient processes but no longer active in the way we are used to. No flowing water, no vegetation, no movement of life, just stillness. But that stillness is not complete because Mars is not entirely inactive. It breathes in its own way, through dust. Because one of the most defining features of Mars today is its dust storms, events that can range from small, localized disturbances to massive, planet-wide storms that cover the entire surface in a layer of fine particles, blocking sunlight, altering temperatures, and reshaping the appearance of the planet over time. And these storms are powerful, driven by temperature differences, by solar heating, by the interaction between the surface and the thin atmosphere, creating winds that, despite the low pressure, can move vast amounts of dust across the planet, lifting it high into the sky, where it can remain suspended for long periods. And sometimes, these storms grow, expanding, merging, until they become global, encircling the entire planet, turning Mars into a world where the sky itself becomes opaque, where visibility drops, where the surface is hidden beneath a moving layer of dust, creating a phenomenon that has no direct equivalent on Earth. But even these storms eventually settle. The dust falls, the sky clears, and the silence returns. A silence that is not just the absence of sound, but the absence of activity. Because Mars is not evolving in the same way Earth is. It is not being reshaped continuously by active systems. It is not being renewed. It is preserving what remains, a snapshot of a past that no longer exists. And this is what gives Mars its atmosphere of mystery. Because when we look at it, we are not just seeing a planet. We are seeing a memory, a record of processes that have stopped, a world that once had movement, water, and possibly even life. and now has only traces. And those traces are everywhere, in the valleys, in the rocks, in the minerals, in the dust that covers the surface. Each one a piece of a larger story, a story that is incomplete, because we still do not know everything that happened here. We still do not know how far the transformation went, or what might have existed before everything changed. Because Mars is not just silent, it is quiet in a way that feels unfinished, as if something was there once and is no longer. For most of human history, Mars was just a distant point of light in the sky, something we could observe but never touch, a world that existed beyond our reach until something changed. We started sending machines. Because reaching Mars is not simple, it requires traveling millions of kilometers through space, navigating precisely, entering an atmosphere that is too thin to slow you down easily, yet still dense enough to create intense heat during entry, and then landing safely on a surface we had never experienced directly. And yet, we did it. Because over the past decades, humanity has sent a series of robotic explorers to Mars, landers and rovers designed to survive, to move, and to study a planet that no human has ever walked on. And when the first images arrived, everything changed, because for the first time Mars was no longer an abstract concept. It was a place, a real landscape, a horizon, a sky, a ground that looked strangely familiar and yet completely alien at the same time, because the images showed rocks, sand, hills, shadows, things we recognize from Earth, but arranged in a way that feels empty, untouched, as if no life had ever interacted with it. And that emptiness is what makes it so powerful, because these machines are alone, completely alone, operating in an environment where there is no life, no sound, no movement beyond the wind and dust, sending back data, images, and measurements across millions of kilometers, turning Mars from a mystery into something we can begin to understand. But these missions are not just about images. They are about questions. Because each rover carries instruments designed to analyze the soil, the rocks, the atmosphere, searching for signs of water, for chemical signatures, for anything that might indicate that Mars once had conditions suitable for life. And what they have found is not life, but something just as important: clues. Because the rocks they study show evidence of past water, sedimentary layers, minerals formed in liquid environments, structures that suggest lakes, rivers, and long-term interaction with water, reinforcing the idea that Mars was once very different from what it is today. And more recently, rovers like Perseverance are doing something even more ambitious. They are collecting samples, carefully storing pieces of Mars, with the intention of bringing them back to Earth in the future, where they can be analyzed with far more advanced instruments, searching for microscopic signs, chemical patterns, or structures that could indicate past life. Because the question is no longer just what Mars is. It is what Mars was, and whether that past included something more. But what makes these missions even more fascinating is the way they operate, because these rovers are not fully autonomous. They are controlled, guided, and monitored from Earth, meaning that every movement, every decision is delayed by minutes. The time it takes for signals to travel between the two planets, creating a system where humans and machines are connected across space, working together to explore a world that neither could reach alone. And this creates something unique, because Mars is not just being explored, it is being experienced through machines, through data, through images that allow us to see a place we have never been. And yet, despite all of this, Mars still feels distant, because no matter how many images we receive, no matter how much data we collect, there is still a gap between observing a world and being there, because the machines are alone, and through them, we are there, but only partially, because Mars is still waiting for something more. If Mars once had water, if it once had a thicker atmosphere, if it once had conditions that were warmer and more stable, then one question becomes unavoidable. Did life ever begin there? Because on Earth, life appeared relatively quickly once the conditions allowed it, emerging from chemistry, evolving into simple organisms, and eventually into the complex systems we see today, suggesting that when the environment is right, life does not necessarily take billions of years to start. And if that is true, then early Mars may have had a chance, because the evidence suggests that Mars was once habitable, at least for a period of time, with liquid water, energy sources, and the necessary chemical ingredients, creating an environment that, in theory, could have supported microbial life. But here is where things become uncertain, because even if life did begin on Mars, the planet changed. The atmosphere was lost. The surface became cold. The water disappeared, and the environment that once supported stability collapsed. Which means that if life ever existed there, it would have faced a choice: adapt or disappear. And this is where the idea becomes more complex, because life does not always require ideal conditions. On Earth, we have found organisms in extreme environments, deep underground in high radiation zones, in acidic lakes, and in environments with almost no light or oxygen, showing that life can survive in places that were once considered impossible. Which raises a possibility, because if life on Mars ever existed, it may not have disappeared completely. It may have moved underground, because beneath the surface of Mars, conditions are different. Temperatures are more stable, radiation is reduced, and there may still be pockets of water, frozen or even liquid under certain conditions, creating environments that are more protected than the surface. And if microbial life adapted to these conditions, it might still exist, hidden, inactive, or slowly surviving, beyond our direct observation. But this is not something we have confirmed. Not yet. Because detecting life, especially microscopic life, especially life that may be dormant or deeply buried, is incredibly difficult, requiring precise measurements, careful analysis, and often direct sampling, something we are only beginning to approach with current missions. And this is why Mars is so important, because it represents a test, a comparison, a second chance to understand how life begins, how it evolves, and how it responds to change, by studying a planet that may have once had the same opportunity as Earth, but ended differently. Because if we find life on Mars, even simple microbial life, it would change everything, showing that life can emerge more than once, that it is not unique to Earth, that the universe may be filled with systems where biology takes hold under the right conditions. But if we do not find it, That is also important, because it would suggest that even when conditions appear suitable, life may not always begin, or that it may be more fragile than we think, disappearing when the environment changes beyond a certain point. And both outcomes matter, because Mars is not just a planet we are exploring. It is a question, a place where we are trying to understand whether life is common or rare, whether it persists or disappears, whether it is resilient enough to survive planetary change, or dependent on conditions that cannot always be maintained. And somewhere beneath that red surface, the answer may already be there, waiting. Imagine waking up on Mars, not as a visitor, not as a scientist observing from a distance, but as someone who lives there. Because for the first time in human history, this is no longer just an idea, it is something being seriously considered, planned, and studied, the possibility that humans could one day travel to Mars, not just to explore it, but to stay. But what would that actually feel like? Because Mars is not Earth, not even close. And the differences begin the moment you arrive. Because the gravity is weaker, about 1/3 of what you experience on Earth, meaning that every movement feels different, lighter, easier, but also unfamiliar, requiring your body to adapt to a new way of moving, a new way of existing in space. And then there is the sky, not blue, but a pale, reddish tone during the day, filled with dust, with the sun appearing smaller and dimmer, casting a different kind of light across the surface, creating an environment that feels both familiar and completely alien at the same time. But the real challenge is not what you see. It is what you cannot survive without, because Mars does not provide what Earth does naturally. There is no breathable air, no stable liquid water on the surface, no natural protection from radiation, meaning that every aspect of survival would depend on technology, habitats, life support systems, protective structures, everything designed to create an artificial environment within a natural one that cannot support life on its own. And this creates a very different kind of existence. Because on Earth, we step outside without thinking. We breathe without effort. We exist within an environment that supports us automatically. But on Mars, nothing is automatic. Every breath is supported by a system. Every drop of water is managed. Every moment outside requires protection. And this changes how you experience the world. Because Mars would not just be a place you live. It would be a place you survive. But there is also something else. Because living on Mars would mean distance. Not just physical distance, but psychological distance. Because Mars is far, millions of kilometers away, meaning that communication with Earth would be delayed, sometimes by several minutes, making real-time interaction impossible, creating a sense of separation that no human has ever experienced before. Because you would not just be in another place. You would be in another world, completely, with no immediate connection to home, and that changes perspective. Because Earth would no longer feel like a place you can return to easily. It would feel distant, almost unreachable in the moment, a blue dot in the sky, visible but far away. And this creates a new kind of experience, a sense of isolation, of being part of something new, something that has never existed before. A human presence on another planet. But despite all the challenges, the risks, the uncertainties, there is also something powerful about the idea. Because living on Mars would not just be about survival. It would be about expansion, exploration, the beginning of something new. Because for the first time humanity would exist beyond Earth, becoming a multiplanetary species, extending its presence into the solar system, taking the first step towards something larger. But that step is not simple. It is not easy, because Mars is not welcoming. It is not prepared for us. It is a world we would have to adapt to build within, to survive through systems we create ourselves. And that makes it one of the greatest challenges humanity has ever faced, because Mars is not just another destination. It is a test of technology, of resilience, of what it means to exist beyond the only world we have ever known. And if we go there, everything changes. At some point when we begin to imagine humans living on Mars, building habitats, surviving in controlled environments, another idea naturally follows, a much bigger idea, one that feels almost like science fiction and yet is taken seriously enough to be studied, debated, and modeled. What if we could change Mars itself? Not just adapt to it, but transform it, turn it into something more like Earth. This idea is known as terraforming, and in theory it sounds simple. Make the atmosphere thicker, warm the planet, release trapped gases, create conditions where liquid water can exist again, restart the processes that once made Mars habitable. But in reality, it is anything but simple, because Mars is not just cold and dry. It is missing key components: a thin atmosphere, a weak gravitational hold on gases, no global magnetic field, meaning that even if we could increase the temperature, even if we could release carbon dioxide from the polar ice caps or the soil, even if we could create a temporary greenhouse effect to warm the planet, there is still a problem. The atmosphere would not stay. Because without a magnetic field, the solar wind would continue to strip it away, just as it has been doing for billions of years, meaning that any attempt to rebuild Mars's atmosphere would be fighting against a constant loss, a process that does not stop. And then there is the question of resources. Because to significantly alter an entire planet, to change its atmosphere, its temperature, and its surface conditions, would require an enormous amount of energy, far beyond anything humanity currently has access to, a scale of engineering that goes beyond building cities, beyond building countries, into something that operates on a planetary level. And even if we could achieve that, it would take time, not years, not decades, but centuries or longer, a process that would extend far beyond a single generation, requiring continuous effort, continuous development, and a level of commitment that is difficult to imagine. But there is also something deeper, because terraforming is not just a technical challenge. It is a philosophical one, because Mars is what it is. A world with its own history, its own evolution, its own path. And changing it would mean altering that path, replacing one planetary state with another, creating something artificial, something shaped by intention rather than natural processes. And this raises questions. Should we change Mars? Should we transform it into something more like Earth? Or should we preserve it as it is, as a record of what happened, as a natural system that tells a story we are still trying to understand? Because Mars is not just a candidate for transformation. It is a source of knowledge, a window into planetary evolution, a place where we can study what happens when a planet loses its atmosphere, its water, and its stability. And once we change it, that record could be lost. But at the same time, the idea of terraforming represents something else: ambition, the possibility that a species can grow beyond its original environment, not just adapting to new worlds but shaping them, creating conditions where life can exist where it otherwise could not, extending the reach of life beyond a single planet. And that idea is powerful, because it suggests that planets are not just destinations, they are possibilities. Things that can be changed, reshaped, and influenced over time. But Mars reminds us of something important, because even if we try to change it, we are working against billions of years of evolution, against a system that has already settled into its current state. And that makes the challenge immense, because Mars is not waiting to become Earth. It is something else entirely, and whether we adapt to it or try to change it, the question remains: can we really turn another planet into a world like our own, or will Mars always remain Mars? Even though Mars already feels empty, already looks like a world that has lost everything that once made it active, the truth is that its story is not finished, because the processes that transformed Mars into what it is today are still happening right now. Because Mars is not a planet that suddenly became cold and stopped changing. It is a planet that is slowly continuing along the same path, losing small amounts of its atmosphere over time, particle by particle, carried away by the solar wind, a process that has been ongoing for billions of years and has not yet come to an end. And while the changes today are subtle, almost impossible to notice on human timescales, they are significant over geological time, meaning that Mars is still evolving, still shifting, still moving further away from the conditions it once had. Because the atmosphere it has now is already thin, but it can become thinner. The water that remains is already limited, but it can become more inaccessible. The surface is already exposed, but it can become even more extreme. And this creates a kind of slow transformation, not dramatic, not sudden, but continuous, because Mars is not frozen in time, it is drifting, gradually, further into a state where the possibility of change becomes smaller and smaller, where the conditions become more stable, but also more extreme, more distant from anything that resembles the past it once had. And this makes Mars feel different from Earth, because Earth is dynamic, balanced, capable of shifting between states, but Mars is moving in one direction, toward simplicity, toward stillness, toward a state where fewer processes remain active, where fewer interactions occur, where the system becomes less complex over time. And this gives Mars a kind of timeline, a trajectory, because if we project forward far enough, Mars will not suddenly become something new. It will continue becoming what it already is: colder, thinner, more silent. A planet that is slowly approaching a kind of equilibrium, not because it is balanced in the way Earth is, but because there is less and less left to change. And this creates something almost unsettling, because when we look at Mars, we are not just seeing a world that changed in the past. We are seeing a world that is still changing, but in a way that leads toward less atmosphere, less activity, less possibility, And that raises a deeper thought, because if Mars once had more, if it once had water, a thicker atmosphere, and a more active system, then what we are seeing now is not just a different state, it is a later state, a future, a direction that a planet can move toward when key systems are lost. And that makes Mars more than just a neighboring world. It makes it an example, a glimpse of what happens when a planet cannot maintain its balance, when protective systems fail, when processes that once sustained complexity begin to disappear. Because Mars is not just empty, it is becoming empty. And that process has not ended. When we place Mars and Earth side by side, not just physically in the solar system, but conceptually as two planets that formed in similar ways around the same star from the same materials, something becomes impossible to ignore. They started similarly, but they did not end the same. Because Mars is smaller, yes, farther from the Sun, yes, but those differences alone do not fully explain the outcome, because what matters is not just where a planet forms, but what happens after. And Mars tells a story of loss, because everything that Earth still has. Mars once may have had an atmosphere, liquid water, a magnetic field, systems that allowed stability. And yet over time those systems disappeared, not suddenly, but gradually, until the planet could no longer support the conditions it once did. And that is what makes Mars feel so different from other planets, because it is not just extreme like Venus. It is not just distant like the outer planets. It is familiar, almost recognizable. A world that looks like it could have been something else. Because when we see valleys that look like dried rivers, when we see minerals that formed in water, when we see landscapes that suggest a past that was more active, more dynamic, more Earth-like, we are not just seeing geology. We are seeing a version of a possibility, a path that did not continue, and that creates a kind of connection. Because Mars is not just another planet, it is a comparison, a reference point, a way of understanding what makes Earth different, not by looking at Earth itself, but by looking at what happens when things go another way. Because Earth maintained its magnetic field, Mars did not. Earth maintained a thick atmosphere, Mars lost it. Earth kept its water in a stable cycle, Mars could not. And these differences, while they may seem small at the beginning, grow over time, leading to completely different outcomes. One planet becomes alive, the other becomes silent, and that contrast is powerful, because it shows us that habitability is not just about starting conditions. It is about continuity, about maintaining systems over time, about preserving balance, because once those systems fail, and it changes, and it does not easily return. And this is where Mars becomes something more than just a neighboring world. It becomes a reminder, not of danger in the same way Venus is, but of fragility, because Mars did not explode. It did not experience a single catastrophic event that destroyed everything at once. It changed slowly, losing piece after piece of what made it active, until what remained was something simpler, colder, quieter. And that is what makes it so powerful. Because when we look at Mars, we are not just looking at what it is, we are looking at what is left. And in that sense, Mars is not just a planet, it is a memory. For all of human history, Mars has been something we looked at from a distance, a point of light in the sky, a symbol of mystery, of possibility, of something just out of reach. But now, for the first time, that distance is beginning to shrink, because Mars is no longer just a target for robotic exploration. It is becoming the next destination for humans, and that changes everything, because sending humans to Mars is not just another mission. It is a shift, a transition from exploring a planet to becoming part of it, even if only temporarily, a step that moves humanity beyond Earth in a way that has never happened before. But this step is not simple, because Mars is not close. It is not easily accessible. It requires months of travel through space, exposure to radiation, isolation, and the challenge of sustaining life far from the systems that naturally support it on Earth. And once you arrive, the challenges continue, because landing on Mars is one of the most difficult tasks in space exploration, requiring precise timing, complex engineering, and systems that must work perfectly, because there is no margin for error, no second attempt. And even if the landing is successful, survival on Mars is not guaranteed, because everything needed to live must be brought, built, or produced locally. Air, water, food, energy, all of it part of a system that must function continuously, without interruption, in an environment that offers no natural support. And this creates a kind of tension, because Mars is both the next step and a massive risk. Because unlike missions to the Moon, where return is relatively quick, a mission to Mars involves long durations, limited opportunities to return, and a level of isolation that has never been experienced before, meaning that the first humans to go there will not just be explorers. They will be pioneers, operating at the edge of what is possible. But there is also something else, because going to Mars is not just about survival, it is about presence. Because once humans are there, even briefly, Mars changes, not physically, but conceptually. Because it is no longer just a place we observe, it becomes a place we have been, a place that is part of human experience. And that shift is important, because it transforms Mars from an idea into a reality, something that is no longer distant but connected to us in a direct way. And from that point on, everything changes, because exploration does not stop with arrival, it expands. Because once humans are on Mars, the question is no longer can we go, it becomes how long can we stay, and what comes after, because Mars is not just the next destination. It is the beginning of something larger, a step toward becoming a species that is not limited to one planet, a step toward a future where Earth is not the only place where human life exists. But that future is not guaranteed, because Mars is not easy, it is not forgiving. It is a world that demands preparation, precision, and resilience. And that makes it one of the greatest challenges humanity has ever faced. Because going to Mars is not just about reaching another planet. It is about proving that we can exist beyond Earth. Even after everything we have discovered about Mars, the valleys, the dried riverbeds, the minerals shaped by water, and the thin atmosphere that remains, there is one place we have barely explored at all: beneath the surface. Because while Mars looks empty from above, its surface may only tell part of the story, a layer that has been exposed, eroded, and frozen over time, while something else may still exist below, hidden from direct observation, protected from the harsh conditions that define the planet today. And this is where things become more mysterious. Because Mars is filled with structures that suggest the existence of underground spaces, lava tubes, caverns, and voids formed by ancient volcanic activity, tunnels created when molten rock flowed beneath the surface and later cooled, leaving behind empty channels that could extend for kilometers. And these spaces are different, because underground conditions change. Temperatures become more stable. Radiation is reduced. The environment is shielded from the constant impact of the solar wind and cosmic radiation, creating a region that is far less extreme than the surface above. And this raises a possibility. Because if Mars once had life, and if the surface became uninhabitable, then the underground may have become a refuge, a place where conditions remained stable enough for something to survive, hidden from the changes that transformed the rest of the planet. And even today, there are hints that water may still exist below the surface, not in large oceans, but in pockets, in frozen layers, or possibly even in briny liquid forms that can remain stable under certain conditions, creating environments that are not entirely dry, not entirely inactive. And if water exists, even in small amounts, then the possibility remains. Because life does not require vast oceans, it requires conditions, energy, chemistry, time, and Mars has had all of these at some point. And perhaps in some places it still does. But exploring the underground is not easy, because we cannot see it directly. We cannot send rovers deep below the surface easily. We rely on indirect methods, radar, seismic data, and surface observations that suggest what might be below but do not confirm it completely. And this means that some of the most important parts of Mars may still be hidden, unexplored, unknown, because everything we have seen so far is only the surface. A layer that tells us what Mars looks like now, but not necessarily everything about what it is. And this creates a different kind of mystery, because when we look at Mars, we are not just looking at a planet that has been explored. We are looking at a planet that is only partially known. A world where the most important answers might not be on the surface at all, but beneath it, hidden in darkness, protected from time, waiting. If you could go back in time billions of years into the history of Mars, what you would see would not resemble the planet we know today, because the red, dry, silent world we observe now is only the final stage of a much longer story. A story that once looked very different, because early Mars may have been warmer, wetter, more active. A world where liquid water flowed across the surface, where rivers carved their paths, where lakes filled basins, and where, in the northern hemisphere, a vast ocean may have stretched across the lowlands, reflecting the sky in a way that we can only imagine today. And the sky itself would have been different. Not the pale, dusty red we see now, but thicker, hazier, filled with a denser atmosphere that trapped heat, creating a climate that allowed water to remain stable, creating conditions that, at least for a time, could support a dynamic environment. And in that environment, the planet would not have felt empty. Because water changes everything. It moves, it erodes, it transports materials, it creates patterns, it shapes landscapes, turning a static surface into a system that is constantly evolving, constantly interacting with itself. And this would have given Mars a sense of activity, of motion, of something happening, but this version of Mars did not last because something shifted. The atmosphere began to thin, the magnetic field disappeared, the temperature dropped, and the water slowly began to disappear. And if you could watch this process unfold, not in moments but across millions of years, you would see a transformation that is both gradual and irreversible, rivers shrinking, lakes drying, the ocean retreating until eventually, what was once a flowing system became a frozen and fragmented one. And this creates a strange perspective, because when we look at Mars today, we are not just looking at a planet. We are looking at two versions of it at once, the present and the past, because the surface still carries the marks of what used to exist, valleys that no longer carry water, minerals that formed in environments that no longer exist, structures that tell a story of a time when Mars was something else. And this makes Mars feel almost like a time capsule, a record of planetary evolution, preserved in a way that allows us to see what happened, even if we cannot experience it directly. Because unlike Earth, where active processes constantly reshape the surface, erasing older features, Mars has remained relatively unchanged for long periods, preserving its history in a way that allows us to study it, to reconstruct it, to imagine it. And that imagination is powerful, because it allows us to see Mars not just as it is now, but as it once was, a world that may have had clouds, rain, flowing water, and a climate that supported a completely different environment. And that leads to a final thought. Because if Mars once looked like that, if it once had water, atmosphere, and stability, then for a moment in time, it may have been a place where something more could exist, something that we have not yet found, or something that existed and is now gone. There is something about Mars that feels different from every other planet we have explored, not just because of its history, not just because of the possibility that it once had water, but because of how it feels. Because Mars feels empty, not just physically empty, but emotionally empty. Because when we look at images from Mars, when we see the landscapes captured by rovers, the wide horizons, the rocky terrain, the endless dust, there is something familiar about it, something that almost resembles places on Earth, deserts, dry valleys, rocky plains. And yet, something is missing, because on Earth, even in the most remote deserts, there is still life. Microorganisms, insects, movement, sound. Something that reminds you that the system is active, but on Mars, there is nothing, no movement, no sound, no sign that anything is happening beyond the slow movement of dust across the surface. And that creates a feeling that is difficult to describe, because it is not just the absence of life, it is the absence of activity. A world that is no longer participating in the processes that define a living planet. And this is what makes Mars feel so different from Earth, because Earth is full of interactions, full of systems, full of life constantly shaping and reshaping the environment. But Mars is quiet, as if something ended there, as if the processes that once made it active have stopped, leaving behind a surface that continues to exist but no longer evolves in the same way. And this creates a kind of loneliness, not for the planet itself, but for us, Because when we look at Mars, we are not just observing it, we are projecting ourselves onto it, imagining what it would feel like to stand there, to be surrounded by that silence, to look out across a world that has no signs of life, no signs of movement, no signs that anything is happening beyond what you can see. And that experience would be unlike anything on Earth. Because on Earth, even when you are alone, you are not truly alone. The environment is still active, still alive, still interacting with you in subtle ways. But on Mars, you would be completely isolated, not just from other humans, but from life itself. And that changes the experience, because Mars would not just feel distant, it would feel disconnected. A place where the systems that define a living world are no longer present, where the environment does not respond, does not interact, does not change in ways that are familiar to us. And this is what gives Mars its emotional weight, because it is not just a planet that lost its atmosphere, its water, and its stability. It is a planet that lost its presence, a world that exists, but no longer feels alive. And when we look at it, when we imagine standing there, when we try to understand what it would be like, that is what stays with us. Not the dust, not the rocks, not even the cold, but the silence, because Mars is not just empty, it is alone. And if we ever go there, for the first time in its history, it won't be anymore. There are many planets in our solar system, each with its own characteristics, its own extremes, its own story. And yet Mars stands apart in a way that is difficult to explain using only science, because while other planets impress us with their scale, their storms, their rings, or their complexity, Mars does something else. It resonates, because Mars is not just interesting, it is relatable, in a way that no other planet is, because when we look at Jupiter, we see something massive and distant. When we look at Saturn, we see beauty and structure. When we look at Venus, we see a warning. But when we look at Mars, we see something that feels familiar, a landscape that resembles our own, mountains, valleys, deserts, a horizon that looks like something we could stand on. And that familiarity creates a connection, because Mars is not completely alien. It is almost Earth-like, but not quite. And that almost is what makes it so powerful, because it feels like something that could have been more, something that was close, close to being habitable, close to being active, close to being a world where life could exist. And yet, it is, and that creates a kind of tension, because Mars is not just different from Earth. It is a version of Earth that didn't make it, a path that ended differently, a world that started with potential and lost it. And this idea goes beyond science, because it touches something deeper, something about possibility, about how systems evolve, about how outcomes are not guaranteed, because Mars shows us that being close is not enough, that having the right starting conditions does not ensure the right outcome, that small differences can grow into large consequences over time. And this makes Mars feel less like a distant object and more like a story of what happens when a system loses its balance, when processes fail, when conditions shift beyond recovery. And that story feels familiar because it reflects something we understand in other contexts, that things can change, that systems can break, that outcomes are not fixed. And that is why Mars stays with us, because it is not just a planet we observe. It is a planet we relate to, a world that feels like it could have been something else, a world that reminds us that potential does not always become reality. And in that sense, Mars is not just a place, it is a reflection. There is a moment when you think long enough about Mars, when the question changes, when it stops being just about what the planet is or what it used to be and becomes something else entirely. What if something is still there? Because even though Mars looks empty, even though everything we have seen so far suggests a world without life, without activity, without presence, there is still uncertainty because we have not explored everything, not even close. Because the surface we have studied represents only a fraction of the planet, small regions visited by rovers, specific locations chosen for their scientific value, leaving vast areas untouched, unseen, unexplored. And beneath that surface, we know even less. Because the underground of Mars remains largely inaccessible, a place where conditions are different, more stable, protected from radiation, shielded from the extreme environment above, creating regions that are not as hostile as the surface we observe. And this is where the uncertainty begins. Because if life ever existed on Mars, even in simple forms, even as microorganisms, then it may not have disappeared completely when the surface became uninhabitable. It may have adapted, moved, changed, because life does not always vanish when conditions worsen. Sometimes it survives, in hidden places, in environments that are not immediately obvious, in forms that are difficult to detect. And this idea is not just theoretical. Because on Earth, we have found life in places that were once considered impossible, deep underground, in extreme conditions, surviving without sunlight, without oxygen, relying on chemical energy instead. Which means that if similar conditions exist on Mars, then the possibility remains, even if it is small, even if it is uncertain, even if we have not yet found evidence. And this is what makes Mars different from a completely lifeless world, because it is not confirmed to be dead. It is only unconfirmed to be alive. And those are not the same thing, because absence of evidence is not evidence of absence. And this creates a tension, because every time we explore Mars, every time we send a new mission, every time we analyze new data, we are not just studying geology or atmosphere. We are searching, looking for something that may or may not exist, something that may be hidden, something that may have survived in ways we do not yet fully understand. And until we know for sure, the possibility remains. And that possibility changes how we see the planet, because Mars is no longer just a world that lost everything. It is a world that may still hold something, something small, something hidden, something waiting to be discovered. And that idea is powerful, because it means that Mars is not just a memory, it is still a question. And that question has not been answered yet. Imagine a moment in the future, a moment that does not seem dramatic at first, no explosions, no sudden signals from the sky, no instant realization that everything has changed, but instead something quiet, a result, a pattern in the data, a structure under a microscope, something small, almost easy to miss, but different. Because one day, a rover or a lander or a sample returned to Earth might reveal something unexpected, not a clear sign of life in the way we imagine it, not a moving organism or something visible to the eye, but something more subtle. A chemical signature that should not be there. A pattern that cannot be explained by geology alone. A structure that suggests organization, complexity, something that does not form randomly. And at first it would be questioned, analyzed, rechecked, because the discovery would be too important to accept immediately, too significant to risk being wrong. But if the evidence holds, if the pattern repeats, if the data confirms what it suggests, then something changes, because for the first time we would know that life is not unique to Earth, that it has happened more than once, that the universe is not a place where biology exists in only one location, but something that can emerge wherever conditions allow it. And that realization would be quiet, at first, because it would begin in laboratories, in data, in analysis, but it would not stay there, because once confirmed it would spread across science, across humanity, across the way we understand existence itself. Because finding even the simplest form of life on Mars, even something microscopic, even something ancient, would change the scale of the question. Because it would mean that life is not a rare accident. It is a process, something that can happen under the right conditions, something that may be happening in many places across the universe. And that changes everything. Because suddenly, Earth is not the only example. Mars becomes the second, a confirmation, a proof that life is not limited to one planet. And from that point on, the search expands. Because if life existed on Mars, where else might it exist? On icy moons, on distant planets, in environments we have not yet explored, and the universe becomes less empty, less silent, more alive. But there is also another possibility. Because what if we find something, but it is not what we expect? What if it is not just simple life? What if it is something that does not resemble life on Earth at all? Something that evolved differently, something that followed another path, because Mars had different conditions, different timelines, different changes, and that could mean different outcomes. And that idea is even more unsettling, because it suggests that life is not just repeating. It is diversifying, taking different forms, following different rules, expanding beyond what we understand. And that would not just answer a question, it would create new ones. Because understanding life on Earth is one thing, understanding life that evolved somewhere else is something entirely different. But until that moment comes, until we find something, until the data confirms it, Mars remains in a state of possibility, a place where the answer exists, but has not yet been revealed. And that makes it one of the most important places we can explore, because one discovery could change everything. For all the questions we ask about Mars, for all the possibilities we imagine, for all the theories about water, atmosphere, and life, there is one possibility that is often overlooked, not because it is unlikely, but because it is difficult to accept. What if there was never anything there? Because even though Mars once had water, even though it may have had conditions that were suitable for life, that does not guarantee that life ever began. Because on Earth, life emerged. But we do not fully understand how. We do not know exactly what conditions are required, how precise they must be, or how often they occur, meaning that even if Mars had water, even if it had a thicker atmosphere, even if it had energy sources, it may still not have crossed the threshold. Because the origin of life may not be inevitable. It may be rare, extremely rare, something that requires a very specific set of conditions, aligned in just the right way, at just the right time. And if that is true, then Mars may have been close, but not close enough. And that possibility changes everything, because it means that Mars is not a failed Earth. It is a planet that never became one, a world that had potential, but never transitioned into something more. And that idea is unsettling, because it suggests that even when conditions seem right, even when everything appears to be in place, life does not always happen. That there may be many planets in the universe that look similar to early Earth, with water, atmosphere, and energy, but remain completely lifeless. And if that is the case, then life may not be common. It may not be something that appears wherever it can. It may be something that appears only rarely. And that makes Earth different, not just because it has life, but because it has life at all. Because if Mars, a planet that may have once had similar conditions, remained lifeless, then the existence of life on Earth becomes even more significant, more unlikely, more special. But there is also another layer to this. Because if Mars never had life, then all of its history, all of its changes, all of its transformations happened without biology influencing the system, meaning that everything we see on Mars is purely geological, purely physical, a record of a planet that evolved without life shaping it. And that makes it a perfect comparison, a control, a way to understand how planets evolve without biology, because Earth is shaped by life. Its atmosphere, its chemistry, its surface, all influenced by biological processes. But Mars is not, and that difference allows us to see something clearly, because by comparing the two, we can begin to understand what life does to a planet, how it changes it, how it interacts with it, how it becomes part of the system. And in that sense, Mars is just as important if it never had life, as it would be if it did, because both answers teach us something, but emotionally. The idea of a lifeless Mars is heavier, because it means that all of that potential, all of that water, all of those conditions led to nothing. No organisms, no evolution, no presence, just chemistry, just physics. A planet that had everything it needed. Except the one thing that changes everything. And that thought stays with you, because it makes Mars feel not just empty, but silent in a different way. A silence that was always there. After everything we have explored, the water, the atmosphere, the possibility of life, the loss, the silence, the uncertainty, Mars begins to feel less like a distant planet and more like something else. A reflection, because Mars is not just a world we study. It is a world we compare to Earth, to ourselves, to the path we are on. Because when we look at Mars, we see what happens when a planet changes, when systems fail, when conditions that once supported stability begin to disappear. And while Mars and Earth are different, the comparison is still there. Not as a direct warning, but as a perspective, because Earth is stable, for now, balanced, active, full of systems that support life. But Mars reminds us that stability is not permanent, that conditions can change, that systems can shift, and that the outcome is not always guaranteed, because Mars was not always what it is now. And that is what makes it important, because it shows us that planets evolve, that they move through different states, that what exists now is not fixed, and this connects to something deeper. Because when we study Mars, when we try to understand its past, we are also trying to understand our own future, not in a direct sense, but in a broader way by learning how planetary systems behave, how they change, and what factors determine their stability. And this knowledge matters, because Earth is not separate from these processes. It is part of the same universe, the same physics, the same long-term evolution. And while the timescales are different, the principles are the same. But there is also something more personal, because Mars is not just about planets. It is about perspective. Because when we look at Earth from Mars, when we imagine standing on that red surface and looking up at the sky, seeing a small blue point in the distance, that changes how we think about our home. Because Earth is no longer everything. It is something. Something specific. Something limited. A place that exists within a much larger system. And that realization is powerful, because it shifts our understanding from being centered on one planet to being part of something bigger. Something that extends beyond Earth, beyond Mars, beyond the solar system. And this is where Mars plays a unique role, because it is close enough to reach, similar enough to compare, different enough to teach. A planet that allows us to step outside of our own world, even if only conceptually, and see things from a different perspective. And that perspective is important, because it reminds us that what we have on Earth is not common, not guaranteed, not easily replicated. And that makes it valuable, not just scientifically, but fundamentally, because Mars is not just about what it is. It is about what it shows us, about change, about possibility, about fragility, and about the fact that even when two worlds begin in similar ways, they can end very differently. And that realization stays with you, because it is not just about Mars, it is about us. As we reach the end of our journey across Mars, something becomes clear that was not obvious at the beginning, something that only reveals itself when you step back and look at the entire picture, from the ancient oceans to the silent deserts, from the thick atmosphere to the thin air that remains today. Mars is not just a planet. It is a story of what was and what is no longer. Because billions of years ago, Mars may have been a world with flowing water, with a sky that held warmth, with conditions that allowed something more to exist, a planet that was not empty, not silent, but active, evolving, changing. And then, something shifted, not all at once, not in a single moment, but gradually. The magnetic field faded, the atmosphere thinned, the water disappeared, and the planet changed, until what remained was something completely different. A world that still carries the marks of its past but no longer lives in it. And that is what makes Mars so powerful, because when we look at it, we are not just seeing a planet. We are seeing time, frozen, preserved, a record of a transformation that has already happened but that we are only now beginning to understand, because Mars is not hiding its story. It is written across its surface, in every valley, in every rock, in every layer of dust. But the story is incomplete, because we still do not know everything. We do not know if life ever existed there. We do not know how long the water remained. We do not know how far the transformation went before it became irreversible. And that uncertainty is part of what makes Mars so fascinating, because it is not just a world we understand. It is a world we are still discovering, still questioning, still exploring. And that exploration is not over, because the next missions, the next discoveries, the next steps towards sending humans there, all of them will bring us closer to understanding what Mars really is, not just as a planet, but as a process, a history, a possibility. And as we leave Mars behind, as we prepare to continue our journey through the solar system, there is one final thought that remains, because every planet we visit tells us something different. Mercury showed us extremes. Venus showed us what happens when balance is lost. Earth showed us what happens when everything works. And Mars shows us what happens when a world begins to change and cannot recover. And that is why we will keep coming back, because somewhere in that silence, there is still something we have not found, something that could change the way we understand everything. What if I told you that Jupiter almost became a star, not metaphorically, not symbolically, but physically? Because when Jupiter formed billions of years ago, it didn't just become the largest planet in our solar system. It came dangerously close to becoming something else entirely, something much more powerful, a second sun. Because Jupiter is not like the other planets. It is massive. So massive that it contains more than twice the mass of all the other planets combined. A giant made mostly of hydrogen and helium, the same elements that make up stars, the same building blocks that, under the right conditions, can ignite nuclear fusion. And that's where things get interesting. Because if Jupiter had just a little more mass, not 10 times more, not even 5 times more, but roughly 80 times its current mass, it could have ignited fusion in its core, becoming what we call a brown dwarf, an object that sits between a planet and a star, which means that our solar system almost had 2 suns, but it didn't, because Jupiter stopped growing. It reached a point where it could no longer accumulate enough material to cross that threshold, leaving it in a strange state, not a true planet in the traditional sense and not a star either, but something in between. A failed star. And that alone would make Jupiter fascinating. But that's just the beginning, because Jupiter is not just massive, it is dominant. Because its gravity is so strong that it influences everything around it, shaping the structure of the solar system itself, affecting the orbits of other planets, capturing asteroids, deflecting comets, acting almost like a shield or sometimes a threat, because Jupiter doesn't just protect, it also disrupts. Because its gravitational pull can send objects inward, toward the inner solar system, potentially toward Earth, meaning that Jupiter is not just a guardian. It is also a source of chaos. And this dual role makes it one of the most important objects in our solar system. Because without Jupiter, everything would be different. The structure of the solar system, the frequency of impacts, even the stability of Earth's orbit, all influenced by this one planet. But when you look at Jupiter, when you see its massive size, its swirling clouds, its iconic Great Red Spot, it is easy to forget just how extreme it really is. Because Jupiter is not a place you can stand on. It has no solid surface, no ground, no land, just layers of gas that become denser and denser as you go deeper, transitioning into states of matter that do not exist naturally on Earth, creating an environment that is not just hostile, but incomprehensible, because Jupiter is not a world, it is a system. A massive, dynamic, violent system of storms, pressure, and energy, operating on a scale that goes far beyond anything we experience on Earth. And yet, it is right there, in our solar system, orbiting the Sun, shaping everything around it, a planet that almost became a star, and still behaves like something much bigger than a planet ever should. And that raises a question, because if Jupiter is this massive, this powerful, this close to becoming something else, then what is really happening inside it? If you were able to descend into Jupiter, if you could somehow survive the journey, what you would experience would not resemble anything we know from Earth, because Jupiter does not have a surface in the way we understand it. There is no point where you arrive, no solid ground, no clear boundary between sky and land. Instead, Jupiter is a gradual descent, a transition, from one extreme to another. Because at the very top you would first encounter clouds, vast layers of swirling gases, mostly hydrogen and helium, mixed with trace compounds that give Jupiter its colors, ammonia, methane, water vapor, creating bands of white, orange, red, and brown that wrap around the entire planet. And these clouds are not calm. They are moving, fast, driven by powerful winds that can reach speeds of over 600 kilometers per hour, forming massive storms, jet streams, and turbulent systems that stretch across thousands of kilometers, creating a constantly shifting atmosphere that never truly settles. But as you descend deeper, things begin to change because the pressure increases, slowly at first, then more rapidly. Because unlike Earth, where the atmosphere transitions into solid ground, Jupiter's atmosphere just keeps going, becoming denser, thicker, heavier, until the gas begins to behave differently. Because under enough pressure, gas becomes liquid, and this is where Jupiter becomes truly alien. Because at a certain depth, the hydrogen that makes up most of the planet transitions into a liquid state, not like water, not like any liquid we are familiar with, but something else entirely, a dense, compressed fluid that exists under conditions far beyond anything we can recreate easily on Earth. And as you go deeper still, the pressure continues to rise, millions of times greater than Earth's surface pressure, crushing, relentless, until something even stranger happens. Because hydrogen, under extreme pressure, begins to change its properties, becoming what is known as metallic hydrogen, a state where hydrogen behaves like a metal, conducting electricity, carrying currents, creating effects that are not just unusual, but fundamental to how Jupiter works. Because this layer of metallic hydrogen is what generates Jupiter's magnetic field, one of the strongest in the entire solar system, created by the movement of this conductive material deep within the planet, producing an invisible force that extends far into space, shaping the environment around Jupiter. But even deeper, we are no longer certain, because beyond this layer there may be a core, a region made of heavier elements, possibly rocky, possibly partially dissolved, possibly something that does not resemble a solid core in the way we imagine it, but rather a diffuse, mixed region where the boundaries between materials are not clearly defined. And this uncertainty is important because it shows that even though we have studied Jupiter for decades, even though we have sent spacecraft, collected data, and built models, there are still things we do not fully understand. Because Jupiter is not just large, it is complex, a system of layers, transitions, and extreme conditions that challenge our understanding of physics, of matter, of how planets behave under pressure and energy far beyond what we experience on Earth. And this makes Jupiter more than just a giant planet. It makes it a laboratory, a place where the rules we know are pushed to their limits, where matter behaves differently, where familiar concepts no longer apply in the same way. Because Jupiter is not just bigger than Earth. It is different, fundamentally. A world where there is no surface, no clear boundary, no simple structure, just layers of increasing intensity, leading deeper and deeper into conditions that are almost impossible to imagine. And that leads to a final thought. Because if we cannot even fully understand what is happening inside Jupiter, then what else about this planet are we still missing? If there is one feature on Jupiter that stands out more than anything else, one structure that has captured attention for centuries, it is the Great Red Spot, a storm. But calling it a storm almost feels like an understatement, because this is not a storm like the ones we experience on Earth. It is something far larger, far more powerful, and far more persistent. Because the Great Red Spot is a massive, rotating system of clouds, an anticyclonic storm that has been raging for at least 300 years, possibly even longer, first observed in the 17th century and still active today, making it one of the longest-lasting storms ever recorded in the solar system. And its size is difficult to fully understand. Because at its largest, it was wide enough to swallow Earth whole, a structure so vast that our entire planet could fit inside it. A storm operating on a scale that goes beyond anything we can directly compare to. But even today, as it slowly shrinks over time, it remains enormous, a swirling vortex of clouds moving in a counterclockwise rotation, with wind speeds exceeding 400 kilometers per hour, creating a system that is both stable and violent at the same time. And that combination is what makes it so fascinating, because storms, by their nature, are temporary. They form, they evolve, they dissipate, but the Great Red Spot does not follow that pattern. It persists. Because Jupiter's atmosphere provides the conditions needed to sustain it, continuous energy from internal heat, combined with the planet's rapid rotation, creates a system where storms can feed on surrounding flows, maintaining their structure for extended periods of time. And the Great Red Spot is not alone. Because Jupiter is covered in storms, smaller vortices, massive bands of turbulence, jet streams that move in opposite directions, creating shear zones where energy builds and releases, forming new storms, merging old ones, constantly reshaping the atmosphere. And this creates a world that is never still, because on Jupiter there is no calm surface, no stable ground, only motion, continuous, relentless, because the atmosphere is not just moving. It is alive in a dynamic sense, a system of energy transfer, rotation, and pressure differences that create patterns we can observe, but not fully predict. And what makes this even more extreme is the speed. Because Jupiter rotates incredibly fast, completing a full rotation in just under 10 hours, meaning that its atmosphere is constantly being twisted, stretched, and accelerated, contributing to the formation of its distinct bands and powerful storms. And this rapid rotation amplifies everything, because it creates forces that shape the atmosphere into organized structures, long bands of clouds that wrap around the planet, separated by jet streams that define regions of different movement, different composition, different energy levels. And within these bands, the storms form, grow, collide, merge, and sometimes disappear. But the great red spot remains, a constant, a reminder of just how powerful Jupiter's atmosphere really is, because this is not just a weather system. It is a demonstration of energy, of scale, of what happens when a planet is large enough, fast enough, and dynamic enough to sustain processes that on Earth would be impossible. And when we look at it, when we observe this massive storm continuing year after year, century after century, it raises a question. Because if something like this can exist for so long, what else on Jupiter has been happening for just as long, without us even realizing it? If you think Jupiter is dangerous because of its size, its storms, or its pressure, then there is something even more extreme that you cannot see, something that makes this planet one of the most hostile environments in the entire solar system: radiation. Because Jupiter does not just have a magnetic field, it has one of the strongest magnetic fields of any planet we know. A field so powerful that it traps charged particles, accelerating them to incredibly high energies, creating intense radiation belts that surround the planet like an invisible shield. But this is not a protective shield. It is a trap. Because these particles, electrons, protons, ions, are captured by Jupiter's magnetic field and forced to move along its lines, spiraling, accelerating, colliding, building up energy levels that are far beyond what we experience around Earth. And the result is lethal. Because the radiation near Jupiter is so intense that it can destroy electronics, damage materials, and would be fatal to humans in a very short amount of time, delivering doses that exceed safe limits within minutes or even seconds, depending on the region. And this creates a zone around Jupiter that is almost impossible to enter safely. Because any spacecraft that travels close to the planet must be carefully designed, shielded, and operated in ways that minimize exposure, following precise trajectories to avoid the most intense regions, because staying too long in the wrong place can mean the end of the mission. And even with all of our technology, we struggle. Because missions like Juno, which currently studies Jupiter, have to endure these conditions, passing through regions of high radiation, collecting data quickly, and then moving away again, limiting exposure to survive as long as possible. And this radiation is not just a local effect. Because Jupiter's magnetic field extends far into space, influencing its moons, especially Io, Europa, and others, creating environments where radiation levels are still high, affecting surfaces, chemistry, and the potential for life. And this is where things become even more complex. Because while Jupiter itself is completely uninhabitable, its moons exist within this system, protected in some ways, exposed in others, creating a balance between shielding and danger that shapes their environments in unique ways. But focusing on Jupiter itself, the message is clear. This is not a place for life, not in any form we understand, because between the radiation, the pressure, the lack of a surface, and the extreme conditions, Jupiter is not just hostile, it is overwhelming, a planet that does not just challenge survival, it prevents it entirely, and yet, this is part of what makes it so important, because Jupiter is not just a dangerous world, it is a key part of the solar system. A planet whose gravity shapes orbits, whose presence affects the distribution of objects, whose influence extends far beyond its own atmosphere. And this creates a contrast, because Jupiter is both destructive and protective, a source of radiation and chaos, and a stabilizing force for the system as a whole. And that duality makes it unique, because Jupiter is not just a planet, it is a force, one that defines the environment around it, one that cannot be ignored, and one that reminds us that not every world is meant to be explored up close, because some places are simply too extreme. If Jupiter itself is too extreme, too violent, too hostile for anything to survive, then you might think the story ends there, that this giant planet is simply a massive, dangerous object with nothing more to offer. But that's not true, because around Jupiter, there are worlds, dozens of them, moons of all sizes, shapes, and environments orbiting within its massive gravitational field, each one shaped by Jupiter's influence, each one carrying its own story. And some of these moons are not just interesting, they are extraordinary. Because among Jupiter's many moons, there are four that stand out above all others. The Galilean moons discovered by Galileo Galilei in 1610, the first objects ever observed orbiting another planet, proving that not everything revolves around Earth, changing our understanding of the universe forever. These moons are Io, Europa, Ganymede, and Callisto, and each one is completely different. Because Io is the most volcanically active world in the entire solar system, covered in hundreds of volcanoes, constantly erupting, reshaping its surface, driven by tidal forces caused by Jupiter's immense gravity, stretching and compressing the moon, generating heat from within. A world that is constantly changing, constantly active, constantly violent. But then there is Europa. And Europa is something else entirely, because beneath its icy surface, there is an ocean, a vast global ocean of liquid water hidden beneath a thick layer of ice, kept warm not by sunlight but by internal heating, again caused by Jupiter's gravitational pull, creating a system where water remains liquid despite being so far from the sun. And this ocean is not small. It may contain more water than all of Earth's oceans combined. Hidden, dark, protected. And that changes everything, because where there is liquid water, there is always a possibility. Because on Earth, wherever we find water, we find life. And Europa has water, energy, chemistry, the key ingredients that in theory could support life, even if that life is not like anything we know. And this makes Europa one of the most important places in the search for life beyond Earth. A world that is not exposed, not obvious, but hidden beneath ice, waiting to be explored. But Europa is not alone, because Ganymede, the largest moon in the solar system, even larger than the planet Mercury, has its own magnetic field, its own internal structure, its own complex system that we are still trying to understand. And Callisto, heavily cratered, ancient, a record of impacts and time, showing us what a surface looks like when it remains largely unchanged for billions of years. And together, these moons create something incredible, because while Jupiter itself is uninhabitable, the system around it may not be, because life does not have to exist on planets. It can exist on moons, hidden beneath surfaces, protected from extreme conditions, existing in environments that are very different from Earth but still capable of supporting complex processes. And this is what makes Jupiter so important, because it is not just a planet, it is a system. A collection of worlds, each one offering something different, each one expanding our understanding of where life might exist, how environments can form, and how planetary systems can create unexpected possibilities. Because Jupiter may be too extreme for life itself, but around it, there may be places where life could still exist, hidden, protected, waiting. If there is one place in Jupiter's system that changes everything we think we know about life, it is not Jupiter itself, but a small, icy moon orbiting within its gravity. Europa. Because at first glance, Europa does not look like a place where anything could exist. Its surface is covered in ice, smooth, cracked, and frozen, reflecting sunlight in a cold, distant way, giving no immediate sign that anything unusual lies beneath. But beneath that ice, there is something else, an ocean, not a lake, not a small pocket of water, but a global ocean stretching across the entire moon, hidden beneath a thick shell of ice, completely isolated from the surface, existing in total darkness. And this ocean is deep, possibly deeper than any ocean on Earth, containing more water than all of Earth's oceans combined. A vast, hidden environment that we cannot see directly, but know is there based on gravitational measurements, magnetic field interactions, and surface observations. And what makes this ocean even more interesting is how it stays liquid. Because Europa is far from the sun, too far for sunlight to provide enough heat, and yet the water remains unfrozen, because the heat comes from within, from Jupiter. Because Europa is constantly being stretched and compressed by Jupiter's immense gravity, a process known as tidal heating, where the moon's interior is flexed, generating heat, preventing the ocean from freezing, creating a system where energy is continuously supplied. And where there is energy, there is potential, because life does not need sunlight. On Earth, we have found ecosystems deep in the ocean, near hydrothermal vents, where organisms survive without any connection to sunlight, relying instead on chemical energy, using heat and minerals from the planet's interior to sustain life. And if similar conditions exist on Europa, then the possibility becomes real, because Europa has water, it has energy, it has the chemical building blocks, the same ingredients that allowed life to emerge on Earth. But there is something different because Europa's ocean is completely sealed off. No light, no direct connection to the surface, a world that exists in permanent darkness. And that changes how we imagine life there. Because if life exists on Europa, it would not look like life on Earth's surface. It would not depend on sunlight. It would not resemble forests, oceans, or ecosystems we are familiar with. It would be something else, something adapted to darkness, to pressure, to isolation. And that makes it harder to imagine, harder to understand, because it would not just be life somewhere else. It would be life in a completely different kind of environment. And this creates a different kind of mystery, because Europa is not just a place we want to explore. It is a place where the answer could be hidden beneath kilometers of ice, beyond our current reach, in a world we cannot yet access directly. And that means that everything we know about it is indirect, inferred, suggested, but not confirmed. And yet, the possibility remains that beneath that frozen surface, in the dark, in the pressure, there is something moving, something existing, something alive. And if that is true, then the universe may be very different from what we thought, because it would mean that life does not need a planet like Earth. It can exist in places we once ignored, hidden, beneath ice, far from the sun, waiting. If Europa represents quiet mystery, hidden oceans, and the possibility of life in darkness, then Io represents the complete opposite: chaos, fire, constant destruction. Because Io is not just another moon. It is the most volcanically active world in the entire solar system. And nothing about it is calm. Because unlike Earth, where volcanic eruptions are relatively rare and localized, on Io they are everywhere, hundreds of volcanoes spread across its surface, many of them erupting continuously, throwing massive plumes of sulfur and lava hundreds of kilometers into space, reshaping the landscape over and over again. And this is not random, because Io is caught in a gravitational battle, pulled by Jupiter, pulled by other moons, stretched, compressed, again and again. Because every time Io moves through its orbit, Jupiter's immense gravity deforms it, literally bending the moon, generating internal friction, creating heat from within, a process so intense that it melts rock, fuels volcanic activity, and prevents the surface from ever becoming stable. And this creates a world that is constantly renewing itself, but not in a peaceful way, because Io has no time to settle, no time to cool, no time to become still, because the surface is continuously covered by fresh lava, burying older layers, erasing impact craters, making Io one of the youngest surfaces in the solar system in terms of geological age. A world where the past does not stay visible for long, because it is constantly replaced. But what makes Io even more extreme is its composition, because the surface is not just rock. It is covered in sulfur compounds, giving it a yellow, orange, and red appearance, a world that looks almost unreal, as if it does not belong in the same system as the other moons. And the eruptions are not like Earth's. Because the lack of a thick atmosphere means that the plumes expand differently, spreading into space, creating massive arcs of material that fall back onto the surface, coating it, reshaping it, adding to the cycle of constant change. And this creates an environment that is completely uninhabitable, not just difficult, but impossible, because the temperatures, the eruptions, the lack of stability all combine into a system that does not allow anything to survive. And yet, it is one of the most dynamic places we know. Because while Earth is active and Mars once was, Io is active in a way that goes beyond both. It is not just a planet or a moon that changes. It is a world that never stops changing. And this makes Io important, because it shows us what happens when gravitational forces are pushed to their limits, when energy is constantly injected into a system, when a world is not allowed to stabilize. Because Io is not just volcanic, it is continuously volcanic, a state that most worlds do not reach. And this creates a contrast within Jupiter's system, because around the same planet you have Europa, calm on the surface, hiding a deep ocean, and Io, violently active, reshaping itself constantly. Two worlds, opposites, both influenced by the same source, Jupiter. And that is what makes this system so fascinating, because it is not uniform, it is not predictable, it is a collection of extremes, each moon responding differently to the same gravitational force, each one telling a different story. And Io's story is one of constant fire, constant motion, constant destruction, a world that never rests. After the chaos of Io, after the hidden mystery of Europa, Jupiter's system shifts again, becoming quieter, colder, and in some ways even more mysterious, because not all worlds around Jupiter are violent or active. Some are silent, ancient, unchanged. And among them two stand out, Ganymede and Callisto, because Ganymede is not just another moon. It is the largest moon in the entire solar system, even larger than the planet Mercury, a world so massive that it could almost be considered a planet on its own, and yet it remains bound to Jupiter, orbiting within its powerful gravitational field. But what makes Ganymede truly unique is not just its size. It is what lies within it. Because Ganymede has its own magnetic field, the only moon in the solar system known to have one, which means that, unlike other moons, Ganymede generates its own internal protection, creating a miniature magnetosphere within Jupiter's much larger one, a rare and complex interaction between two magnetic systems overlapping in space. And beneath its surface, there may also be water, not a single ocean like Europa, but possibly multiple layers of water and ice stacked beneath the surface, separated by different pressure conditions, creating a structure that is far more complex than we once imagined. A world that is not just frozen, but layered, dynamic in ways we are still trying to understand. But then there is Callisto, and Callisto feels different. Because where Ganymede shows signs of internal activity, of structure, of change, Callisto appears almost frozen in time. Because its surface is one of the oldest in the solar system, covered in craters, thousands upon thousands of them, overlapping, stacking, recording billions of years of impacts, a surface that has not been significantly reshaped, not renewed, not erased. A world that has simply remained, unchanged. Because Callisto lacks the internal heating that drives activity on other moons, meaning that it has not experienced the same level of geological transformation, leaving it as a record of the past, a snapshot of what surfaces can look like when they are not constantly reshaped. And this makes it valuable, because Callisto shows us something rare: stability. Not in the sense of balance, but in the sense of inactivity. A world where processes have slowed down to the point where time becomes visible, where history is not erased but preserved. And this creates a contrast within Jupiter's system. Because around one planet you have Io, constantly erupting, Europa, hiding an ocean, Ganymede, structured and complex, and Callisto, ancient and still. 4 worlds, each one different, each one shaped by Jupiter. And this is what makes Jupiter more than just a planet, because it is not alone. It is surrounded by a system that reflects its influence in different ways, creating environments that range from extreme activity to complete stillness. And in that sense, Jupiter is not just a giant, it is a center, a force that shapes not just itself, but everything around it. For a long time, Jupiter has been described as Earth's protector, a massive gravitational shield that deflects comets and asteroids, preventing them from reaching the inner solar system, reducing the number of impacts that could threaten life on Earth. And in many ways, that is true, because Jupiter's gravity is enormous, so strong that it can capture objects, alter their trajectories, and pull them away from paths that might otherwise bring them closer to Earth, acting like a barrier, a gatekeeper at the edge of the inner solar system. But the story is not that simple, because Jupiter does not just remove threats. It can also create them, because gravity does not only pull objects away, it can also redirect them. Because when asteroids and comets pass near Jupiter, they do not always get captured or pushed outward. Sometimes they are sent inward, toward the inner planets, toward Earth. And this creates a dual role, because Jupiter is not just a shield, it is also a slingshot. A system that can accelerate objects, change their orbits, and send them into new paths that may cross the inner solar system in ways they would not have otherwise. And this means that Jupiter is both protective and dangerous, because without Jupiter, some objects might never reach Earth. But with Jupiter, others are given the energy needed to move inward, increasing the complexity of the system, making it impossible to define Jupiter as purely one or the other. And we have seen this effect before. Because in 1994, a comet known as Comet Shoemaker, Levy 9 collided with Jupiter, breaking apart and crashing into its atmosphere in a series of impacts that released enormous amounts of energy, leaving visible scars on the planet, dark marks that were larger than Earth itself. And this event showed us something important, because it demonstrated Jupiter's role as a collector, a planet that absorbs impacts, a planet that takes the hit. But it also showed us the scale of what is moving through the solar system, because if Jupiter had not been there, those fragments might have continued on different paths, and some of those paths could have crossed Earth, and this is where the uncertainty comes in. Because we do not fully know whether Jupiter reduces the number of impacts on Earth overall, or whether it sometimes increases them, depending on how objects interact with its gravity. Because the system is complex, dynamic, unpredictable over long timescales. And that makes Jupiter something more than just a protector. It makes it a force, one that shapes the movement of objects across the solar system, influencing trajectories, creating pathways, altering outcomes in ways that are not always obvious. And this changes how we see it, because Jupiter is not simply good or bad. It is not a guardian in the traditional sense. It is a massive gravitational presence that affects everything around it, sometimes in ways that benefit Earth, sometimes in ways that create new risks. And that duality makes it powerful, because Jupiter does not choose, it does not protect intentionally, it does not threaten intentionally, it simply exists, and in doing so, it shapes the solar system, and that includes us. To truly understand Jupiter, you have to go back to the very beginning, not just to when the planet formed, but to when the entire solar system was still taking shape, a chaotic disk of gas, dust, and debris surrounding a young sun. Because Jupiter did not just form within this system, it helped shape it. Because early in the solar system's history, Jupiter began to grow rapidly, accumulating gas and material from the surrounding disk, becoming massive very quickly, far faster than the smaller rocky planets closer to the Sun. And that early growth changed everything. Because as Jupiter increased in mass, its gravity began to influence the entire disk, pulling material toward it, scattering other parts outward, and creating regions where planet formation was disrupted. And this is one of the reasons why the inner solar system looks the way it does today. Because without Jupiter's influence, more material might have remained closer to the Sun, potentially forming larger planets, changing the structure of the system completely. But Jupiter did not just stay in one place, because some models suggest that early in its history, Jupiter may have migrated inward, moving closer to the Sun before eventually shifting back outward to its current position, a process that would have dramatically reshaped the distribution of material in the solar system. A movement that could have scattered planetesimals, disrupted forming planets, and influenced the final arrangement of worlds we see today. And this idea, often referred to as the Grand Tack hypothesis, suggests that Jupiter's motion played a direct role in shaping the size and position of planets like Mars, which is smaller than expected, possibly because Jupiter's movement limited the material available for it to grow. And this means that Jupiter is not just a part of the solar system. It is one of the reasons the solar system exists in its current form, because its gravity, its movement, and its early formation influenced the distribution of material, the formation of planets, and the long-term stability of the system. And this influence continues today, because Jupiter still affects the orbits of asteroids in the asteroid belt, creating gaps known as Kirkwood gaps, regions where objects are removed or prevented from forming stable orbits due to gravitational interactions. And this shows that Jupiter is not just a relic of the past. It is still active in shaping the system, still influencing the movement of objects, still playing a role in the structure of the solar system as we know it. And this gives Jupiter a different identity. Because it is not just the largest planet, it is an architect, a force that helped design the layout of the solar system, not intentionally, but through its presence, its gravity, and its interactions with the surrounding material. And that changes how we see everything. Because when we look at Earth, when we look at Mars, when we look at the asteroid belt, we are not just seeing independent objects. We are seeing the result of a system that was shaped, in part, by Jupiter. A system where one planet had enough influence to alter the path of everything around it. And that raises a final thought. Because if Jupiter had formed differently, if it had grown larger, or smaller, or in a different position, then the solar system we know today might not exist at all. When we look at Jupiter, it feels permanent, massive, unchanging, a giant that has existed for billions of years and will continue to exist far into the future. But even Jupiter is not eternal, because like everything in the universe, it is part of a timeline, a system that evolves, changes, and eventually reaches a different state. But Jupiter's future is not about sudden transformation. It is about slow change, because over time, Jupiter is cooling, very slowly. Because when it formed, it retained a significant amount of heat, energy left over from its formation, trapped within its massive structure. And even today, Jupiter radiates more heat than it receives from the Sun, meaning that it is still releasing that internal energy into space. But that energy is finite, and over billions of years it will continue to decrease. The planet will cool, gradually. Its internal processes will slow. Its structure will become more stable, less dynamic. But the changes will be subtle. Because Jupiter is so large that it takes immense amounts of time for anything significant to happen, meaning that on human timescales, it appears almost unchanged. But if we extend the timeline far enough, things become more interesting, because in the distant future the Sun itself will change, expanding into a red giant, growing larger, brighter, altering the conditions of the entire solar system. And while the inner planets may be destroyed or heavily altered, Jupiter will remain, but it will not be unaffected, because the increased radiation and heat from the expanding Sun will change Jupiter's outer layers, affecting its atmosphere, its temperature, and possibly even the dynamics of its storms. But even beyond that, there is an even longer timeline. Because after the Sun eventually loses its outer layers and becomes a white dwarf, the solar system will enter a much quieter phase, a colder, darker environment where Jupiter will continue to orbit, but under very different conditions. A dim star, a distant system, a planet that still exists, but in a universe that feels completely different from what we know today, and over even longer timescales. Jupiter will continue to evolve, its heat fading, its activity slowing, its storms potentially weakening as internal energy decreases, though this process would take trillions of years, far beyond anything we can directly observe. But there is also something else. Because Jupiter's gravity will continue to influence the solar system long after Earth is gone, long after the inner planets have changed, long after the conditions that support life here have disappeared. Because Jupiter will remain, a massive object orbiting a dying star, a remnant of a system that once supported life. And this gives Jupiter a different role, because it is not just part of the present. It is part of the future, a constant in a system that will change dramatically around it. And that changes how we see it, because Jupiter is not just a giant planet. It is one of the longest-lasting structures in our solar system, a world that will outlive most of what we know, a planet that will continue to exist long after everything else has changed. And that makes it something more than just another world. It makes it a witness to the past, to the present, and to a future we will never see. When you think about Jupiter, it is easy to focus on its size, its storms, its gravity, the physical aspects that make it so extreme. But there is something else about Jupiter that goes beyond its structure, something that changes how we think about planets, about systems, and even about our place in the universe, because Jupiter represents scale. A scale that is difficult to fully understand, because on Earth, everything we experience is limited, distances, sizes, forces, all within a range that our minds can process. But Jupiter exists outside of that range. A world so large, so massive, that it forces us to think differently. Because it is not just bigger, it is overwhelmingly bigger. And that creates a shift in perspective. Because when we compare Earth to Jupiter, the difference is not just numerical. It is conceptual, because Earth feels like a complete world, self-contained, balanced, but Jupiter feels like something else, a system that is not meant to be lived on, not meant to be experienced directly, but meant to exist as part of a larger structure, because Jupiter is not about habitability, it is about influence. Because its presence affects everything around it, shaping orbits, controlling movement, interacting with other bodies, acting as a central force within the solar system. And this makes it different from the planets we relate to. Because Jupiter is not a place we imagine standing on. It is a place we observe, a force we study, a system we try to understand, and that changes how we see planets in general, because not all planets are worlds in the way we think of Earth. Some are environments, systems, structures that play roles beyond being places where life can exist, and Jupiter is one of those. But there is also something else, because Jupiter shows us that not everything in the universe is designed for us. Not everything is accessible. Not everything is meant to be explored in the way we explore Earth or even Mars, because some places are simply too extreme, too vast, too powerful, and that is part of what makes the universe what it is, because it is not centered around life. It is not built for us. It is a system that exists on its own terms, with structures and processes that go far beyond what we need or expect. And Jupiter is a perfect example of that, because it exists as it is, massive, dynamic, uninhabitable, and yet essential. Because without Jupiter, the solar system would not be the same, and that creates a kind of balance. Because while Jupiter is not a place for life, it may be one of the reasons life exists elsewhere in the system, because its gravity shapes orbits, its presence stabilizes regions, its influence extends far beyond itself. And that means that Jupiter, in a way, contributes to the conditions that allow Earth to exist as it does, even if indirectly. And that makes it important, not because we can go there, not because we can live there, but because it plays a role in a system that includes us. And this is where the perspective shifts again, because Jupiter is not just a planet we observe. It is part of the reason we are here. A massive, distant world that has influenced the structure of the solar system in ways that have allowed Earth to remain stable, to support life, to continue evolving. And that connection, even if indirect, even if distant, makes Jupiter feel less like something separate and more like something connected, because in a system as complex as the solar system, everything is connected, and Jupiter is one of the strongest connections of all. Imagine for a moment that you are falling toward Jupiter, not observing it from a distance, not studying it through data or images, but actually descending into it. Because unlike Earth, there is no surface waiting for you, no ground, no moment where you land, only layers, endless layers. Because as you approach Jupiter, the first thing you would see is its immense size, filling your entire field of view, growing larger and larger, its bands of color becoming more defined, its storms more visible, the great red spot appearing not as a feature but as a massive structure in motion. And then you enter the atmosphere, but there is no clear entry point, no boundary, just a gradual transition from space into gas. Because the outer layers of Jupiter are already part of its atmosphere, meaning that you would begin to feel resistance, pressure, movement without ever crossing a defined line. And at first, it might not seem so extreme. Clouds, winds, movement. But as you descend deeper, everything intensifies because the pressure increases, the temperature rises, the winds become stronger, more chaotic, because you are entering a system that is not stable, a system that is constantly moving, constantly shifting with currents flowing in different directions, creating turbulence that is far beyond anything we experience on Earth. And there is no escape, because once you are in, you cannot leave, because there is no solid surface to stand on, no place to stop, only deeper layers and deeper conditions. Because as you go further, the clouds become thicker, darker, the light from the sun fades, replaced by a dim, scattered glow, until eventually you are surrounded by darkness. Because the deeper you go, the less light can penetrate, and the environment becomes something else entirely. Because the pressure continues to rise, crushing, relentless, until the gas around you begins to behave like a liquid, dense, heavy, surrounding you from all directions, removing any sense of direction, any sense of up or down. Because in Jupiter, those concepts lose meaning because there is no surface, no reference point, only depth, and as you descend even further, the pressure becomes unimaginable, millions of times greater than Earth's surface pressure, enough to destroy any known structure, any known material, any known form of life, because Jupiter is not a place you can survive. It is a place that overwhelms everything, and beyond that, it becomes even more unknown. Because eventually, you would reach the region of metallic hydrogen, a state of matter that does not exist naturally on Earth, where the environment is so extreme that our understanding becomes limited, where physics behaves in ways that are difficult to fully grasp. And beyond that, we are no longer certain, because we do not know exactly what lies at the center, a core, a mixed region, something that does not fit neatly into our models. And this uncertainty is part of what makes Jupiter so fascinating, because even in this imagined descent, there are limits to what we can understand, because Jupiter is not just extreme, it is beyond experience, a place where the conditions go beyond what we can survive, beyond what we can fully imagine, beyond what we can directly observe. And that is what makes it different from planets like Earth or Mars, because those are worlds we can picture ourselves on. But Jupiter is a world we can only fall into and never return from. When you look at Jupiter, really look at it, not just as an image, not just as a planet in the sky, but as an object that actually exists, something so massive that it dominates everything around it, something so large that Earth could fit inside it more than 1,000 times, something so powerful that its gravity shapes the structure of the solar system. Something begins to shift. because it changes your sense of scale. Because on Earth everything feels significant, distances feel large, mountains feel massive, oceans feel endless, but Jupiter makes all of that feel small. Because compared to Jupiter, Earth is not large. It is tiny. A small, fragile world orbiting a star, existing within a system that includes objects so much larger that they redefine what size even means. And this creates a kind of perspective, because it reminds us that what feels big to us is not big in the universe, because Jupiter is not even the largest type of planet. There are planets far larger than Jupiter, gas giants and superjupiters orbiting other stars, objects that make Jupiter itself seem small in comparison, meaning that even something as massive as Jupiter is just one example of a much larger category. And that realization goes even further, because Jupiter orbits the Sun. And the Sun itself is just one star among hundreds of billions in our galaxy. And our galaxy is just one among billions of galaxies in the universe. And suddenly, the scale becomes overwhelming, because everything we know, everything we experience, everything we consider important exists within a system that is incredibly small compared to the whole. And this can feel unsettling, because it makes us feel insignificant. Because when you compare yourself, your life, your planet to something like Jupiter, and then to the scale beyond that, it becomes clear that we are not at the center of anything. We are part of something much larger. Something that does not revolve around us. But there is another way to look at it, because while Jupiter makes us feel small, it also makes us aware, because we are capable of understanding it, of observing it, of studying it, of building models that explain how it works, even if not perfectly. And that is something unique, because while we are small physically, we are not small in terms of awareness, because we can look at something like Jupiter, something so massive, so distant, so extreme, and still begin to understand it. And that creates a balance, because yes, we are small, but we are also capable of exploring, capable of learning, capable of reaching beyond our immediate environment and trying to understand the universe we are part of. And Jupiter becomes a symbol of that, because it represents both extremes. It shows us how small we are, and at the same time, it shows us how far we can reach. Because despite the distance, despite the scale, despite the complexity, we are still able to study it, to send missions, to collect data, to turn something that once seemed unreachable into something we can begin to understand. And that is what makes this perspective powerful, because it is not just about size. It is about contrast between what we are physically and what we are capable of understanding. And Jupiter sits right in the middle of that contrast, a reminder that the universe is vast, but not completely beyond our reach. For all that we have learned about Jupiter, for all the missions, the data, the models, and the observations, there is something important that is easy to overlook. We still don't fully understand it. Because despite decades of study, despite spacecraft like Pioneer, Voyager, Galileo, and Juno, Jupiter remains a planet filled with unknowns, a system so complex that every answer seems to lead to new questions. Because we know what Jupiter looks like. We know its size, its composition, its storms, but knowing what something looks like is not the same as fully understanding how it works, Because even something as iconic as the Great Red Spot is still not completely understood. We know it has existed for centuries. We know it is a massive storm, but we do not fully understand why it has lasted so long, why it has not dissipated, or what exactly maintains its structure over such long periods. And then there is the interior. Because while we have models of Jupiter's internal structure, layers of gas, liquid hydrogen, metallic hydrogen, and possibly a core, we are still not certain about the details. Is the core solid? Is it partially dissolved? Does it even exist in the way we imagine it? Or is Jupiter more mixed, more fluid, more complex than our models suggest? And these are not small questions. Because the structure of Jupiter affects everything else, its magnetic field, its heat distribution, its long-term evolution. And speaking of the magnetic field, that is another mystery. Because Jupiter's magnetic field is incredibly strong, far stronger than Earth's, but its exact structure, its variations, and how it interacts with the planet's interior are still being studied, still being mapped, still not completely understood. And then there are the storms. Because while we can observe them, track them, measure their speeds, we still do not fully understand how energy moves through Jupiter's atmosphere, how storms form, merge, and persist, or why certain structures appear stable while others disappear. And this complexity is not a limitation of observation. It is a limitation of understanding. Because Jupiter operates under conditions that are difficult to recreate, extreme pressures, extreme temperatures, extreme dynamics, making it challenging to test theories directly, forcing us to rely on models, simulations, and indirect measurements. And this means that Jupiter is not just a planet we study. It is a planet that challenges us. Because it pushes the limits of what we can understand, forcing us to refine our models, question our assumptions, and accept that there are still things we do not know. And that is what makes it exciting. Because science is not just about answers. It is about questions. And Jupiter provides many of them. Because every time we learn something new, every time we collect more data, every time we refine our understanding, we also discover how much more there is to learn. And this creates a sense of openness, because Jupiter is not a solved problem. It is an ongoing exploration, a system that continues to reveal new details, new complexities, new challenges. And that means that even in the future, even with more advanced technology, more missions, more data, Jupiter will likely remain a source of mystery. Because some systems are so large, so complex, that they are never fully understood, only better understood. And Jupiter is one of them, a planet that we can observe, we can measure, we can model, but may never completely explain. And that is what keeps us looking. Because somewhere in those clouds, in those storms, in those layers we cannot reach, there are still answers we have not found. There is something strange about Jupiter, because the more dangerous it becomes, the more fascinating it feels. Because this is not a planet that invites you. It does not offer a surface to walk on. It does not offer conditions you can survive. It does not offer anything that resembles comfort, safety, or familiarity. And yet, we keep looking at it because Jupiter represents something extreme, something that exists beyond the limits of our world, a place where everything is amplified, size, gravity, storms, radiation, all pushed far beyond what we experience on Earth. And that creates a kind of attraction, because humans are drawn to extremes, to the largest, the fastest, the most powerful. And Jupiter is all of those at once, because it is not just big. It is overwhelmingly big, not just violent, but continuously violent, not just dangerous, but completely uninhabitable. And that makes it different, because planets like Earth or Mars feel reachable, understandable, places where we can imagine ourselves. But Jupiter does not allow that. It forces us to observe from a distance, to accept that some places are not meant to be experienced directly, and that creates a different kind of fascination, because it is not about being there. It is about understanding something that we cannot experience, because Jupiter exists in a category of its own, a world where the rules are the same. But the scale changes everything, because gravity is stronger, pressure is higher, energy is greater, and those differences create environments that are not just difficult, but impossible for us. And yet, we study it, we send missions, we build instruments capable of surviving just long enough to collect data before being overwhelmed. We push our technology to its limits just to understand what is happening there. And that effort says something important, because it shows that curiosity does not stop at danger. It does not stop at difficulty. It does not stop at impossibility, because even when a place is completely hostile, we still want to know, we still want to understand. And Jupiter becomes a symbol of that, because it represents the boundary, the edge of what we can explore, a place where we cannot go, but can still learn from. And that makes it valuable, because it expands our understanding of what is possible, not for life, but for matter, for systems, for the universe itself. Because Jupiter shows us that the universe is not limited to environments like Earth. It is filled with extremes, with places that operate on scales and conditions that are far beyond what we experience. And by studying those places, we expand our understanding of reality, of what exists, of what is possible. And that is why we keep looking, because Jupiter is not just dangerous, it is important, a world that we will never stand on, but will never stop exploring. Imagine for a moment that Jupiter never existed, that when the solar system formed, something changed. The gas did not accumulate in the same way. The mass did not gather in one place, and instead of becoming the giant we know today, that region of space remained empty. At first, it might not seem like a big difference, because Jupiter is far away, distant, not something we interact with directly. But removing Jupiter would not just remove a planet, it would change everything, because Jupiter's gravity shapes the solar system, and without it, the structure we know today would not exist. Because the asteroid belt, the region between Mars and Jupiter, is not just a random collection of rocks. It is a result of Jupiter's influence. Because its gravity prevented that material from forming into a planet, constantly disturbing the region, keeping it fragmented, meaning that without Jupiter, that material might have come together, forming another planet, a completely different world between Mars and the outer solar system. And that alone would change the balance. But it goes further, because Jupiter also affects the movement of comets and asteroids, capturing some, redirecting others, creating a system where objects are constantly being influenced by its presence. Without Jupiter, those objects would follow different paths. Some might remain in the outer regions, others might move inward more frequently, and that could increase the number of impacts on Earth. Because while Jupiter sometimes sends objects inward, it also removes many from the system entirely. And without that effect, the inner planets might experience a very different history. More impacts, more collisions, more instability, and that could change everything. Because Earth's history is shaped by impacts, some of them beneficial, some of them destructive. And changing the frequency of those impacts could alter the conditions for life, delaying it, interrupting it, or even preventing it entirely. But there is also something else. Because Jupiter's gravity helps stabilize the orbits of the planets, creating a structure where the inner solar system remains relatively stable over long periods of time. Without Jupiter, that stability might be reduced. Orbits could shift more over time. Interactions between planets could become more significant, creating a system that is less predictable, less stable. And this means that Jupiter is not just an addition to the solar system. It is a defining feature, a factor that influences the entire structure. Because without it, the solar system might look completely different. Different planets, different orbits, different histories, and possibly no Earth as we know it. And this changes how we see Jupiter, because it is not just a giant planet in the distance. It is part of the reason the solar system exists in its current form. Part of the reason Earth has remained stable enough to support life. Part of the reason we are here. And that idea is powerful, because it means that something so distant, so extreme, so uninhabitable, is still connected to us, not directly, but fundamentally, because in a system as complex as the solar system, even the largest and most distant objects play a role in shaping everything else, and Jupiter's role is one of the biggest. Out there, far beyond Earth, beyond Mars, beyond the warmth of the inner solar system, Jupiter exists in a region where the sunlight is weaker, where the space between worlds becomes larger, quieter, more distant. And in that space, Jupiter dominates. Because even though it is far from the sun, it is still visible, still present. A massive sphere of swirling clouds and storms, reflecting what little light reaches it, glowing faintly in the darkness, a giant that does not need to shine to be seen. But what makes Jupiter feel different is not just its size. It is its isolation, because Jupiter is not surrounded by environments like Earth. There are no oceans, no continents, no life as we know it, just space, and a system of moons orbiting around it. And beyond that, emptiness. Because as you move further away from the sun, the distances between objects increase, the interactions become less frequent, the environment becomes quieter, and Jupiter exists at the edge of that transition between the inner solar system, where planets are closer together, and the outer regions, where everything begins to spread out. And that creates a different feeling, because Jupiter is not just large, it is alone in its scale. Because nothing else in the solar system comes close to it in size or influence, meaning that it exists in a category of its own, a giant among smaller worlds, a central force in a region where everything else feels secondary. And this gives it a kind of presence. Because when you imagine being near Jupiter, not on it, but near it, looking at it from space, seeing its immense size filling the sky, watching its storms move across its surface, knowing that beneath those clouds are layers of pressure and energy beyond anything you can experience. It creates a sense of distance, not just physical distance, but conceptual distance, because Jupiter does not feel like a place you can connect to in the same way as Earth or Mars. It feels like something separate, something that exists on a different level, and that separation creates a kind of loneliness, not for Jupiter itself, but for us, because it reminds us that not everything in the universe is accessible, not everything is relatable, not everything is within reach. Because Jupiter is there, visible, observable, but never truly reachable in the way we understand other worlds, and that creates a boundary, a limit, a point where exploration becomes observation, where curiosity meets reality, because we can study Jupiter, we can send missions, we can collect data, but we cannot stand on it, we cannot experience it directly. And that makes it different, because it is a world we will always observe from the outside. A giant that exists in the distance, shaping everything around it but remaining separate from direct experience. And yet, it is still part of our story, because even in its distance, even in its isolation, it is connected to the system we are part of, a massive presence in the darkness that we cannot ignore. After everything we have seen, the storms, the pressure, the radiation, the massive scale, the moons, the influence it has on the entire solar system, Jupiter begins to feel less like just another planet and more like something else entirely. A presence. Because Jupiter is not subtle, it does not hide, it does not blend in. It defines its region, shapes it, controls it in ways that are impossible to ignore, and that leaves an impression. Because when you think about the solar system, when you imagine its structure, its balance, its motion, Jupiter is always there, always part of the picture, always influencing what happens around it. And that makes it important, not because we can go there, not because we can live there, but because it plays a role that extends beyond itself. Because Jupiter is not just a world, it is a force that connects other worlds. Because its gravity shapes the asteroid belt, its presence affects the orbits of planets, its system of moons creates environments that may hold the potential for life. And that means that Jupiter is not isolated, it is integrated, part of a larger system where everything interacts, everything influences everything else, creating a structure that is stable enough to exist for billions of years. And this is where the perspective changes, because Jupiter is not just something we observe. It is something that has helped shape the conditions that allowed Earth to become what it is. Indirectly, quietly, but significantly. And that connection is easy to miss, because Jupiter is so different, so distant, so extreme, that it does not feel related to us, but it is, because without Jupiter, the solar system might not look the same, and Earth might not be what it is today, and that makes Jupiter part of our story, even if it does not feel like it, because sometimes the most important influences are the ones we do not experience directly, but are still there, shaping everything in the background, and Jupiter is one of those influences. A massive, distant world that has been part of the system since the beginning, a planet that has watched the solar system evolve, that has remained as everything else changed, that will continue to exist long after many of the things we know today are gone. And that gives it a kind of permanence, a sense that it is not just part of the present, but part of a much longer timeline. And when you think about it that way, Jupiter becomes more than just a planet. It becomes a constant in a system that is constantly changing. As we reach the end of our journey across Jupiter, something becomes clear that was not obvious at the beginning, something that only reveals itself when you step back and look at the entire picture, from the storms on its surface to the structure deep within, from its moons to its influence across the solar system. Jupiter is not just a planet, it is a system, a force, a presence that extends far beyond its own boundaries. Because everything about Jupiter is larger than expected, its size, its gravity, its storms, its magnetic field, all of it operating on a scale that redefines what a planet can be, turning it into something that feels closer to a star than to the worlds we are used to. And yet, it is not a star, it is something in between, a giant that never ignited, a world that formed at the edge of possibility, almost becoming something else but remaining what it is, a planet that carries within it the characteristics of something much larger. And that alone would make it extraordinary. But Jupiter does more than exist. It shapes, because its gravity influences the orbits of planets. Its presence defines the structure of the solar system. Its moons create environments that may hold the potential for life. Its radiation shapes the space around it. Its storms demonstrate the power of energy on a planetary scale. And all of these things together make Jupiter something more than just a destination, because it is not a place we go to. It is a place that defines where everything else can be, because without Jupiter, the solar system would not look the same. The balance would be different, the history would be different, and possibly we would not be here at all. And that gives Jupiter a different kind of importance, because it is not about exploration, it is about influence. Because even though we cannot stand on it, even though we cannot experience it directly, it is still connected to everything we know, a massive presence that has been shaping the system since the beginning. And that connection is what makes it unforgettable, because Jupiter is not just a world we observe. It is a world that has shaped the environment that allowed us to exist. And that means that even from a distance, even without ever touching it, it is part of our story. And as we move on, as we continue our journey through the solar system, leaving Jupiter behind, there is one final thought that remains. Because every planet we have seen so far has shown us something different. Mercury showed us extremes. Venus showed us what happens when a system collapses. Earth showed us what happens when everything works. Mars showed us what happens when a world loses its balance. And Jupiter shows us what happens when a planet becomes something more than just a world, a force that shapes everything around it. And that is why it matters. What you're hearing right now is not a rocket, it's not wind, it's not something recorded on Earth. It's Saturn, because deep in the data collected by spacecraft, scientists converted electromagnetic signals from Saturn into sound, and what came out did not feel like something from a planet. It sounded wrong, low, haunting, almost mechanical, as if something massive was humming in the darkness of space. And that alone is enough to make you stop, because Saturn looks calm, beautiful, perfect. With its iconic rings, its soft golden color, its smooth appearance, it feels almost peaceful compared to the chaos of Jupiter. But that is only what we see from a distance, because Saturn is not calm, it is not peaceful, it is not simple. Because beneath that smooth appearance lies a system just as extreme, just as powerful, and in some ways even more mysterious than anything we have seen so far. Because Saturn is a gas giant like Jupiter, made mostly of hydrogen and helium, with no solid surface, no ground to stand on, only layers of gas that become denser and more extreme as you go deeper. But Saturn is different, because it is less dense than water, meaning that, in theory, if you could find an ocean large enough, Saturn would float, a planet so massive, yet so light for its size, that it challenges how we think about structure. But that's just the beginning, because Saturn's most defining feature is not what lies inside it, it is what surrounds it, the rings, massive, complex, and incredibly thin. A structure made of billions of particles, ranging from tiny grains to massive chunks of ice and rock, all orbiting Saturn in perfect formation, creating one of the most iconic and recognizable features in the entire solar system. And yet, we still don't fully understand them because the rings are not permanent. They are not stable over infinite time. They are slowly disappearing, fading, being pulled into Saturn's atmosphere, meaning that what we are seeing right now is temporary, a moment in time, a phase in Saturn's life that will not last forever, and that makes it even more strange. Because we are observing Saturn at a very specific time in its existence, a time where its rings are visible, bright, and fully formed, even though they may not have always been there and will not always remain. And that creates a question, because if Saturn looks this perfect now, what did it look like before, and what will it look like after? Because Saturn is not just a beautiful planet, it is a system that is changing, slowly, quietly, but continuously. And when you combine that with the sounds, the strange emissions, the structure of the rings, the hidden layers beneath the clouds, something begins to feel different, because Saturn is not just another gas giant, it is something more mysterious, something that looks calm, but isn't, and that raises the question. Because if Saturn sounds like that, if it looks like this, then what is really happening there? When you look at Saturn, the first thing you notice is not the planet itself. It's the rings, bright, sharp, almost unreal, because nothing else in the solar system looks like this. And that alone raises a question. Why Saturn? Because rings are not unique to Saturn. Jupiter has them. Uranus has them. Neptune has them. But none of them come close. Because Saturn's rings are massive, stretching hundreds of thousands of kilometers across, yet incredibly thin, in some places only about 10 meters thick, a structure so wide and yet so flat that it almost feels impossible. And when you look closer, they are not solid, they are made of countless particles, ice, rock, fragments, each one orbiting Saturn independently, moving at different speeds depending on its distance from the planet, creating a system that looks smooth from afar, but is actually chaotic up close. A swarm, perfectly organized, but constantly moving. And that leads to the biggest mystery, because these rings should not exist, at least not like this. Because over time, collisions between particles should break them down, gravitational interactions should spread them out, and Saturn itself is slowly pulling material inward, causing what scientists call ring rain, where particles gradually fall into the planet's atmosphere. Which means the rings are temporary. They are disappearing, right now, slowly, but continuously. And that creates a strange realization. Because if the rings are fading, then they must have formed at some point. And that moment may not be as ancient as we think, because some evidence suggests that Saturn's rings might be relatively young, possibly only a few 100 million years old, meaning that they formed long after the planet itself. And that raises a darker idea, because if the rings are not original, then something must have happened, a destruction, because one leading theory suggests that the rings formed from a moon that got too close to Saturn, crossing a boundary known as the Roche limit, where the planet's gravity becomes so strong that it tears objects apart, breaking them, shattering them, turning a solid world into fragments, and those fragments became the rings. Which means that what we see today may be the remains of something that once existed, a moon, destroyed, spread out across space, frozen into a structure that looks beautiful, but began with violence. And that changes how you see Saturn, because the rings are not just decoration, they are evidence of something that ended and something that is still ending, because the process is not over. The rings continue to evolve, particles collide, break apart, fall inward, and over time, they will disappear completely, leaving Saturn as just another gas giant, without the feature that makes it so iconic. And that means something important, because right now, we are seeing Saturn at a very specific moment in its existence, a moment where the rings are still there, still visible, still defining the planet, but not forever, because in the future, Saturn will look different, simpler, less extraordinary, and that makes what we see now rare, a temporary phase, a cosmic coincidence, and that realization stays with you, because it means that Saturn's beauty is not permanent, it is fleeting, and we are just lucky enough to see it. If Jupiter is known for its chaos, its massive storms, its constant turbulence, then Saturn seems different at first. Calmer, smoother, almost peaceful. But that calm is an illusion, because hidden within Saturn's atmosphere is something that should not exist. A shape, perfect, precise, and completely unnatural at first glance. A hexagon. Because at Saturn's North Pole there is a storm unlike anything else in the solar system, a massive six-sided structure stretching over 30,000 kilometers across, larger than Earth itself, rotating slowly, maintaining its shape with a precision that feels almost artificial. And that is what makes it so unsettling, because storms are supposed to be chaotic, unpredictable, irregular, but this one is geometric, sharp edges, straight lines, a perfect hexagon floating in the clouds of a gas giant, and it has been there for decades. First observed by the Voyager spacecraft in the 1980s, still present today, unchanged in its basic structure, which raises a question. How? because nothing about Saturn suggests that such a shape should form naturally. And yet, it does. Because the hexagon is created by powerful jet streams, winds moving at incredible speeds, interacting in a way that creates standing wave patterns, stabilizing into this six-sided form, a phenomenon that can be recreated in controlled conditions on Earth, but never on this scale, never this stable, never this perfect. And inside the hexagon, there is a storm, a massive vortex at the center, rotating, pulling clouds inward, creating a system within a system, a structure that combines order and chaos at the same time. And this is what makes Saturn different, because while Jupiter is dominated by chaotic storms, Saturn shows us something else, that even in extreme environments, patterns can emerge, stable, persistent, almost mathematical, and that creates a strange contrast. Because Saturn looks calm from a distance, but when you look closer, it is just as extreme. Because the winds on Saturn can reach speeds of over 1,800 kilometers per hour, faster than anything on Jupiter, faster than anything we experience on Earth, creating a system where energy moves rapidly, shaping the atmosphere into bands, storms, and structures that are constantly shifting. And yet, the hexagon remains stable, defined, as if it exists outside of the chaos around it. And that makes it one of the most mysterious features in the solar system, because it challenges our expectations, because it shows that even in the most extreme conditions, where everything should be unstable, unpredictable, and chaotic, something can form and stay. And when you think about that, when you imagine a perfect geometric shape floating in the atmosphere of a gas giant, it begins to feel almost unreal, because Saturn is not just a planet of storms, it is a planet of patterns, and some of those patterns feel like they shouldn't be there at all. From the outside, Saturn feels almost soft, smooth, elegant. Its pale golden color, its gentle bands, its thin rings, everything about it gives the impression of something lighter, less violent than Jupiter. But that impression does not last, because just like Jupiter, Saturn has no surface, no ground, no place where you could ever stand, only layers, endless layers, and as you move deeper, everything changes. Because the upper atmosphere is only the beginning, clouds made of ammonia ice, drifting across the planet, forming the patterns we can see from space, creating the illusion of calm. But beneath those clouds, the pressure begins to rise, the temperature begins to increase, and the environment becomes something else entirely. Because just like on Jupiter, the hydrogen that makes up most of Saturn does not remain a gas forever. Under enough pressure, it changes, becomes liquid, dense, heavy, a state of matter that does not behave like anything we are familiar with. And as you descend further, the pressure becomes extreme, millions of times greater than what we experience on Earth, enough to crush anything, to break down structures, to remove any possibility of survival. And deeper still, hydrogen begins to transform again into metallic hydrogen, a state where it conducts electricity, where it behaves like a metal, creating currents, generating Saturn's magnetic field, a process happening far beneath the clouds, hidden from view but essential to the planet's structure. But here, where Saturn becomes even more mysterious, because unlike Jupiter, whose interior we have studied more extensively, Saturn's internal structure is less certain, less defined. Because Saturn is less dense, lighter for its size, which suggests that its internal layers may be different, less compact, more mixed, possibly with a core that is not solid in the way we imagine, but partially dissolved into the surrounding layers, creating a gradient rather than a clear boundary. And this uncertainty is important, because it means that Saturn is not just a smaller version of Jupiter. It is its own system, with its own structure, its own dynamics, its own unknowns. Because even something as fundamental as how heat moves through Saturn is still being studied. Because Saturn emits more energy than it receives from the Sun, just like Jupiter, but the exact processes behind this energy flow are not fully understood. And this means that Saturn is not just quiet. It is hidden. Because what we see on the surface, the clouds, the rings, the patterns, is only a thin layer of what actually exists. Beneath it, there is an entire world, one that we cannot observe directly, one that we can only model, estimate, imagine, and that makes Saturn different. Because while Jupiter feels overwhelming and chaotic, Saturn feels mysterious, less visible, less obvious, a planet where the most important processes are not on display, but hidden, deep within layers we cannot reach. And that raises a question, because if we cannot see what is happening inside Saturn, then how much of this planet do we really understand? If Saturn itself is mysterious, if its rings are temporary, if its atmosphere hides structures we don't fully understand, then the real surprise lies not on the planet, but around it, because Saturn has many moons, dozens of them, worlds orbiting within its gravitational field, but one of them stands out, not because it is the largest, not because it is the most extreme, but because it is something else entirely. Titan. Because Titan is not just a moon, it is a world so complex, so different that it feels less like a satellite and more like a planet in its own right. Because Titan has something that no other moon in the solar system has: a thick atmosphere, dense, layered, rich in nitrogen, so thick that the surface is completely hidden from view, covered by an orange haze, a global layer of hydrocarbons that blocks visible light, making Titan look like a glowing sphere from space. And that alone makes it unique, because moons are not supposed to have atmospheres like this, not at this scale, not this stable, and yet Titan does, but that's just the beginning, because beneath that atmosphere, there is weather, clouds, rain, rivers, lakes, but not made of water. Because on Titan, the temperatures are far too low for liquid water to exist on the surface. Instead, the rivers and lakes are made of methane and ethane, liquid hydrocarbons, flowing, collecting, evaporating, falling again as rain, creating a cycle that is eerily similar to Earth's water cycle, but completely alien, because on Titan, it rains methane, rivers carve the surface, lakes gather in lowlands, seas stretch across the poles, a world that looks familiar in structure, but is completely different in substance. And this is what makes Titan so important, because it is one of the few places in the solar system where stable liquid exists on the surface. Not water, but something else, something that behaves similarly. And that raises a question. Because where there are liquids, there are processes, chemistry, interactions, and possibly something more. Because Titan's atmosphere is rich in organic molecules, complex carbon-based compounds that are considered the building blocks of life. And these molecules are constantly interacting, driven by energy from sunlight and Saturn's magnetic environment, creating a system where chemistry is active, dynamic, and continuous. And this leads to an idea. Because while Titan is too cold for life as we know it, it may be possible for a different kind of life to exist there. Not water-based, but methane-based. Organisms that function in completely different conditions, using different Arabic alif, Arabic lam, Arabic kaf, Arabic yet, Arabic meme, Arabic yet, Arabic alif, Arabic hamza, different structures, different processes. And this idea is not just science fiction. It is something scientists are actively studying, because Titan represents something rare, a second type of environment where complex chemistry exists, a place where the rules are different. And that makes it one of the most important worlds in the solar system, because if life can exist on Titan, then life is not limited to Earth-like conditions. It can exist in forms we have not yet imagined, in environments we once thought were impossible. And that changes everything, because Titan is not just a moon, it is a possibility, a world that challenges our understanding of life, of chemistry, of what is possible in the universe. And that makes it one of the most exciting places we have ever discovered, because beneath that orange haze, there may be something we have never seen before. Imagine standing on Titan, not looking at it from orbit, not observing it through instruments, but actually being there. Because Titan is one of the very few places in the solar system where this is even imaginable. Because unlike Jupiter or Saturn, Titan has a surface, a real one, solid, cold, but stable, and when you arrive, the first thing you would notice is the sky, because it wouldn't be clear, it wouldn't be blue, it would be thick, orange, hazy, a dense atmosphere filled with hydrocarbons, scattering light in a way that makes everything feel dim, as if the entire world is covered in a permanent sunset. And the sun would look different, smaller, weaker, just a faint glow behind the haze providing light but not warmth, because Titan is cold, extremely cold, around -180 degrees Celsius, cold enough that water behaves like rock, frozen solid, forming mountains, ice that is harder than anything we experience on Earth. And this changes everything. Because on Titan, water is not the liquid that shapes the world. It is the ground, the solid structure. And instead, methane takes its place. Because as you look around, you would see rivers, channels carved into the surface, leading toward lakes and seas. But these are not water. They are liquid methane and ethane, dark, still, reflecting the faint light from the sky, creating landscapes that feel both familiar and completely alien at the same time, because the shapes are the same, but the substance is different, and if you could walk there, you would feel something strange. Because Titan's gravity is lower than Earth's, about 1/7, meaning that every step would feel lighter, slower, almost as if you were moving in slow motion. And the atmosphere is thick, denser than Earth's, which means that moving through it would feel different, heavier in some ways, easier in others. And this combination creates something unique, because on Titan, you could fly, not with engines, but with wings. Because the thick atmosphere and low gravity mean that human-powered flight is theoretically possible, a world where simply spreading your arms wide enough could allow you to glide through the air. And that alone makes Titan feel unreal. But there is something else. Because Titan is not silent in the way Mars is. Because its atmosphere carries sound. Wind moves. Liquids flow. Rain falls because, yes, it rains on Titan. Methane rain falling from clouds, carving the surface, feeding rivers and lakes, creating a cycle that feels almost like Earth's, but in a completely different form. And this creates a strange sense of familiarity. Because Titan looks like Earth in some ways, it has weather, it has landscapes shaped by liquid, it has a sky, a surface, processes that feel known, but at the same time, everything is different because the chemistry is different, the temperatures are different, the energy is different, and that means that while Titan feels like a world we could explore, it is not a world we understand, not fully. Because beneath that surface, beneath those lakes, beneath that thick atmosphere, there are processes happening that we are only beginning to study. Chemical interactions, organic molecules forming, breaking apart, reforming, creating a system that is active, dynamic, but still mysterious. And that is what makes Titan so fascinating, because it is not just alien. It is almost familiar, a reflection of Earth, in a completely different form, and that makes it one of the most unique places in the solar system, because it shows us that a world does not have to be like Earth to feel like one. If Titan feels like a world we almost understand, a strange version of Earth with different chemistry, then Enceladus feels completely different, because Enceladus hides its secret. It doesn't show it on the surface, it doesn't make it obvious, but once you know it's there, everything changes, because Enceladus is small, much smaller than Titan, a bright, icy moon covered in smooth, reflective ice, almost perfectly white, one of the most reflective objects in the solar system, making it look calm, cold, and completely inactive at first glance. But that appearance is misleading, because beneath that frozen surface, there is an ocean, and not just any ocean, a global ocean, liquid water, hidden beneath kilometers of ice. And we know this not because we saw it directly, but because Enceladus revealed it. Because from cracks near its south pole, massive plumes of water vapor, ice particles, and organic molecules are constantly being ejected into space, geysers shooting material hundreds of kilometers above the surface, creating a kind of spray that escapes the moon's gravity. And those plumes have been sampled because spacecraft flying through them detected something incredible: water, salts, organic compounds, even hints of hydrogen, which is important because hydrogen can be a source of energy, and where there is water and energy, there is always a possibility, because these conditions are very similar to environments on Earth where life exists, especially deep ocean hydrothermal vents, where organisms survive without sunlight. using chemical energy instead. And Enceladus may have something very similar, because beneath its icy shell, tidal forces from Saturn stretch and heat the interior, creating conditions where water remains liquid, where interactions between rock and water could generate energy, creating an environment that is not just stable, but active. And this is what makes Enceladus one of the most important places in the solar system. Because unlike Europa, where the ocean is hidden and difficult to access, Enceladus is already giving us samples. Its ocean is literally being sprayed into space, accessible, testable, within reach. And that means something incredible, because we don't need to drill through ice to study it. We just need to fly through the plumes, collect the material, analyze it, search for patterns, for structures, for anything that might suggest life. And that possibility changes everything. Because if life exists in Enceladus, even in the simplest form, then life is not limited to planets. It is not limited to sunlight. It can exist in darkness, beneath ice, driven by chemistry instead of light, and that expands the definition of what life can be, where it can exist, how common it might be, because Enceladus is not just a moon, it is a test, a place where one discovery could redefine everything we think we know. And that makes it one of the most exciting worlds we have ever found, because beneath that ice, there may be an ocean that is not empty. When you step back and look at Saturn as a whole, not just the planet, not just the rings, not just one moon, but everything together, something begins to emerge that is very different from what we saw around Jupiter. Because Saturn is not just a collection of extremes. It is a system of contrasts, balanced, almost carefully arranged. Because around one planet you have Titan, a world with rivers, lakes, and weather, a place that feels almost like a distant, colder version of Earth. You have Enceladus, small, bright, and quiet on the surface, yet hiding an ocean beneath, actively sending material into space. You have other moons, smaller, irregular, shaped by impacts, by gravity, by time, each one carrying a piece of Saturn's influence. And then, you have the rings, a structure that is both fragile and massive, both temporary and defining, a feature that gives Saturn its identity, even though it is slowly disappearing. And all of these elements exist together, in orbit, in motion, each one interacting with Saturn's gravity, each one influencing the others in subtle ways, creating a system that is not random, but structured, because the moons do not just orbit freely. They are locked in resonances, gravitational relationships that keep their orbits stable, that maintain distances, that create patterns over time, a system where motion is not chaotic but organized. And this organization creates something that feels almost harmonious. Because despite the scale, despite the complexity, despite the differences between each object, everything fits together. Everything moves in a way that maintains the system. And this is what makes Saturn different from Jupiter, because Jupiter feels dominant, overwhelming, a force that controls everything around it, but Saturn feels more balanced, more structured, a system where the planet, the rings, and the moons all contribute to something larger, because Saturn is not just the center, it is part of the system, A system where the rings are shaped by moons, where moons are influenced by Saturn, where gravitational interactions create stability rather than chaos. And this creates a different kind of beauty, because it is not just visual, it is structural. Because when you look at Saturn, you are not just seeing a planet with rings. You are seeing a system where everything is connected. Everything influences everything else. And that connection is what makes it so unique, because Saturn is not just defined by one feature. It is defined by how all of its features interact. And that creates something that feels almost intentional, even though it is. Because this system formed through natural processes, through gravity, through motion, through time, creating a structure that just happens to look perfect from our perspective. But that perfection is temporary. Because just like the rings are fading, the system will continue to evolve, moons will shift, interactions will change, structures will adjust, and over time, Saturn will not look the same, and that makes what we see now a moment, a snapshot, a phase in the life of a system that is still changing. And that realization adds something deeper, because it means that Saturn is not just beautiful. It is temporary beauty, a system that looks perfect, but will not always be. Saturn looks gentle, its colors are soft, its rings are thin. Its appearance feels almost calm compared to the chaos of Jupiter. But that calm hides something powerful, because Saturn's true strength is not in what you see. It is in what you don't. Gravity, because Saturn is massive. Not as massive as Jupiter, but still large enough to dominate everything around it, to control the motion of its moons, to shape the rings, to pull, stretch, and influence objects across vast distances. And this force is constant, invisible, but always there. Because every particle in Saturn's rings is held in place by gravity, orbiting at just the right speed, just the right distance, creating a structure that looks stable, but is actually in constant motion, a balance between falling inward and moving forward. And that balance is fragile, because if anything changes, even slightly, the entire structure can shift, particles can collide, break apart, fall into the planet, or escape. Because gravity does not just hold things together, it also tears them apart. And Saturn shows this clearly. Because just like with the rings, any object that comes too close to Saturn can be destroyed, pulled apart by tidal forces, stretched until it can no longer hold itself together, broken into fragments that may become part of the rings or disappear into the atmosphere. And this means that Saturn is not just a beautiful planet. It is also destructive, because anything that crosses the wrong boundary does not survive, and this extends beyond the rings. Because Saturn's gravity also influences objects passing nearby, altering trajectories, capturing some, redirecting others, creating a system where motion is constantly being adjusted, where paths are not fixed but influenced by a force that cannot be seen, only felt. And this creates a sense of unpredictability. Because while the system appears stable, it is actually dynamic, always changing, always adjusting. And that makes Saturn feel different, because it is not obviously violent like Jupiter. It does not show its power through massive storms or extreme radiation. It shows it quietly, through motion, through structure, through the way everything around it behaves. And that quiet power is what makes it dangerous, because it is not something you can see coming. It is something that is always there, always influencing, always shaping what happens. And that changes how you see Saturn, because it is not just a planet with rings. It is a system held together by a force that can also destroy it. A balance between order and destruction, between stability and change. And that balance is what defines Saturn, because everything around it exists, only because that balance holds. To understand Saturn, you have to go back to the beginning, not just of the planet, but of the entire solar system. Because Saturn formed from the same cloud of gas and dust that created everything else, a rotating disk surrounding the young sun, where particles collided, combined, and slowly grew into larger bodies. And in that process, Saturn became a giant, because it formed far enough from the sun that gases could remain stable, allowing it to accumulate vast amounts of hydrogen and helium, building a massive atmosphere, becoming one of the largest planets in the system. But its formation was not isolated, because as Saturn grew, so did everything around it. Moons began to form, material collected, orbits stabilized, creating the system we see today. But the rings are different, because they do not fit neatly into this formation story. Because if the rings formed at the same time as Saturn, they should be older, darker, more spread out, more degraded, but they are not. They are bright, relatively clean, structured, which suggests that they are younger. And that leads back to the same idea, destruction, because something must have happened after Saturn formed, something that created the rings we see today. And one of the strongest theories points to a moon, a world that once orbited Saturn, stable, intact, existing just like Titan or Enceladus does today, until something changed. Because over time, gravitational interactions can alter orbits, slowly shifting a moon closer to the planet, bringing it into a region where tidal forces become stronger, where the difference in gravity between one side of the moon and the other becomes too great. And eventually, that force wins, because when the moon crosses the Roche limit, it cannot hold itself together anymore. It begins to break, crack, fragment, until it is no longer a world but debris. And that debris spreads out, forms a disk, organizes into rings, particles colliding, sorting themselves by size and orbit, creating the structure we see today. And this changes everything, because it means that Saturn's most iconic feature may be the remains of something that no longer exists, a world that was destroyed. Not instantly, but inevitably, pulled apart by the very planet it once orbited. And that gives the rings a different meaning, because they are not just beautiful, they are a record, a trace of something that ended. And that ending is still ongoing, because the rings are not stable forever. They are slowly fading, particles falling into Saturn, being lost over time, meaning that the structure we see today is temporary. A phase, a moment in a much longer process. And that makes Saturn feel different, because it is not just a planet with rings. It is a system shaped by events, by interactions, by destruction and creation happening over time. And when you look at it that way, the rings are not just something to admire, they are something to think about. Because they represent a moment in Saturn's history that we are lucky enough to witness. A moment that will not last forever. A moment that began with the end of something else. And that idea stays with you, because it means that even something as perfect as Saturn has a past that is far more complex than it appears. Right now, when you think of Saturn, you think of its rings. That's what defines it. That's what makes it instantly recognizable. The one planet that stands out from all the others. But that identity is temporary because Saturn is losing its rings right now, at this very moment. Particles from the rings are slowly falling into the planet, pulled inward by gravity, interacting with Saturn's magnetic field, turning into what scientists call ring rain, a constant but nearly invisible process where material is being lost over time. And it's not slow on a cosmic scale, because estimates suggest that Saturn's rings could disappear in tens to hundreds of millions of years, a relatively short time compared to the age of the solar system, which means something strange. Because Saturn has existed for over 4 billion years, but the rings may only last a fraction of that. And that means we are seeing Saturn at a very specific moment, a rare phase, because for most of its existence, Saturn may not have had rings like this, and in the future, it won't. And that changes everything, because it means that the Saturn we recognize is not permanent. It is a version, a phase in its life, and eventually, that phase will end. Because as the rings fade, as particles are lost, as the structure becomes thinner and weaker, Saturn will slowly transform into something simpler, just a gas giant, like Jupiter, without the feature that makes it unique. And that transformation will not be dramatic. It won't happen all at once. It will be gradual, subtle, almost unnoticeable over short periods of time. But over millions of years, it will become clear, because the rings will shrink, fade, disappear, until one day they are gone. And that leaves a question, because if we were observing Saturn millions of years in the past, would we even recognize it? Would it have looked the same? Or would it have been just another gas giant without anything that makes it stand out? And if we could see it millions of years in the future, would we miss what it once was? Because the version of Saturn we know, the one with the rings, is not the only version. It is just the one we happen to see, and that makes it feel different, because it turns Saturn into something temporary, something that changes, something that evolves, not in the sense of life, but in the sense of structure, because even something as large and stable as a planet can have features that come and go. And that idea is powerful, because it reminds us that nothing is truly permanent, not even something as iconic as Saturn's rings. Because what feels timeless to us is just a moment in a much longer timeline, and Saturn is slowly moving toward a version of itself that we will never see. There is something different about Saturn, not just because of how it looks, but because of what it represents. Because Saturn is one of the few places in the solar system where beauty and decay exist at the same time, where something can look perfect, almost designed, almost unreal, and yet be in the process of disappearing. And that contrast changes how you see it. Because when you look at Saturn, you don't just see a planet. You see something that feels complete, balanced, elegant, the rings forming a perfect disk, the planet sitting at the center, everything aligned in a way that feels almost intentional. But it is. Because that perfection is temporary. because the rings are fading, slowly, quietly, but inevitably, and that creates a strange feeling, because it means that what we are looking at right now is not permanent, it is not timeless. It is a moment, a phase, something that exists now, but won't always exist. And that makes Saturn different from the other planets, because Jupiter feels constant, massive, unchanging. But Saturn feels fragile in a different way, not because the planet itself is fragile, but because the thing that defines it is, and that makes it feel almost human in a way, because we understand things that don't last, moments, phases, things that are beautiful because they are temporary, and Saturn becomes a symbol of that, because its rings are not just a feature, they are a reminder that even the most perfect things can fade, and that does not make them less important. It makes them more, because it means that their value is not in how long they last, but in the fact that they exist at all, and that we are able to see them. Because if Saturn's rings had disappeared millions of years ago, we would never know they were there. If they formed millions of years in the future, we would never see them, but we are here at the exact moment when they exist, and that coincidence is rare. Because the universe operates on timescales that are far beyond human experience, billions of years, processes that take longer than anything we can directly observe, and yet somehow we exist at a time where one of the most beautiful structures in the solar system is visible. And that changes how you think about it, because Saturn is not just something we observe. It is something we experience in time, a moment that we are part of, even if we are not directly there. And that makes it more than just a planet, because it becomes a reminder that even in a universe that feels permanent, there are things that come and go, things that exist for a moment, and then disappear, and Saturn's rings are one of those things. Imagine falling towards Saturn, not from far away, but already close enough that the rings fill your vision, stretching across space like a thin, endless plain of ice and dust, each particle moving silently, orbiting in perfect alignment, creating a structure that looks solid from a distance, but isn't, because as you approach the rings, something becomes clear. They are not dense, they are not a surface, they are space, filled with fragments, pieces of ice and rock, some as small as dust, others as large as buildings, all moving at incredible speeds, separated by distances that make collisions less frequent than you might expect. And as you pass through them, nothing happens, no impact, no resistance, just silence. Because even though you are surrounded by countless particles, the space between them is vast, creating a moment that feels almost unreal, like moving through something that should be solid, but isn't. And then you leave the rings behind, and Saturn fills everything, massive, dominant, its clouds stretching across the horizon, its color shifting from pale gold to deeper tones, its bands becoming more visible as you descend. And then you enter the atmosphere, but just like Jupiter, there is no clear boundary, no surface, only a gradual transition, because the upper layers are thin, almost transparent, giving way slowly to thicker clouds, to denser gas, to an environment that becomes more intense with every moment. And the deeper you go, the quieter it feels, Because Saturn does not have the same violent visual chaos as Jupiter, its storms are less obvious, its structure more subtle, and that creates something different, because instead of overwhelming noise, there is a kind of silence, a stillness, even though everything is moving, because the clouds surround you, endless, layer after layer, fading into each other. No clear direction, no reference point, just depth. And as you descend further, the light fades, because sunlight cannot penetrate deep into the atmosphere, leaving you in a dim, golden darkness, a world where everything is obscured, where visibility disappears, where you are no longer seeing the planet, but experiencing it, and the pressure begins to build, slowly at first, then faster, until it becomes overwhelming. Because the deeper you go, the more the gas around you compresses, becoming thicker, heavier, turning into something that no longer feels like air, but something closer to a fluid, surrounding you completely. And at that point, there is no turning back, because there is nowhere to go, no surface to reach, no place to stop, only deeper layers, more pressure, more heat, more unknown, and eventually, you reach regions we cannot fully describe, where hydrogen behaves differently, where matter changes state, where the environment becomes so extreme that our understanding becomes limited, and beyond that, there is nothing we can imagine clearly, because Saturn is not a place you can reach the bottom of. It is a place you fall into, endlessly, and never return. And that is what makes it different. Because Saturn is not just a planet you observe, it is a world you can only descend into, without ever finding the end. When you look at Saturn, not just quickly, not just as an image, but really think about what it is, its size, its structure, the scale of its rings, the distance between each part of its system, something begins to shift in your mind. Because Saturn changes your sense of scale. Because on Earth, everything feels large. Mountains feel massive. Oceans feel endless. Distances feel significant. But Saturn makes all of that feel small, because Saturn is enormous. So large that you could fit over 700 Earths inside it. And its rings stretch hundreds of thousands of kilometers across space, wide enough that if they were placed around Earth, they would extend far beyond the Moon. And yet, they are incredibly thin. A structure so wide and so flat that it almost feels impossible. And that contrast alone is enough to change how you think, because it shows that size is not just about volume. It is about proportion, about relationships between things. And Saturn exists at a scale where those relationships become difficult to understand. Because when you imagine standing near Saturn, not on it, but near it, seeing the rings stretching across the sky, seeing the planet filling your entire field of view, realizing that what you are looking at is something that exists far beyond anything you can experience on Earth. It creates a sense of distance, not just physical, but conceptual, because Saturn does not feel like a place you can relate to. It feels like something outside of your experience, something that exists on a different level, and that makes everything else feel smaller. Because Earth, with all its complexity, all its life, all its systems, becomes just one small part of a much larger structure. A structure where planets like Saturn exist, where scales are different, where the idea of large changes completely. And that can feel overwhelming, because it reminds you that we are not at the center, that we are part of something much bigger, something that does not revolve around us. But there is another side to that, because even though Saturn makes us feel small, it also shows us something else, because we can understand it, we can observe it, we can study it. We can send spacecraft across millions of kilometers to explore it, and that changes the perspective, because while we are small physically, we are not small in what we can do, because we are capable of reaching out, of learning, of understanding systems that exist far beyond our immediate environment. And Saturn becomes a symbol of that, because it represents both extremes. It shows us how small we are, and at the same time, it shows us how far we can reach, because even something as distant, as massive, as complex as Saturn is still within our ability to explore, and that creates a balance between insignificance and capability, between scale and understanding. And Saturn sits right in the middle of that, a reminder that the universe is vast, but not completely beyond our reach. Even after everything we've discovered about Saturn, the rings, the moons, the atmosphere, the strange patterns, the hidden oceans, there is something that still defines this planet more than anything else. We don't fully understand it, because Saturn, just like Jupiter, is not a solved world. It is a system filled with unanswered questions, details that don't quite fit, processes that we can observe but not completely explain. And some of those questions are fundamental, because we still don't know exactly how Saturn formed in detail, how quickly it accumulated mass, how its internal structure developed, or how its current composition reflects its early history. And that uncertainty extends to its interior, because we don't know exactly what lies at its center. Is there a solid core? Is it partially dissolved? Is the entire planet more mixed than our models suggest? Because the data we have, even from missions like Cassini, gives us clues but not complete answers. And then there are the rings, because even though we have theories about how they formed from a destroyed moon, from captured material, from ancient remnants, we still don't know for certain which explanation is correct, because each theory has evidence, and each theory has gaps, and that means the true origin of Saturn's rings is still unknown. And then there's the hexagon, that perfect six-sided storm at the North Pole. We know how similar patterns can form in controlled environments. We understand the physics behind standing waves. But we still don't fully understand why Saturn's hexagon is so stable, why it has lasted for decades, why it maintains its shape so precisely under conditions that should be far more chaotic. And then there's Titan, because while we understand parts of its atmosphere, its chemistry, its methane cycle, we still don't know exactly how complex its chemistry can become, whether it can lead to structures that resemble life, whether something is already happening there that we have not yet detected. And Enceladus, because we know there is an ocean, we know there are plumes, we know there are organic molecules, but we don't know what's actually in that ocean. We don't know if there are processes similar to those on Earth. We don't know if life exists there. And that might be one of the biggest questions in the entire solar system, because the answer could change everything. And this is what makes Saturn so important, because it is not just what we know, it is what we don't. Because Saturn is a reminder that even with advanced technology, even with decades of exploration, Even with missions that have traveled billions of kilometers, there are still things we cannot fully explain, because the universe is complex, and Saturn is part of that complexity. A system that continues to challenge us, to push us, to make us question what we think we understand. And that is what makes it exciting, because every unknown is an opportunity, because somewhere in Saturn's rings, in its atmosphere, in its moons, there are answers waiting to be discovered. And we are still searching. There is something deceptive about Saturn, because when you look at it, it doesn't feel threatening. It doesn't look violent. It doesn't look like a place where anything extreme is happening. It looks calm, smooth, almost gentle, but that is exactly what makes it dangerous. Because Saturn does not show its power the way Jupiter does. It hides it beneath layers, beneath patterns, beneath a surface that feels controlled even though it is. Because Saturn is just as extreme, just as unforgiving, just as impossible to survive, but it expresses that in a different way. Because the winds on Saturn can reach incredible speeds, faster than anything we experience on Earth, moving silently across the planet, shaping the atmosphere in ways that are not immediately visible, but constantly active. And the deeper you go, the more intense it becomes, because pressure builds, temperature rises, and the environment becomes something that cannot be experienced, something that overwhelms anything that enters it. But what makes Saturn different is not just the conditions, it is the contrast, because everything about it feels soft. The colors, the rings, the smooth transitions in its atmosphere, and that softness creates a false sense of safety, because it looks like something you could approach, something you could get close to, something that is less dangerous than Jupiter. But that is not true, because Saturn is just as destructive, because anything that gets too close can be torn apart by its gravity, broken down by tidal forces, turned into fragments that may become part of the rings or disappear into the planet. And this has happened before, because the rings themselves may be the result of destruction. A moon that got too close, a world that was pulled apart. Its remains now forming one of the most beautiful structures in the solar system, and that creates a strange contrast, because the rings look peaceful, elegant, but they may have formed from something violent, something that ended. And that combination is what makes Saturn unique, because it is both beautiful and dangerous at the same time, because it shows us that something can look perfect while hiding extreme conditions, that something can feel calm while being completely uninhabitable. And that duality makes Saturn different from the other planets, because it is not obviously extreme, it is subtly extreme. And that subtlety makes it more unsettling, because it is not what you expect, it is not what it appears to be. And that makes it harder to understand, because Saturn is not just a planet you look at, it is a planet you have to think about, a world where what you see is not the full story. Imagine Saturn without its rings. Take away the bright, glowing disk that surrounds it. Remove the feature that makes it instantly recognizable. And what remains is something very different. Because without the rings, Saturn would not stand out the same way. It would still be large, still beautiful in its own way, but it would look ordinary, just another gas giant, similar to Jupiter, less defined, less iconic. And that changes how we see it, because the rings are not just an addition. They are Saturn's identity. They are what makes it unique, what makes it different from every other planet in the solar system. And without them, Saturn becomes something else, something less distinct, and that raises a strange idea, because in the future, this will be real. Because as the rings fade, as particles fall into the planet, as the structure slowly disappears, Saturn will become that version of itself. A planet without rings. A world that no longer has the feature that defines it. And that creates a kind of loss, because we are used to seeing Saturn in a certain way, with rings, always with rings, but that is not permanent. That is just the version we happen to see. And that means that somewhere in the future, there will be observers, if anything is still there to observe it, that will see Saturn as just another gas giant, without knowing what it once looked like, without knowing that it once had one of the most beautiful structures in the solar system. And that idea feels strange, because it means that something so iconic can disappear completely, leaving no obvious trace, no clear evidence of what it once was, because once the rings are gone, they are gone, and that changes how you think about Saturn, because it is not just a planet with rings. It is a planet that happens to have rings right now, and that distinction is important, because it means that Saturn is not defined by something permanent. It is defined by something temporary, a feature that came into existence and will eventually disappear. And that makes Saturn feel different, because it is not just stable, it is changing, evolving, moving toward a version of itself that we will never see. And that makes the present moment more important, because it means that what we are seeing now is rare, a phase that does not last forever, a version of Saturn that exists only for a limited time. And that realization adds something deeper, because it reminds us that even in space, even on planetary scales, things change, things fade, things disappear. And Saturn's rings are one of those things. Far from the sun, far from the warmth and activity of the inner solar system, Saturn exists in a region where everything begins to slow down. The light is weaker, the energy is lower, the distances between objects grow larger, and in that quiet space, Saturn remains. Because even though it is massive, even though it dominates its region, there is a sense of stillness around it, a kind of silence that makes it feel different from the worlds closer to the sun. Because Saturn is not surrounded by life. It is not surrounded by activity in the way Earth is. There are no oceans filled with organisms, no continents, no atmosphere filled with sound as we know it, just space, and a system of moons and rings orbiting in silence. And that creates a feeling. Because when you imagine Saturn out there, orbiting slowly, taking nearly 30 Earth years to complete a single revolution around the Sun, moving through a region where time feels stretched, where change happens slowly, where processes take millions of years, it begins to feel distant in more than just space, because Saturn is not just far away, it is far removed from our experience, because everything about it operates on a different scale, a different pace, a different kind of environment, and that creates a kind of separation, because while we can observe it, while we can study it, while we can send spacecraft to explore it, we cannot connect to it in the same way we connect to Earth or even Mars, Because Saturn is not a place we can imagine living. It is not a place we can imagine visiting in a meaningful way. It is a place we observe from a distance, a world that exists beyond our direct reach. And that creates a kind of loneliness, not for Saturn itself, but for us, because it reminds us that there are places in the universe that will always remain out of reach, places that we can understand in theory but never experience directly. And Saturn is one of those places, a giant in the distance, surrounded by silence, moving slowly through space, unchanged by anything we do, unaffected by anything we are. And yet, it is still part of our system, still connected to us. Because even in its distance, even in its silence, Saturn is part of the same structure that we are part of, orbiting the same star, existing within the same gravitational system, influencing and being influenced in ways that are not always visible. And that connection matters, because it means that even something so distant is not completely separate, because in a system as large as the solar system, everything is connected, even the quietest, most distant, most unreachable worlds. After everything we've seen, the rings, the storms, the strange hexagon, the hidden oceans, the alien landscapes of Titan, the possibility of life beneath ice, Saturn begins to feel like something more than just a planet, because it leaves an impression, not just visually, but conceptually. Because Saturn is not defined by one thing, it is defined by contrast, because it is beautiful, but temporary, calm, but extreme, simple from a distance, but complex up close. And that combination creates something unique, because most planets can be described in a straightforward way. Jupiter is massive and chaotic. Mars is dry and ancient. Earth is alive and balanced. But Saturn is harder to define, because it exists between categories, because it is not just a gas giant, it is a system, a structure, a moment in time, because its rings are not permanent, its moons are not simple, its atmosphere hides patterns we do not fully understand, and all of these elements together create something that feels almost designed, even though it is. And that makes Saturn different, because it feels intentional, even though it is not, because everything about it aligns in a way that creates beauty, structure, and complexity at the same time. And that creates a kind of meaning, because Saturn becomes more than just an object in space. It becomes a reminder that the universe is not just chaotic, it is also capable of creating systems that feel balanced, that feel almost perfect, even if only for a moment. And that moment is what we are seeing right now, because Saturn's current form, with its rings, its structure, its system of moons, is just one phase in a much longer timeline, a phase that will change, that will evolve, that will eventually disappear. And that makes it more important, because it means that what we are seeing is rare, a version of Saturn that exists only now, a combination of conditions that will not last forever. And that realization adds weight to the observation, because it turns Saturn into something that is not just there, but something that we are witnessing, a moment in the life of a planet, a structure that exists now, but will not always exist. And that makes it feel different, because it is not just something to look at, it is something to think about, something that represents change, time, and the idea that even the most beautiful structures in the universe are not permanent. As we come to the end of Saturn's story, something becomes clear that wasn't obvious at the beginning. Saturn is not just a planet you look at. It is a moment you experience. Because everything about it, the rings, the moons, the atmosphere, the strange patterns hidden in its clouds, all of it exists together right now, forming something that feels complete, something that feels almost perfect. And yet, it won't last because the rings are fading, the system is evolving. The structure we see today is changing slowly but constantly, moving toward a version of Saturn that will look very different in the future. And that is what makes it powerful, because it means that Saturn is not just a static object in space. It is part of a timeline, a story, a process that continues long after we are gone. Because long after Earth has changed, long after the inner planets have evolved, long after the Sun itself begins to transform, Saturn will still be there, orbiting in the outer solar system, but not as the planet we know today. Because its rings will be gone, its identity will be different, its appearance simpler, and that transformation will happen quietly, without a single moment where everything changes, just a slow fading, a gradual loss of the feature that defines it. And that makes Saturn feel almost fragile, not in its structure, but in its identity, because what makes it special is temporary, and that creates a final thought. Because when you look at Saturn, when you imagine its rings stretching across space, when you think about how rare that moment is, how unlikely it is that we exist at the exact time when those rings are visible, it changes how you see it. Because it is not just something that exists, it is something we are lucky to witness. A brief moment in a much larger timeline, a structure that appears perfect, but is slowly disappearing. And that idea stays with you, because it reminds you that even in the vastness of space, even on scales that are difficult to understand, even in systems that feel permanent, there are things that come and go, things that exist for a moment, and then fade into the dark, and Saturn is one of those things. There is something wrong with Uranus, not violent like Jupiter, not dramatic like Saturn, but strange. Because Uranus doesn't behave like a normal planet. It doesn't rotate the way others do. It doesn't sit upright in its orbit. It doesn't follow the pattern you would expect, because Uranus is tilted, not slightly, not a few degrees, but completely, almost 98 degrees. Which means that Uranus is essentially lying on its side, rolling around the sun instead of spinning like the other planets. And that alone makes it different, because this tilt changes everything: seasons, day and night, the entire way the planet experiences sunlight. Because for long periods of time, one pole of Uranus faces the sun directly, receiving constant daylight for years, while the other side is left in complete darkness. And then it switches, slowly, over decades, because Uranus takes about 84 Earth years to orbit the Sun, meaning that each season lasts over 20 years. A world where time feels stretched, where change happens slowly, where light and darkness are not daily cycles, but long phases. And that creates something unusual, because Uranus is not dynamic in the way Jupiter or Saturn are. It appears calm, almost featureless. a smooth, pale blue sphere with very little visible structure. No obvious storms, no strong bands, nothing that immediately suggests activity. But that calm is misleading, because Uranus is not inactive. It is hidden, because its atmosphere contains methane which absorbs red light and reflects blue, giving the planet its distinct color, but also masking deeper layers, hiding structures that are not easily visible. And beneath that calm appearance, there is something else, because Uranus is cold, extremely cold, colder than any other planet in the solar system, even colder than Neptune, which is farther away from the Sun. And that should not happen, because Uranus receives more energy from the Sun than Neptune does. But it emits almost no internal heat, unlike Jupiter, unlike Saturn, unlike Neptune, which means that something about Uranus is different, something about its interior, its structure, its history, does not match the others. And that brings us back to the tilt. Because one leading theory suggests that Uranus was hit, a massive collision, early in its history, a collision so powerful that it knocked the planet over, tilting it onto its side, changing its rotation, possibly affecting its internal structure, its heat distribution, its entire evolution. And if that is true, then Uranus is not just strange, it is damaged, a planet that was changed by a single event, an impact so large that it altered everything. And that changes how you see it, because Uranus is not just quiet, it is quiet after something happened. A world that looks calm now, but may have had a violent past, and that creates a different kind of mystery. Because unlike Jupiter or Saturn, where the activity is visible, where the power is obvious, Uranus hides it. It shows almost nothing, but suggests something much deeper, something that we have not fully understood yet. And that makes Uranus one of the most unusual planets in the entire solar system, because it is not defined by what we see, but by what we don't. If Earth feels balanced with its steady rhythm of day and night, sunrise and sunset, a cycle that repeats every 24 hours, then Uranus feels completely disconnected from that idea. Because on Uranus, there is no normal day, no regular night, no rhythm that feels familiar. Because of its extreme tilt, Uranus experiences something that no other planet does to this degree: seasons that take decades, and light that behaves in ways that feel almost unnatural. Because when one pole of Uranus faces the Sun, it stays there for years, decades. Constant daylight, the Sun never setting, never dipping below the horizon, just circling slowly in the sky, creating a world where time loses its meaning, where there is no transition, no change between day and night. And on the opposite side, the opposite is happening: total darkness, for years. A frozen hemisphere where the sun never rises, where everything remains in shadow, where temperatures drop even further, creating one of the coldest environments in the entire solar system. And this imbalance lasts for a long time, because Uranus moves slowly, taking 84 Earth years to orbit the Sun, meaning that each extreme, each phase of light or darkness, lasts for over 20 years. A world where seasons are not just noticeable, but dominant, where entire generations could pass under the same conditions. And then, slowly, everything begins to change, because as Uranus continues its orbit, the angle shifts. The pole that was facing the sun begins to move away. The dark side begins to emerge, and for a brief moment, there is balance, a period where both hemispheres receive light, where the planet experiences something closer to what we would recognize as normal. But that moment doesn't last, because Uranus keeps moving, and eventually, the roles reverse. The side that was in darkness becomes illuminated. The side that was in light falls into shadow, and the entire cycle begins again. And this creates something strange, because Uranus is not just a planet with seasons. It is a planet defined by them. Because its entire environment, its temperature, its atmosphere, its behavior, is shaped by these long periods of light and darkness. And yet, it still looks calm, because from a distance, Uranus appears almost featureless, a smooth blue sphere, without the visible storms of Jupiter, without the detailed bands of Saturn. And that contrast makes it feel even more unusual, because a planet with such extreme conditions should look more active, more chaotic, but it doesn't, at least not on the surface. And that suggests something deeper, because it means that whatever is happening on Uranus is not easily visible, hidden beneath the clouds, masked by its atmosphere, or happening in ways that we do not yet fully understand. And that makes Uranus different, because it is not obvious. It does not show its extremes clearly. It hides them, behind a calm appearance, behind a smooth surface, behind a color that looks peaceful, but represents something much more extreme. And that is what makes Uranus so unsettling, because it looks simple, but it is. At first glance, Uranus looks like the most boring planet in the solar system. No massive storms like Jupiter, no visible rings like Saturn, no dramatic surface like Mars, just a smooth, pale blue sphere, almost featureless, almost still. But that stillness is not real, because Uranus has an atmosphere, and that atmosphere is moving constantly. We just don't see it the same way. Because Uranus is covered in a thick layer of methane gas, which absorbs red wavelengths of sunlight and reflects blue, giving the planet its distinct color, but also masking the deeper layers beneath. And this creates an illusion, because it hides details, softens contrasts, makes the planet appear smoother than it actually is. But when we look closer, using more advanced instruments, we begin to see something else, because Uranus does have storms, cloud systems, winds, moving across its atmosphere at high speeds, in some cases reaching hundreds of meters per second, creating flows that circle the planet, shaping the atmosphere in ways that are not immediately visible from a distance. And these storms are strange, because they don't behave like Jupiter's. They don't form massive, long-lasting structures like the Great Red Spot. They appear, they change, they fade, more subtle, more temporary. And that makes them harder to study, because they don't leave obvious marks. They don't define the planet visually. They remain hidden unless you look closely. And that hidden activity creates a deeper mystery, because Uranus is cold, very cold, colder than Neptune, even though Neptune is farther from the sun. And that suggests something unusual. Because most giant planets emit internal heat, Jupiter does, Saturn does, Neptune does, but Uranus doesn't, or at least not in the way we expect, because it emits very little excess heat. which raises a question, because if there is less internal energy, then what is driving the atmosphere? What is powering the winds? What is creating the storms we do see? And we don't fully know because Uranus challenges our models. It doesn't fit perfectly into the patterns we see with other gas giants. Its energy balance is different. Its structure may be different. Its history may have changed how it behaves today. And that makes it difficult to understand, because Uranus is not just a quieter version of Jupiter or Saturn. It is something else, a planet that looks calm, but still moves, a planet that appears inactive, but still has processes we cannot fully explain. And that contrast makes it more mysterious because it is not obvious. It does not show its complexity clearly. It hides it beneath layers, beneath color, beneath an appearance that suggests simplicity, while masking something much more complex. And that is what makes Uranus so different, because it is not what it looks like. It is something deeper, something quieter, but still active, still changing, still not fully understood. Uranus is often grouped together with Jupiter and Saturn, called a gas giant, treated as part of the same category. But that is not entirely accurate, because Uranus is different, fundamentally different, because it is not just made of gas. It is an ice giant, and that changes everything. Because while Jupiter and Saturn are dominated by hydrogen and helium, Uranus contains a much higher proportion of heavier elements: water, ammonia, methane, materials that, under the extreme pressures and temperatures inside the planet, do not behave like ice as we know it, but form something far more unusual. Because inside Uranus, there may not be clear layers, not a simple structure of atmosphere, liquid core, but something more mixed, more complex. A deep interior where materials blend, where water, ammonia, and methane form a dense, hot fluid, sometimes described as a slushy ocean of exotic chemistry. And within that, something even stranger may exist, because under extreme pressure, carbon atoms from methane could be compressed into diamonds, not small ones, but potentially massive ones, forming deep within the planet, and then falling like rain, diamond rain, a process where carbon separates, crystallizes, and sinks deeper into the planet, moving through layers we cannot observe directly. And while this may sound unreal, it is supported by experimental data, because under the right conditions, methane can break apart, releasing carbon, which then forms diamond structures. And Uranus has those conditions, and that changes how you imagine the planet, because it is not just a ball of gas. It is a world with processes that feel almost alien, where materials behave differently, where chemistry operates under conditions we cannot replicate easily, where even something as familiar as carbon becomes something else, something solid, falling through layers of fluid. And this is only part of the mystery, because Uranus's internal structure is not well understood. We don't know exactly how these materials are distributed. We don't know how stable these processes are. We don't know how they affect the planet's magnetic field, its temperature, its evolution over time. And that uncertainty is important, because it means that Uranus is not just different on the surface. It is different all the way through. Because its interior is not just hidden, it is unfamiliar, operating under conditions that challenge our understanding of planetary physics. And this makes Uranus more than just a distant planet. It makes it a laboratory, a place where extreme conditions create processes that we cannot fully observe, but can begin to imagine, to model, to study. And that is what makes it interesting, because Uranus is not obvious. It does not show its complexity clearly, but beneath that smooth, pale blue surface, there is a world made of something else entirely, something that does not exist on Earth, something that behaves in ways we are only beginning to understand. And that makes Uranus one of the most unusual planets in the entire solar system, because it is not just different, it is fundamentally different. When you think about rings in the solar system, you think about Saturn, bright, massive, impossible to ignore. But Saturn is not the only planet with rings. Uranus has them too. And they are completely different. Because Saturn's rings are wide, reflective, and visible even with small telescopes. But Uranus' rings are dark, thin, and almost invisible because they don't reflect much light, they don't glow, they don't stand out. They sit there quietly surrounding the planet like faint outlines, structures that you would miss entirely if you didn't know they were there. And that alone makes them strange, because rings are usually associated with beauty, with brightness, with something visually impressive. But Uranus rings feel different because they feel hidden, almost secret. Because they are made of darker material, likely carbon-rich particles, mixed with ice, creating a structure that absorbs more light than it reflects, making the rings appear narrow, sharp, and difficult to detect. And they are not spread out like Saturn's. They are confined, tightly packed into thin bands, separated by gaps, orbiting the planet in a way that feels more rigid, more controlled. And that gives them a different character, because instead of looking like a smooth disk, they look like a system of lines, precise, defined, almost mechanical, and that creates a strange contrast because Uranus itself looks soft, smooth, featureless, but its rings are sharp, structured, dark. And that combination makes the entire system feel different from anything else we've seen because it doesn't draw attention to itself. It doesn't try to be visible. It exists quietly, in the background, and that raises a question, because if Uranus has rings, why do they look like this? Because they are likely younger, or at least different in origin, possibly formed from collisions between moons, fragments that did not spread out into wide disks like Saturn's, but instead remained confined, influenced by the gravitational interactions of nearby moons, which act as shepherds, keeping the rings narrow, preventing them from dispersing. And this creates a system that is stable, but fragile, because just like Saturn's rings, Uranus' rings are not permanent. They will evolve, change, possibly disappear over time, but unlike Saturn, they are not obvious. They are not something you would immediately notice, and that makes them feel more mysterious, because they are there, but almost hidden, a feature that exists without defining the planet, and that fits Uranus perfectly. Because Uranus is not a planet that reveals everything at once. It hides. It keeps its most interesting features subtle, quiet, difficult to see, and its rings are part of that, a structure that surrounds the planet, but never fully reveals itself. If Uranus itself feels strange, tilted, quiet, almost hiding its complexity, then one of its moons takes that feeling even further. Because Miranda, doesn't look like it should exist. Because when you first see it, it doesn't look like a normal moon. It looks broken, as if pieces from different worlds were forced together, as if something shattered it, and then tried to rebuild it, but didn't quite succeed. Because Miranda's surface is unlike anything else in the solar system. Massive cliffs, deep canyons, chaotic regions where the terrain changes abruptly, smooth areas suddenly giving way to rough, jagged structures, as if the surface was rearranged, shifted, torn apart, and then frozen in place. And one of its most extreme features is Verona Rupes, a cliff so high that it reaches up to 20 kilometers, one of the tallest known cliffs in the entire solar system, far higher than anything on Earth. A drop so extreme that if you were standing at the top looking down, it would feel almost unreal, because the scale is difficult to comprehend. And that alone makes Miranda unusual, but it goes deeper, because the surface doesn't just have one strange feature. It has many regions that look completely different from each other, as if they formed under different conditions, at different times, or from different processes. And that leads to a question, because how does a small moon like this become so complex? Because Miranda is not large. It doesn't have the gravity to drive intense geological activity like larger moons. It shouldn't have enough energy to reshape itself in such dramatic ways. And yet, it did, and one of the leading ideas is something extreme, because Miranda may have been destroyed, or at least partially. Because in the past, gravitational interactions with Uranus could have created internal heating, enough to destabilize the moon, possibly leading to fragmentation, breaking it apart, and then allowing it to reassemble under its own gravity. A process that would create exactly what we see, a patchwork surface, fragments of different regions, reconnected, but not perfectly. And that idea is unsettling, because it means that Miranda is not just unusual, it is a survivor, a world that may have been torn apart and put back together. And that creates a different kind of story, because while other moons evolve slowly through impacts and gradual changes, Miranda may have experienced something sudden, something violent, something that left a permanent mark. And that mark is still visible today, because its surface is not smooth, not uniform, but chaotic, a record of something that happened, something that changed it completely. And that makes Miranda one of the strangest objects in the solar system. Because it doesn't just look different, it tells a story of destruction and reconstruction, a world that should not look the way it does, but does, and that makes it unforgettable. When you step back and look at Uranus as a whole, not just the planet, not just one moon, not just the faint rings, but everything together, something begins to feel different. Not dramatic, not chaotic, but off. Because Uranus doesn't behave like the other systems we've seen. It doesn't dominate like Jupiter. It doesn't balance like Saturn. It doesn't show its structure clearly. It feels quieter, more distant, almost disconnected. Because everything around Uranus is subtle. The rings are faint. The atmosphere is smooth. The storms are hidden. The moons are irregular. Nothing stands out immediately. Nothing draws your attention the way it does with the other planets. And yet, everything is still there. Because Uranus has a system, a collection of moons, a structure of rings, a gravitational field that holds everything together, but it feels different because it lacks contrast. It lacks obvious activity. It lacks the visual signs that we associate with dynamic systems, and that creates a strange effect because it makes Uranus feel still, even though it is, because everything is moving. The moons are orbiting, the rings are shifting, the atmosphere is flowing, but it happens quietly, subtly, without the dramatic visuals we see elsewhere. And that quietness creates something unusual, because it makes Uranus feel almost isolated, even though it is part of the same solar system, because it doesn't interact in the same visible way. It doesn't influence its surroundings as strongly as Jupiter. It doesn't display its structure as clearly as Saturn. It exists, but without drawing attention to itself. And that makes it harder to understand, because we rely on what we can see, on what stands out, on what is obvious. But Uranus doesn't offer that. It hides its complexity behind a smooth surface, behind faint features, behind an appearance that suggests simplicity, even though it isn't simple at all. And this creates a different kind of mystery, because Uranus is not unknown because we haven't looked at it. It is unknown because it doesn't reveal itself easily, because its most interesting features are not obvious. They are subtle, hidden, and that makes the entire system feel different, because it is not chaotic, not balanced, but quiet in a way that feels almost unnatural, because in a solar system full of extremes, Uranus stands out by not standing out, and that makes it one of the most unusual systems we have, because it is not defined by what it shows, but by what it hides. Uranus does not look dangerous. There are no massive storms visible from a distance, no violent colors, no structures that immediately suggest power, just a smooth, pale blue sphere. Calm, silent, almost empty, but that calm hides something fundamental: gravity. Because Uranus may not dominate its region like Jupiter, but it is still massive enough to control everything around it, to shape the orbits of its moons, to hold its rings in place, to pull, adjust, and influence objects that come too close. And that force is constant, invisible, but always there, because every moon around Uranus exists because of that balance, a continuous motion between falling toward the planet and moving forward, creating stable orbits that can last for millions or even billions of years. But that stability is not guaranteed, because gravity is not just a force that holds things together. It is also a force that can destroy them. Because if an object gets too close to Uranus, crosses the wrong boundary, enters the region where tidal forces become too strong, it can be stretched, pulled apart, broken into fragments. Just like we saw with Saturn, just like we see across the solar system. And that means Uranus is not passive. It is active, in a quiet way, because it does not show its power openly. It expresses it through motion, through influence, through the way everything around it behaves. And that quiet power is what makes it different, because it does not feel threatening. It does not look extreme, but it still has the same potential, the same ability to reshape objects, to alter paths, to create structures like rings from destruction. And this creates a strange contrast, because Uranus looks harmless, but it is. Because anything that enters its system is affected, changed, controlled, even if that change is not visible immediately. And that makes it harder to understand, because we expect danger to be obvious, to be loud, to be visible. But Uranus shows something else: that danger can be silent, that a system can be powerful without looking powerful. And that changes how you see it, because Uranus is not just a quiet planet. It is a planet that hides its influence, a world where forces are always at work, even if you can't see them. Uranus did not start like this. It did not begin its existence lying on its side, rotating in a way that feels completely wrong compared to every other planet. Something happened, something powerful enough to change an entire world, because planets don't just tilt like that on their own. A slight tilt, yes, but 98 degrees, that requires force. And the most widely accepted explanation is simple and violent: a collision. Early in the history of the solar system, when everything was still forming, when planets were still growing, when objects were still moving unpredictably, Uranus may have been struck by something massive. Not a small asteroid, not even something the size of our moon, but something comparable to Earth, a planetary-scale object. And the impact changed everything, because it didn't just hit Uranus, it reshaped it. Because a collision of that scale would have transferred enormous energy, enough to knock the planet over, tilting its axis, altering its rotation, possibly disrupting its internal structure, redistributing material inside the planet in ways we still don't fully understand. And the effects didn't stop there, because such an impact could also explain why Uranus behaves differently from the other giant planets, why it emits so little internal heat, why its interior may be more mixed, why its magnetic field is unusual. Because the collision may have disrupted the internal flow of energy, changing how heat moves through the planet, creating a system that is less active internally, even if it still has motion in its atmosphere. And that idea makes Uranus feel different, because it is not just strange. It is the result of something, a past event, a moment in time that left a permanent mark. Because while other planets evolved more gradually, Uranus may have experienced a single, massive change that altered its entire trajectory. And that creates a different kind of story. Because Uranus is not just a quiet planet, it is a planet that was changed. A world that carries the result of an event that happened billions of years ago, but is still visible today, because its tilt is not temporary, it is permanent, a reminder of that collision, a sign that something happened that was powerful enough to reshape an entire planet. And that raises a question, because if Uranus experienced something like that, what else happened in the early solar system? How many collisions shaped the planets we see today? How many worlds were altered or destroyed entirely? Because the solar system was not always stable. It was chaotic, violent, unpredictable, and Uranus may be one of the clearest examples of that, a planet that survived, but did not come out unchanged. And that makes it more than just unusual. It makes it a record of a past that was far more chaotic than what we see today. If Uranus already feels distant, already feels cold, already feels quiet, then its future only takes those qualities further. Because Uranus is not a planet that will suddenly change. It is a planet that will slowly fade. Because even now, Uranus receives very little energy from the Sun, and unlike Jupiter or Saturn, it does not produce much internal heat of its own, meaning that over time, as energy continues to dissipate, the planet will become even colder, even quieter, even more still. And that process is slow. So slow that it is almost impossible to notice on human time scales. Because planets evolve over millions and billions of years, not days or centuries. But if you extend the timeline far enough, the changes become clear. Because as Uranus continues to orbit the Sun, as its internal energy decreases, as its atmosphere loses what little dynamic activity it has, the planet will gradually become more uniform, more stable, less active. Because without strong internal heat, there is less energy to drive motion, less energy to create storms, less energy to create change. And that means Uranus will become even more silent, even more featureless, a world where movement slows, where activity fades, where the planet settles into a state that is closer to equilibrium. But that is only part of the story, because the future of Uranus is tied to the future of the entire solar system, because eventually, the Sun will change, expanding into a red giant, growing larger, brighter, altering the entire structure of the system, pushing heat outward, affecting planets that were once cold. And Uranus will feel that change, because even at its distance, the increase in solar radiation will affect its atmosphere, its temperature, its outer layers, creating a period where the planet is no longer as cold as it once was. A temporary shift, a phase where Uranus becomes warmer, more active, but only for a time. Because after that phase ends, after the Sun sheds its outer layers and becomes a white dwarf, the entire solar system will enter a much colder state, darker, quieter, with very little energy remaining, and Uranus will continue to orbit, but in a very different environment, a dim star, a cold system, a planet that already felt distant becoming even more isolated, and over extremely long time scales, trillions of years. Uranus will continue to cool, continue to lose energy, continue to become more stable, more still, until it reaches a state where almost nothing changes, a world frozen not just in temperature, but in activity, and that creates a final image, because Uranus already feels like a quiet planet, a distant world, a place where time moves slowly, but in the future, it will become even more that, a planet drifting in the dark, cold, silent, unchanging, and that makes it different from the others, because while other planets are defined by activity, by storms, by energy, Uranus is defined by what happens when that energy fades. A world that shows us what a planet looks like when everything begins to slow down at the very edge of the solar system. There is a planet that doesn't make sense, because by everything we understand, Neptune should be quiet. It is the farthest planet from the Sun. It receives almost no energy. The light is weak. The heat is minimal. Everything about its position suggests one thing, stillness, but Neptune is not still. It is the opposite, because Neptune has the fastest winds in the entire solar system, faster than Jupiter, faster than Saturn, faster than anything we have ever observed. Winds reaching over 2,000 kilometers per hour, supersonic, moving faster than the speed of sound on Earth, on a planet that should be frozen and inactive. And that alone creates a contradiction. Because where does that energy come from? Because Neptune receives very little sunlight. And yet, Its atmosphere is in constant motion, storms forming, winds accelerating, clouds racing across the planet, a system that feels alive, even though it shouldn't be. And then there are the storms, dark spots, massive, temporary, appearing and disappearing over time. Unlike Jupiter's great red spot, which has lasted for centuries, Neptune's storms are unstable. They form, they grow, and then they vanish. A planet where even the largest structures don't last. And that creates something unpredictable because Neptune is not just active. It is constantly changing because nothing stays the same, because everything is moving too fast. Because when you look at Neptune, you don't see stability. You see motion, energy, a system that refuses to be still, even in the coldest part of the solar system. And that makes it different, because Neptune is not just distant, it is extreme, a world that should be quiet, but isn't. And that raises a question, because if Neptune has this much energy, this much motion, this much activity, then what is really happening there? Because something about this planet doesn't match what we expect. When you look at Neptune, the first thing you notice is its color, not pale like Uranus, not striped like Jupiter, not soft like Saturn, but deep, a dark, intense blue, almost unnatural, because Neptune doesn't just reflect light, it absorbs it. Because like Uranus, Neptune's atmosphere contains methane, which absorbs red wavelengths and reflects blue. But on Neptune, that blue is deeper, richer, more saturated, giving the planet a color that feels heavier, almost like looking into something rather than at it. And that creates a different feeling. Because Neptune doesn't look calm, it looks deep, like an ocean, but not one you could ever reach. Because this is not water, it is atmosphere. Layers of gas stretching thousands of kilometers deep, creating a sense of depth that is hard to understand, a world where the surface you see is not a surface at all. And the deeper blue suggests something else, because it hints at energy. Because Neptune's color may be influenced not just by methane, but by other, unknown components in its atmosphere, substances that absorb and scatter light in ways we don't fully understand yet. And that uncertainty makes the color more than just visual. It becomes a clue, because Neptune is telling us something about its composition, something about what exists in its atmosphere, but we don't fully know what, and that makes it more mysterious. Because when you look at Neptune, you are not just seeing a color, you are seeing the result of processes happening deep within the planet, interactions between light and matter that we are still trying to understand. And that creates a different kind of image, because Neptune doesn't feel like a planet you can approach. It feels like something you could fall into, a deep blue world where the further you go, the less you understand. And that idea becomes stronger when you consider how little sunlight reaches it. Because Neptune is so far from the sun that daylight there is faint, weak, barely enough to illuminate the planet, meaning that its deep blue color exists in a dim environment, creating a world that feels darker than the others, more distant, more isolated. And that isolation changes how it feels, because Neptune is not just far away, it is at the edge. The last major planet before space becomes something else entirely, and that gives it a different presence, because it is not just another step in the solar system. It is the boundary, the point where the familiar begins to fade. And when you look at that deep blue color, it begins to feel like more than just a visual feature. It feels like a depth, a hint of something below the surface, something we cannot see, but know is there. On Jupiter, storms last for centuries. On Saturn, patterns can remain stable for decades. But on Neptune, nothing stays, because Neptune's storms are different. They don't last. They don't define the planet. They appear. And then they're gone. And that makes them harder to understand. Because one of the most famous features ever observed on Neptune was the Great Dark Spot, a massive storm system similar in size to Earth, first seen by Voyager 2 in 1989, a deep, swirling vortex moving across the planet's atmosphere. And at the time, it seemed like something permanent, something stable, something we could study over time. But when we looked again, it was gone, completely disappeared. And that was unexpected, because storms that large don't usually vanish like that, not without leaving something behind, not without a trace. But Neptune doesn't follow those rules, because its atmosphere is too dynamic, too fast, too unstable. Because the winds on Neptune move at extreme speeds, tearing structures apart, reshaping the atmosphere constantly, preventing long-term stability, creating a system where nothing holds its form for too long. And this creates something unusual, because Neptune is not just active, it is unpredictable, because storms can form anywhere, grow quickly, and then dissipate without warning, without a clear pattern. And that makes Neptune feel different, because it is not a planet where you can track features over long periods. It is a planet where everything is temporary, because even the largest storms don't last, and that creates a different kind of chaos, because it is not constant like Jupiter. It is shifting, changing, unstable. Because when you look at Neptune, you are not seeing a fixed system. You are seeing a moment, a snapshot, because what you see today might not be there tomorrow. And that makes it harder to understand, because it means that Neptune is always changing, always evolving, always moving towards something different. And that creates a deeper question, because if Neptune's atmosphere is this dynamic, this unstable, this fast, then what is driving it? Because something is fueling that motion. Something is providing energy, but it doesn't come from the sun, at least not enough, which means it must come from within. But how? Because Uranus, which is similar in size and composition, shows almost no internal heat, and yet Neptune does, which means that something about Neptune is different, something about its interior, its history, its structure, is allowing it to remain active, even at the edge of the solar system. And that difference is what makes Neptune so mysterious, because it is not just a distant planet. It is a planet that refuses to be quiet. Neptune shouldn't be this active. By everything we understand about distance and energy, a planet that far from the sun should be cold, quiet, and mostly inactive. And yet, Neptune is alive with motion. Because the key difference between Neptune and Uranus lies deep inside. Because Neptune produces its own energy, not from sunlight, but from within. Because Neptune emits more than twice the energy it receives from the sun, meaning that something inside the planet is still releasing heat, driving atmospheric motion, powering winds, fueling storms. And that creates a contradiction, because Neptune and Uranus are similar in size, similar in composition, similar in distance, and yet they behave completely differently because Uranus is quiet, cold, inactive, but Neptune is not, and that means something about Neptune's interior is different. Because one possibility is that Neptune retains more of its original heat, energy from its formation that has not yet dissipated, trapped within its interior, slowly escaping over time. But that may not be enough to explain everything, because the energy levels we observe suggest that something else could be happening, something more complex. Because Neptune's interior may be more dynamic, more active, with processes that allow heat to move more efficiently, creating convection, movement within the planet that transfers energy outward, feeding the atmosphere. And this could explain the winds, the storms, the constant motion. Because if heat is rising from within, it creates differences in temperature driving circulation, creating a system that is not dependent on sunlight. A system that runs on internal energy, and that changes everything, because it means that Neptune is not just reacting to its environment, it is generating its own, a self-driven system. A planet that remains active even in the coldest part of the solar system. And that makes it different, because most planets rely on external energy to drive activity. But Neptune does not, at least not entirely. And that independence makes it more mysterious, because we don't fully understand how that energy is stored, how it moves, how it is released. Because the conditions inside Neptune are extreme, pressures and temperatures so high that materials behave in ways we cannot fully replicate, creating a system that is difficult to model, difficult to test, difficult to understand. And that leaves us with questions, because if Neptune can remain this active, this energetic, this dynamic, then what else is happening inside it? What processes are taking place that we have not yet discovered? What mechanisms are driving this constant motion? And that is what makes Neptune different, because it is not just distant. It is active in a way that challenges what we expect, a planet that should be quiet, but isn't. If Neptune itself feels strange, distant, and full of hidden energy, then its most important moon takes that feeling even further, because Triton shouldn't be there. Because unlike most large moons in the solar system, Triton does not orbit Neptune in the same direction as the planet's rotation. It moves backward, a retrograde orbit, which is a clear sign of something unusual, because moons don't normally form like that. They form from the same material as their planet. They orbit in the same direction. They follow the same motion. But Triton doesn't. And that means one thing. It wasn't always part of Neptune, because Triton is most likely a captured object. A world that formed somewhere else, possibly in the outer regions of the solar system, and was later pulled into Neptune's gravity, trapped, forced into orbit, becoming part of a system it didn't originate from. And that changes everything, because capture is not a gentle process. It is chaotic, violent. Because for an object to be captured, energy must be lost, orbits must be disrupted, and in many cases, other objects are affected. And that suggests that when Triton was captured, something happened, Because before Triton arrived, Neptune may have had a different system of moons, a system that was disrupted, destroyed, or ejected as Triton settled into orbit, and that makes Triton not just unusual, but disruptive, a moon that changed the system it entered, and Triton itself is just as strange because its surface is cold, extremely cold, one of the coldest places in the solar system, and yet it is active because Triton has geysers, not water geysers like on Enceladus, but nitrogen geysers, plumes of gas erupting from the surface, driven by internal heat, creating dark streaks across the icy terrain, showing that even in such extreme cold, there is still energy, still motion, still activity. And that alone makes Triton unique, because it is a captured world. That is still evolving, still active, still changing, and there is something else, because Triton's orbit is slowly changing, because tidal interactions with Neptune are gradually pulling it closer to the planet, and that leads to a future that is not stable, because eventually Triton will get too close, and when that happens, the same forces that may have created Saturn's rings will take over, because Triton could be torn apart, broken, reduced to fragments, forming a new ring system around Neptune. And that creates a strange timeline, because Triton was captured, changed the system, and in the future, it may be destroyed, becoming something else entirely. And that makes it one of the most unusual objects in the solar system, because it doesn't belong. And yet, it is there, a world that was pulled in, that changed everything, and that may one day become something completely different. Neptune is not just another planet, it is the last one, the outer boundary of what we consider the solar system's main structure, the final major world before space begins to feel different, emptier, less defined. Because beyond Neptune, there are no more planets like this, no more giants, no more worlds with thick atmospheres and complex systems of moons, only smaller objects, distant, scattered, fading into the darkness, and that gives Neptune a different presence, because it is not just part of the solar system, it is the edge of it. Because everything inside Neptune's orbit feels connected, structured, influenced by the Sun in a way that creates a clear system. But beyond Neptune, that structure begins to break down. Objects become more distant, orbits become less regular, the environment becomes colder, quieter, and Neptune sits right at that transition between the known and the unknown, and that makes it feel different, because it is not surrounded by activity in the way inner planets are. It is not part of a dense region of space. It exists in a place where distances are large, where interactions are less frequent, where the environment feels almost empty. And that emptiness creates a sense of isolation, because Neptune is far from the Sun, far from the inner planets, far from anything that resembles what we experience. And that distance is not just physical, it is conceptual, because Neptune feels disconnected, a world that exists at the edge of our understanding, because we have only visited it once. A single spacecraft, Voyager 2, passing by in 1989, giving us our most detailed look, and since then, we have only observed it from a distance. which means that most of what we know about Neptune is limited, incomplete, because we haven't returned, we haven't explored it in detail. We haven't studied its system the way we have with Jupiter or Saturn, and that leaves gaps, because Neptune is not well understood, not compared to the other planets. And that makes it more mysterious, because it is not just distant, it is underexplored. A world that we have seen, but not fully studied. And that creates a different kind of curiosity, because Neptune is not just a known planet. It is a reminder of what we haven't explored yet, of how much is still out there, of how much remains unknown, because even in our own solar system, there are places we barely understand, and Neptune is one of them, a planet at the edge, a world that marks the boundary between what we know and what we are still trying to discover. Neptune doesn't look violent. There are no bright storms like Jupiter, no glowing rings like Saturn, no dramatic features that immediately suggest danger, just a deep blue sphere, calm, distant, silent. But that silence is misleading, because Neptune is one of the most violent worlds in the solar system. Not because of what you see, but because of what you don't. Because the winds on Neptune are the fastest anywhere, over 2,000 kilometers per hour, faster than the speed of sound. Winds so powerful that they can reshape the atmosphere constantly, tearing apart storms, stretching clouds across the planet, creating a system where nothing remains stable for long. And this happens in the coldest environment, which makes it even more extreme, because these winds are not driven by sunlight. They are driven by internal energy, meaning that Neptune is not just reacting to external conditions. It is powered from within, and that makes it dangerous in a different way, because the energy is constant, hidden, always present. Because if you were near Neptune, not on it, because there is no surface, but within its atmosphere, you would not see a stable environment. You would experience motion, continuous, unpredictable, because the winds would surround you, push you, pull you from every direction without warning, without pattern, because Neptune's atmosphere is not stable. It is constantly shifting, and that creates a kind of chaos, but not the visible chaos of Jupiter, a deeper chaos. One that is not immediately obvious, because Neptune hides its violence behind color, behind distance, behind an appearance that feels calm but isn't. And then there is gravity. Because Neptune may not be as massive as Jupiter, but it is still powerful enough to control its system, to influence objects, to pull, to reshape, to capture. Just like it did with Triton, and just like other planets, it can destroy, because anything that gets too close crosses the wrong boundary, enters a region where tidal forces become too strong, can be torn apart, broken into fragments, turned into debris. And that creates a contrast, because Neptune doesn't show its power openly. It doesn't look dangerous, but it is, because everything about it is extreme. The winds, the temperatures, the internal energy, all working together in a way that creates a system that is constantly in motion, constantly changing, constantly unpredictable. And that unpredictability is what makes it different, because Neptune is not just active, it is unstable, in a way that we are still trying to understand. And that makes it one of the most extreme planets we have, because it is not defined by what you see, but by what is happening beneath the surface. Neptune did not form in a calm system. It did not emerge in stability. Because the outer solar system where Neptune exists was once a place of chaos, a region where material was scattered, where objects moved unpredictably, where gravitational interactions shaped everything over time. And Neptune was part of that. Because early in the solar system's history, the giant planets did not necessarily form where they are now. They may have moved, shifted positions, interacted with each other, changing the structure of the entire system. And Neptune may have been part of that movement, because some models suggest that Neptune formed closer to the Sun, in a denser region of material, and was later pushed outward, migrating to its current position at the edge of the solar system. And that migration would not have been gentle, because as Neptune moved outward, it would have interacted with countless smaller objects, scattering them, capturing some, ejecting others, reshaping the outer solar system in the process. And this is where things become important. Because beyond Neptune lies the Kuiper Belt, a region filled with icy objects, remnants of the early solar system, and Neptune's movement may have played a major role in shaping that region, influencing the orbits of those objects, creating the structure we observe today. And this means that Neptune is not just a distant planet. It is a sculptor, a force that helped shape the outer solar system. Because its gravity, its movement, its interactions, all contributed to the distribution of material beyond it. And that includes objects like Pluto, because Pluto's orbit is influenced by Neptune, locked in a resonance that prevents collisions, creating a stable relationship between two objects that might otherwise cross paths. And this shows that even at the edge of the solar system, structure exists, patterns exist, because Neptune's influence extends far beyond itself, and that influence is still present today, because objects in the outer solar system continue to be shaped by Neptune's gravity, their orbits adjusted, their paths influenced, creating a system that is not random, but organized, even in the most distant regions. And that changes how we see Neptune, because it is not just a planet at the edge. It is part of the reason the edge looks the way it does. A world that helped define the boundary between the structured inner system and the scattered outer regions. And that makes it important, because it shows that even in the most distant parts of the solar system, there is still order, still structure, still influence, and Neptune is one of the reasons why. Neptune is the last, the final giant planet, the outermost world that still feels like part of a system we understand, and beyond it, everything changes. Because past Neptune, the solar system begins to fade into something else. Smaller objects, distant orbits, cold, scattered remnants of what once formed the planets. And that makes Neptune feel different, because it is not just another planet. It is the boundary, the last step before the familiar ends. And that gives it a kind of isolation. Because while Jupiter is surrounded by activity, by massive moons, by constant interaction, and Saturn has its rings, its complex system, Uranus has its strange tilt and hidden structure, Neptune stands alone, not because it has nothing, but because everything around it is more distant, more spread out, more quiet, because the sun is far away, its light is weak, its warmth barely reaches this far, and that creates a world that feels disconnected, a planet that exists at the edge of influence. Because even though Neptune is still bound to the Sun, still part of the solar system, it feels like it is on the edge of leaving it. Because one step further, and you are no longer in a system of planets. You are in a region of fragments, of debris, of objects that never became worlds, and Neptune sits right before that. A final presence, a last structure, before everything becomes less defined. And that creates a different kind of feeling, because Neptune is not just distant, it is alone in a way the other planets are not. Because there are no larger planets beyond it, no stronger gravitational forces shaping its region, no nearby giants influencing its motion. It is the outermost major world, and that makes it feel like a boundary, a marker, the end of something. And when you imagine it out there, a deep blue sphere moving slowly through the darkness, surrounded by faint moons, influenced by a distant sun, existing at the edge of a system that fades into space. It creates a sense of distance that is hard to fully understand, because Neptune is not just far, it is far enough that the solar system itself begins to feel small. And that changes how you see everything, because when you look at Neptune, you are not just looking at a planet. You are looking at the edge of where the familiar ends. And now, we've reached the end, not just of Neptune, but of the journey, because Neptune is not just the last planet. It is the point where everything begins to fade, because beyond this world, there are no more giants, no more familiar structures, no more planets that define the system, only fragments, only distant objects, only the slow transition into deep space. And that gives Neptune a different meaning, because it is not just a destination, it is a boundary, the final step before the solar system becomes something else. Because when you look at Neptune, when you imagine its deep blue color, its fast-moving storms, its quiet but violent atmosphere, its distant orbit around a fading sun, you begin to realize something. This is where the system ends, not suddenly, not sharply, but gradually, because Neptune is not a wall, it is a transition. A world that marks the point where structure begins to dissolve, where order becomes less defined, where the influence of the sun weakens and the vastness of space begins to take over. And that creates a final image. Because if you were to stand far beyond Neptune looking back toward the sun, you would see something small, a distant star, surrounded by faint points of light, the planets, barely visible, barely noticeable. And Neptune would be the last one you could still recognize. The final marker of a system that, from that distance, feels almost insignificant. And that changes everything, because it reminds you that even something as vast as the solar system is small, because beyond it, there is more, far more. More stars, more systems, more planets, more unknown. And that is where the journey leads, because Neptune is not the end of everything. It is just the end of what we know, and beyond it, there is still more to discover, more to understand, more to explore. And that is what makes this journey meaningful, because it does not end here. It continues. Beyond Neptune, beyond the solar system, into a universe that is far larger than anything we can fully imagine. At the very edge of the solar system, there is a world that used to be a planet, and then it was, Because Pluto is different, not just because of where it is, but because of what happened to it. Because for decades Pluto was the ninth planet, part of the system, part of the structure, something that belonged, taught in schools, printed in books, remembered as the final world. And then in 2006, everything changed because Pluto was reclassified. No longer a planet, now something else. A dwarf planet, a category that feels smaller, less important, as if something was taken away. And that change was not physical. Nothing about Pluto itself changed. It didn't shrink, it didn't move, it didn't lose anything. But our definition did. And that changed how we see it. Because Pluto didn't become smaller. We just decided it wasn't enough anymore. And that creates a strange feeling, because Pluto is still there, still orbiting the Sun, still part of the solar system. But now, it feels different, because it exists in between, not quite a planet, not just an asteroid, something else entirely. And that makes Pluto unique, because it is not just defined by what it is, but by what it used to be. And that history changes everything. Because when you look at Pluto now, you're not just looking at a distant world. You're looking at something that was redefined, reclassified, almost forgotten, but still there, still moving, still existing at the edge of everything. And that raises a question, because if Pluto didn't change, then why did we? Pluto doesn't move like the other planets. Because if you look at the solar system from above, most planets follow a pattern, nearly circular orbits, aligned along the same flat plane, moving in a way that feels organized, predictable, almost perfect. But Pluto breaks that pattern because its orbit is not circular, it is stretched, elliptical, bringing it closer to the Sun at some points, and much farther away at others. And that alone would make it different. But there's more, because Pluto's orbit is tilted, significantly, about 17 degrees off the main plane of the solar system, which means that instead of moving along the same flat disk as the other planets, Pluto moves above and below it, crossing through space in a path that feels disconnected from the rest. And that creates something unusual, because Pluto doesn't just orbit differently. It moves through the system in a way that feels almost chaotic, because at certain points in its orbit, Pluto is actually closer to the Sun than Neptune, which shouldn't happen, because Neptune is supposed to be the last planet. And yet, for a period of time, Pluto moves inside Neptune's orbit, crossing what should be a boundary. And that raises a question, because if their orbits cross, why don't they collide? Because in a system like this, that should be a risk, but it never happens, because Pluto and Neptune are locked in a gravitational resonance, a precise relationship, a pattern that ensures they never occupy the same position at the same time. Because for every 3 orbits Neptune makes around the Sun, Pluto completes 2, a perfect ratio, a synchronized motion that keeps them apart, even though their paths intersect. And that creates something fascinating, because it shows that even in what looks like chaos, there is structure. Because Pluto's orbit may look irregular, but it is not random. It is controlled, balanced, maintained by the gravity of Neptune. And that means Pluto is not just drifting at the edge of the solar system. It is part of a system, even if it doesn't look like it, because its orbit is different, tilted, stretched, crossing boundaries that other planets don't. And that makes it feel separate, disconnected, almost like it doesn't belong. And that idea connects back to its classification. Because Pluto doesn't behave like the other planets, it doesn't follow the same rules, it doesn't fit the pattern, and that may be part of the reason why it was redefined, because Pluto is not just smaller, it is different, in the way it moves, in the way it exists, in the way it interacts with the rest of the solar system, and that difference is what makes it so interesting. Because Pluto is not just at the edge of the solar system, it is at the edge of what we consider a planet. For a long time, Pluto was just a dot, too far away, too small, too distant to see clearly, just a blurry point of light in the darkness. And then, in 2015, everything changed. Because when the spacecraft New Horizons finally reached Pluto after traveling for nearly a decade across billions of kilometers, it showed us something no one expected. Pluto wasn't empty. It wasn't just a frozen rock. It had structure, detail, and something that felt almost intentional, a heart. Because one of the most iconic features on Pluto's surface is a massive, bright region shaped like a heart, known as Tombaugh Regio, stretching across a large part of the planet, standing out clearly against the darker terrain around it. And that changes everything. Because suddenly, Pluto is no longer just distant. It becomes recognizable, memorable, almost emotional. Because a heart is not something you expect to find on a world this far away, but it's there, and it's real. And when you look closer, it becomes even more interesting. Because this heart is not just a visual feature, it is a region of activity. Because part of it, called Sputnik Planitia, is a vast basin filled with nitrogen ice, smooth, bright, and constantly reshaped by slow-flowing processes, where the ice behaves almost like a liquid over long periods of time, moving, circulating, creating patterns that show Pluto is not completely inactive. Because even in this extreme cold, there is motion. Because Pluto is around minus 220 degrees Celsius, cold enough that most substances freeze solid. But nitrogen, methane, carbon monoxide can still exist in different states, creating a surface that is not static but slowly changing. And that makes Pluto feel different. Because it is not just a dead world. It is active, but in a very slow way. Because instead of rapid storms or fast winds, Pluto changes over years, decades, centuries, processes that are almost invisible unless you observe them over long periods of time. And that creates a different kind of motion, a quiet motion, a slow evolution. And when you combine that with the heart-shaped region, it creates something unique. Because Pluto becomes more than just a distant object. It becomes a world with character, a world that surprised us. Because we expected something simple, something uninteresting. But instead, we found detail, complexity, and something that feels almost symbolic. Because out at the edge of the solar system, in one of the coldest, darkest places we've ever explored, there is a heart, and that makes Pluto unforgettable. Pluto shouldn't have an atmosphere, it's too small, its gravity is too weak, its temperature is too low. Everything about it suggests one thing: it shouldn't be able to hold gas around it. And yet, it does, because Pluto has a thin atmosphere, made mostly of nitrogen with traces of methane and carbon monoxide, forming a fragile layer that surrounds the planet, creating something that feels almost impossible at that distance. But this atmosphere is not stable because it doesn't stay. It comes and goes. Because as Pluto moves along its orbit, getting closer to the Sun, even though that closer is still extremely far, the slight increase in temperature is enough to cause the frozen nitrogen on its surface to sublimate, turning directly from ice into gas, rising into the sky, forming an atmosphere. A thin, hazy layer, barely there, but real. And then, as Pluto moves away again, that atmosphere begins to collapse because the temperature drops and the gas freezes, falling back to the surface as ice, disappearing, leaving Pluto almost airless again. And that creates something strange, because Pluto does not have a constant sky, it has a temporary one, a world where the atmosphere appears and then vanishes, a cycle that takes decades. Because Pluto's orbit around the Sun takes about 248 Earth years, meaning that these changes happen slowly, gradually, over long periods of time. And that makes it difficult to observe, because by the time we begin to understand one phase, it is already changing. And that creates a sense of instability, because Pluto is not just distant, it is variable because its environment is not fixed. It shifts, changes, transforms, depending on where it is in its orbit. And that gives Pluto a different feeling because it is not just cold. It is dynamic in a way that is subtle because its atmosphere is not thick, not powerful, but it is fragile. And that fragility makes it feel temporary, because everything about it can disappear, and that includes the sky itself. And when you imagine standing on Pluto, looking up at a thin, hazy atmosphere, knowing that over time, that sky will fade, will collapse, will freeze and fall back to the surface, it creates a different kind of image. Because Pluto is not just a world with an atmosphere. It is a world where the atmosphere is not guaranteed, a place where even the sky is temporary. Pluto is not alone, and unlike most planets, it doesn't just have moons. It has something closer to a partner, because its largest moon, Charon, is not small compared to Pluto. It is massive, about half the size of Pluto itself, which creates something unusual. Because instead of Pluto simply dominating its moon, the two bodies interact in a much more balanced way. Because they don't orbit like a typical planet and moon. They orbit each other. Because the center of their motion, the barycenter, lies outside of Pluto's surface, which means that Pluto and Charon both move around a point in space between them, creating what is essentially a binary system. Two worlds locked together, and that changes everything, because Pluto is not just a planet with moons, it is part of a pair, and that creates a unique dynamic, because Pluto and Charon are tidally locked, meaning that the same side of Pluto always faces Charon, and the same side of Charon always faces Pluto. They never change their view of each other, always seeing the same hemisphere, forever. And that creates something strange, because if you were standing on Pluto in the hemisphere facing Charon, you would see it fixed in the sky, not rising, not setting, just hanging there, always present. And on the opposite side of Pluto, you would never see it at all. And that creates two completely different worlds on the same planet, one with a constant moon, one with none. And that difference changes how Pluto feels, because it is not uniform, it is divided, not just by geography, but by perspective. And Charon itself is just as strange, because its surface is dark in some regions, lighter in others, with a massive canyon system stretching across it, suggesting that it has experienced geological activity in the past, possibly even internal processes that shaped its surface. And that makes it more than just a passive object, because Charon is a world, not just a moon, a place with its own structure, its own history, its own features. And together, Pluto and Charon form something unique, because they are not just a planet and a moon, they are a system, a pair of worlds, locked together, moving through space as one. And that makes Pluto even more unusual, because it doesn't follow the typical rules. It doesn't behave like the other planets. It exists in a way that feels different, a world that is not alone, but not quite part of a standard system either. And that makes it one of the most unique places in the entire solar system, because it is not just a planet, it is part of something else, something shared, something balanced, something rare. Pluto is not loud, it doesn't have massive storms, it doesn't shine brightly, it doesn't dominate its surroundings. Everything about it is quiet, subtle, distant. And yet, it feels meaningful, because Pluto is not just a single world. It is part of a small system, a collection of objects moving together at the edge of the solar system, far from the influence of the sun, far from the activity of the inner planets, existing in a region where everything slows down. Because beyond Neptune, space begins to feel different, less crowded, less structured, more empty. And Pluto exists within that. A region where objects are spread out, where distances are large, where interactions are rare. And that creates a different kind of environment, because Pluto is not shaped by constant collisions or strong gravitational forces from nearby planets. It exists in a quieter space, a place where change happens slowly, where motion continues, but without disruption. And that gives the entire system a different feeling, because Pluto and its moons are not part of a dense, active region. They are part of something more isolated, more distant. And that isolation creates something almost peaceful, because nothing moves quickly, nothing changes suddenly. Everything happens over long periods of time, orbits that take hundreds of years, processes that take centuries to become visible, a system that exists in slow motion. And that makes Pluto feel different from every other planet we've explored, because it is not defined by energy, not by motion, not by power, but by stillness, by quiet, by distance. And that creates a different kind of importance, because Pluto is not impressive in the way Jupiter is. It is not visually dominant like Saturn. It does not stand out with obvious features, but it has something else, something subtle, because Pluto represents the edge, the point where the solar system transitions into something else, because beyond Pluto, everything is direct, everything is extreme. Because when sunlight reaches Pluto, even though it is weak, it hits the surface without interference. And when it disappears, the temperature drops immediately. And that creates a world where conditions are not balanced, not moderated, but raw. And that raw environment makes Pluto feel different because it is not just cold. It is empty because there is no sound, no movement, no activity that you would notice. Because even the surface, which does change over time, does so slowly that it appears frozen, unchanging. And that creates a different kind of danger, because Pluto is not a place where something happens to you. It is a place where nothing happens at all, because the cold stops everything. Because the vacuum removes everything. Because the environment does not support motion, or life, or energy in the way we understand it. And that makes Pluto one of the most extreme environments we know, not because of what it does, but because of what it does. Because it is a world where everything has slowed down to the point where it almost feels like time itself is moving differently. And that creates a final thought, because Pluto is not loud, not violent, not chaotic, but it is still one of the most hostile places in the solar system, because sometimes the most dangerous environments are the ones that feel completely still. Pluto is not just a distant world. It is ancient, older than anything we've ever built, older than life on Earth, a remnant from the very beginning of the solar system. Because Pluto didn't form like the inner planets. It didn't grow in a dense region close to the Sun where heat and collisions shaped large, solid worlds. It formed far away, in the outer regions, where temperatures were low, where material was sparse, where ice could exist, and that changes everything, because Pluto is not made primarily of rock. It is a mixture, ice, rock, frozen gases, materials that, closer to the Sun, would never remain stable. And that makes Pluto different from the planets we usually imagine, because it is not a world that formed in a structured environment. It formed in a region that was chaotic. Because the outer solar system was filled with countless small objects, colliding, merging, separating, interacting in ways that created a wide range of bodies. And Pluto is one of those bodies, one of the largest survivors. Because beyond Neptune lies the Kuiper Belt, a vast region filled with icy remnants, objects that never became full planets, left over from the formation of the solar system. And Pluto is part of that, not separate from it, but embedded within it, a member of a population. And that changes how you see it, because Pluto is not just a unique object, it is an example, a representative of a class of worlds that exist far beyond the inner planets. And that makes it important, because by studying Pluto, we are not just learning about one object. We are learning about an entire region, an entire category of worlds. And that region is still largely unexplored, because we have only visited Pluto once, and we have not yet explored the Kuiper Belt in detail, which means that Pluto is one of our only direct glimpses into that part of the solar system, a window into the past, because these objects have changed very little over billions of years. Because they are far from the Sun, far from major gravitational disturbances, far from the processes that reshape planets closer in. And that means Pluto still holds information from the early solar system, from a time when everything was forming, when planets were still developing, when the structure we see today did not yet exist. And that makes Pluto more than just distant. It makes it valuable because it preserves something, a record, a piece of history that has remained mostly unchanged. And that gives it a different kind of importance, because Pluto is not just a world at the edge. It is a memory a relic of a time when the solar system was still forming. And that is what makes it so interesting, because when you look at Pluto, you are not just looking far away. You are looking back in time. Pluto feels different, not because of what it has, but because of where it is. Because Pluto is far, far beyond the main planets, far beyond the warmth of the sun, far beyond the region where things feel connected. And that distance creates something else. Isolation, because Pluto is not surrounded by large planets. It does not sit in a dense system of moons and rings like Jupiter or Saturn. It exists in a region where objects are scattered, where space feels empty, where distances between worlds are vast, and that makes Pluto feel alone. Because even though it has moons, even though it is part of the Kuiper belt, it still feels separate because everything around it is smaller, colder, less defined, because Pluto is one of the largest objects out there. And that gives it a strange role, because it is not a dominant planet. But it is not just another object either. It sits in between, just like its classification, just like its orbit, just like its identity. And that creates a kind of quiet tension, because Pluto used to belong. It used to be part of the main system, part of the planets. And now it is, and that change lingers, because even though nothing physical happened, the meaning changed because Pluto didn't move. We just moved it in our understanding, in our definitions, and that creates a strange perspective because Pluto is still doing the same thing it always did, orbiting the sun, moving through space, existing at the edge of the solar system. But now, it feels like it was left behind, not in reality, but in perception. Because we changed how we categorize it, how we talk about it, how we remember it. And that creates something emotional, because Pluto becomes more than just an object. It becomes a symbol of how our understanding changes, of how definitions evolve, of how something can remain the same, while the way we see it changes completely. And that makes Pluto unique, because no other planet has gone through that. No other world has been redefined in such a visible way. And that gives it a different kind of identity, because Pluto is not just a distant object. It is a reminder that what we consider important can change, that what we classify can change, that even something as fundamental as a planet is not just about what exists, but about how we define it. And that makes Pluto more than just a world at the edge. It makes it something that exists between categories, between definitions, between what it was and what it is now. And that is what makes it unforgettable. And now we reach the end of Pluto's story. But unlike the other planets, this ending feels different, because Pluto didn't disappear, it didn't break apart, it didn't change its path, it didn't leave the solar system. It is still there, exactly where it has always been, moving slowly, orbiting the sun, existing at the edge of everything. And yet, something about it feels different, because Pluto is no longer what it once was, not physically, but in how we see it, because once it was the ninth planet, the final world, the edge of the system, and now it is something else. A dwarf planet, a member of a larger group, part of a region rather than the end of one. And that change stays with it, because Pluto is now defined by two identities: what it was and what it is. And that duality makes it unique, because no other world carries that kind of history. No other planet has been redefined in such a way. And that gives Pluto something the others don't have: a story. Because when you look at Pluto, you're not just looking at a distant, frozen world. You're looking at something that represents change, something that shows how our understanding evolves. Because Pluto didn't change. We did. Our definitions, our categories, our way of organizing the universe. And that realization shifts the perspective, because it reminds you that the solar system is not just a collection of objects. It is also a reflection of how we interpret those objects, how we classify them, how we decide what they mean. And Pluto sits right at the center of that idea. A world that forces us to question what a planet really is, what matters, what defines something. And that makes it more than just a distant object, because Pluto is not just part of the solar system. It is part of the story of how we understand it. And even now, far beyond Neptune, in the cold, quiet darkness, Pluto continues to move, unaffected, unchanged, still there. And maybe that's the most important part, because no matter what we call it, no matter how we define it, no matter how we classify it, Pluto remains exactly what it has always been: a world at the edge, still orbiting, still existing, still part of the story. And with that, we've reached the end of our journey, from the burning surface of Mercury to the thick clouds of Venus, from our home, Earth, to the red deserts of Mars, through the giants Jupiter and Saturn, past the silent mystery of Uranus, all the way to the distant storms of Neptune, and finally to Pluto, the world at the edge that was never really lost. We've traveled across our entire solar system, every planet, every story, every mystery, and now we're here at the end of it all. And if you're still listening right now, that honestly means a lot, because this wasn't just a video. It was a journey, a quiet one, a long one, and you stayed until the very end. So really, props to you. And maybe, just maybe, you're starting to see space a little differently now, not just as something far away, but as something real, something connected, something we're all a part of. So thank you for being here. Thank you for listening. And if you enjoyed this journey, I'd really appreciate it if you could leave a like, and maybe even subscribe, so we can keep exploring the universe together. There's still so much out there, and this is just the beginning.